Section 21 of Optics. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Pamela Krantz. Opticks by Isaac Newton. Book 2, Part 1. Observations 17 through 24. Observation 17. If a bubble be blown with water first made tenacious by dissolving a little soap in it, 'tis a common observation that after a while it will appear tinged with a great variety of Colours. To defend these bubbles from being agitated by the external air, whereby their Colours are irregularly moved one among another, so that no accurate observation can be made of them, as soon as I had blown any of them, I covered it with a clear glass, and by that means its Colours emerged in a very regular order, like so many concentric rings encompassing the top of the bubble. And as the bubble grew thinner by the continual subsiding of the water, these rings dilated slowly and overspread the whole bubble, descending in order to the bottom of it, where they vanished successively. In the meanwhile, after all the Colours were emerged at the top, there grew in the center of the rings a small round black spot, like that in the first observation, which continually dilated itself till it became sometimes more than 1/2 or 3/4 of an inch in breadth before the bubble broke. At first I thought there had been no light reflected from the water in that place, but observing it more curiously, I saw within it several smaller round spots, which appeared much blacker and darker than the rest, whereby I knew that there was some reflection at the other places which were not so dark as those spots. And by farther trial I found that I could see the images of some things as of a candle or the sun, very faintly reflected, not only from the great black spot, but also from the little darker spots which were within it. Besides the aforesaid coloured rings, there would often appear small spots of Colours, ascending and descending up and down the sides of the bubble, by reason of some inequalities in the subsiding of the water, and sometimes small black spots generated at the sides would ascend up to the larger black spot at the top of the bubble, and unite with it. Observation 18. Because the Colours of these bubbles were more extended and lively than those of the air thinned between two glasses, and so more easy to be distinguished, I shall here give you a farther description of their order, as they were observed in viewing them by reflection of the skies when of a white Colour, whilst a black substance was placed behind the bubble. And they were these: red blue, red blue, red blue, red green, red yellow, green blue purple, red yellow green blue violet, red yellow white blue black. The three first successions of red and blue were very dilute and dirty, especially the first, where the red seemed in a manner to be white. Among these there was scarce any other Colour sensible besides red and blue, only the blues, and principally the second blue, inclined a little to green. The fourth red was also dilute and dirty, but not so much as the former three. After that succeeded little or no yellow, but a copious green, which at first inclined a little to yellow, and then became a pretty brisk and good willow green, and afterwards changed to a bluish Colour, but there succeeded neither blue nor violet. The fifth red at first inclined very much to purple, and afterwards became more bright and brisk, but yet not very pure. This was succeeded with a very bright and intense yellow, which was but little in quantity, and soon changed to green. But that green was copious and something more pure, deep and lively than the former green. After that followed an excellent blue of a bright sky Colour, and then a purple, which was less in quantity than the blue, and much inclined to red. The sixth red was at first of a very fair and lively scarlet, and soon after of a brighter Colour, being very pure and brisk, and the best of all the reds. Then after a lively orange followed an intense, bright and copious yellow, which was also the best of all the yellows, and this changed first to a greenish yellow, and then to a greenish blue. But the green between the yellow and the blue was very little and dilute, seeming rather a greenish white than a green. The blue which succeeded became very good, and of a very bright sky Colour, but yet something inferior to the former blue, and the violet was intense and deep, with little or no redness in it, and less in quantity than the blue. In the last red appeared a tincture of scarlet next to violet, which soon changed to a brighter Colour, inclining to an orange, and the yellow which followed was at first pretty good and lively, but afterwards it grew more dilute until by degrees it ended in perfect whiteness. And this whiteness, if the water was very tenacious and well tempered, would slowly spread and dilate itself over the greater part of the bubble, continually growing paler at the top, where at length it would crack in many places, and those cracks as they dilated would appear of a pretty good but yet obscure and dark sky colour, the white between the blue spots diminishing until it resembled the threads of an irregular network, and soon after vanished and left all the upper part of the bubble of the said dark blue Colour. And this Colour, after the aforesaid manner, dilated itself downwards, until sometimes it hath overspread the whole bubble. In the meanwhile at the top, which was of a darker blue than the bottom, and appeared also full of many round blue spots, something darker than the rest, there would emerge one or more very black spots, and within those, other spots of an intenser blackness, which I mentioned in the former Observation, and these continually dilated themselves until the bubble broke. If the water was not very tenacious, the black spots would break forth in the white, without any sensible intervention of the blue, and sometimes they would break forth within the precedent yellow, or red, or perhaps within the blue of the second order, before the intermediate Colours had time to display themselves. By this description you may perceive how great an affinity these Colours have with those of air described in the fourth Observation, although set down in a contrary order, by reason that they begin to appear when the bubble is thickest, and are most conveniently reckoned from the lowest and thickest part of the bubble upwards. Observation 19. Viewing in several oblique positions of my Eye the rings of Colours emerging on the top of the bubble, I found that they were sensibly dilated by increasing the obliquity, but yet not so much by far as those made by thinned Air in the seventh Observation. For there they were dilated so much, as when viewed most obliquely, to arrive at a part of the Plate more than 12 times thicker than that where they appeared when viewed perpendicularly, whereas in this case the thickness of the water at which they arrived when viewed most obliquely was to that thickness which exhibited them by perpendicular Rays, something less than as 8 to 5. By the best of my Observations it was between 15 and 15½ to 10, an increase about 24 times less than in the other case. Sometimes the bubble would become of an uniform thickness all over, except at the top of it near the black spot, as I knew, because it would exhibit the same appearance of Colours in all positions of the eye. And then the Colours which were seen at its apparent circumference by the obliquest Rays would be different from those that were seen in other places, by Rays less oblique to it. And diverse Spectators might see the same part of it of differing Colours, by viewing it at very differing obliquities. Now observing how much the Colours at the same places of the bubble, or at diverse places of equal thickness, were varied by the several obliquities of the Rays, by the assistance of the 4th, 14th, 16th, and 18th Observations, as they are hereafter explained, I collect the thickness of the water requisite to exhibit any one and the same Colour, at several obliquities, to be very nearly in the proportion expressed in this Table. Incidence on the water, 0 degrees 0 minutes. Refraction into the water, 0 degrees 0 minutes. Thickness of the water, 10 parts. Incidence on the water, 15 degrees 0 minutes. Refraction into the water, 11 degrees 11 minutes. Thickness of the water, 10 1/4 parts. Incidence on the water, 30 degrees 0 minutes. Refraction into the water, 22 degrees 1 minute. Thickness of the water, 10 4/5 parts. Incidence on the water, 45 degrees 0 minutes. Refraction into the water, 32 degrees 2 minutes. Thickness of the water, 11 4/5 parts. Incidence on the water, 60 degrees 0 minutes. Refraction into the water, 40 degrees 30 minutes. Thickness of the water, 13 parts. Incidence on the water 75 degrees 0 minutes. Refraction into the water 46 degrees 25 minutes. Thickness of the water 14 1/2 parts. Incidence on the water 90 degrees 0 minutes. Refraction into the water 48 degrees 35 minutes. Thickness of the water 15 1/5 parts. In the two first columns are expressed the obliquities of the rays to the superficies of the water, that is, their angles of incidence and refraction, where I suppose that the sines which measure them are in round numbers, as 3 to 4, though probably the dissolution of soap in the water may a little alter its refractive virtue. In the third column, the thickness of the bubble, at which any one Colour is exhibited in those several obliquities, is expressed in parts, of which 10 constitute its thickness when the Rays are perpendicular, and the rule found by the 7th Observation agrees well with these measures, if duly applied, namely, that the thickness of a Plate of Water requisite to exhibit one and the same Colour at several obliquities of the Eye, is proportional to the secant of an Angle, whose Sine is the first of 106 arithmetical mean proportionals between the Sines of Incidence and Refraction counted from the lesser Sine, that is, from the Sine of Refraction when the Refraction is made out of Air into Water, otherwise from the Sine of Incidence. I have sometimes observed, that the Colours which arise on polished Steel by heating it, or on Bell Metal, and some other metalline Substances, when melted and poured on the ground, where they may cool in the open Air, have, like the Colours of Water Bubbles, been a little changed by viewing them at diverse obliquities, and particularly that a deep blue or violet, when viewed very obliquely, hath been changed to a deep red. But the changes of these Colours are not so great and sensible as of those made by Water. For the Scoria or vitrified part of the Metal, which most Metals, when heated or melted, do continually protrude and send out to their surface, and which by covering the Metals in form of a thin glassy skin causes these Colours, is much denser than Water, and I find that the change made by the obliquation of the Eye is least in Colours of the densest thin Substances. Observation 20. As in the 9th Observation, so here the Bubble by transmitted Light appeared of a contrary Colour to that which it exhibited by reflection. Thus when the Bubble being looked on by the Light of the Clouds reflected from it seemed red at its apparent circumference, if the Clouds at the same time or immediately after were viewed through it, the Colour at its circumference would be blue. And on the contrary, when by reflected Light it appeared blue, it would appear red by transmitted Light. Observation 21. By wetting very thin Plates of Muscovy Glass, whose thinness made the like Colours appear, the Colours became more faint and languid, especially by wetting the Plates on that side opposite to the Eye. But I could not perceive any variation of their Species. So then the thickness of a Plate requisite to produce any Colour depends only on the density of the Plate, and not on that of the ambient medium. And hence by the 10th and 16th Observations may be known the thickness which bubbles of water or plates of Muscovy glass or other substances have at any Colour produced by them. Observation 22. A thin transparent body which is denser than its ambient medium exhibits more brisk and vivid Colours than that which is so much rarer, as I have particularly observed in the Air and Glass. For blowing glass very thin at a Lamp Furnace, those Plates encompassed with Air did exhibit Colours much more vivid than those of Air made thin between two Glasses. Observation 23. Comparing the quantity of Light reflected from the several Rings, I found that it was most copious from the first or inmost, and in the exterior Rings became gradually less and less. Also the whiteness of the first Ring was stronger than that reflected from those parts of the thin medium or Plate which were without the Rings, as I could manifestly perceive by viewing at a distance the Rings made by the two Object Glasses, or by comparing two Bubbles of Water blown at distant times, in the first of which the whiteness appeared, which succeeded all the Colours, and in the other the whiteness which preceded them all. Observation 24. When the two Object glasses were laid upon one another so as to make the Rings of the Colours appear, though with my naked eye I could not discern above 8 or 9 of those Rings, yet by viewing them through a Prism I have seen a far greater multitude, insomuch that I could number more than 40, besides many others, that were so very small and close together, that I could not keep my eye steady on them severally so as to number them, but by their extent I have sometimes estimated them to be more than 100. And I believe the Experiment may be improved to the discovery of far greater numbers, for they seem to be really unlimited, though visible only so far as they can be separated by the Refraction of the Prism, as I shall hereafter explain. But it was but one side of these Rings, namely, that towards which the Refraction was made, which by that Refraction was rendered distinct, and the other side became more confused than when viewed by the naked eye, insomuch that there I could not discern above 1 or 2, and sometimes none of those Rings, of which I could discern 8 or 9 with my naked eye. And their segments or arcs, which on the other side appeared so numerous, for the most part exceeded not the third part of a circle. If the Refraction was very great, or the Prism very distant from the Object glasses, the middle part of those arcs became also confused, so as to disappear and constitute an even whiteness, whilst on either side their ends, as also the whole arcs farthest from the Center, became distincter than before, appearing in the form as you see them designed in the 5th Figure. The arcs, where they seemed distinctest, were only white and black successively, without any other Colours intermixed. But in other places there appeared Colours whose order was inverted by the Refraction in such manner, that if I first held the Prism very near the Object glasses, and then gradually removed it farther off towards my eye, the Colours of the 2nd, 3rd, 4th, and following Rings shrunk towards the white that emerged between them, until they wholly vanished into it at the middle of the arcs, and afterwards emerged again in a contrary order, but at the ends of the arcs they retained their order unchanged. I have sometimes so laid one Object glass upon the other, that to the naked eye they have all over seemed uniformly white, without the least appearance of any of the coloured Rings, and yet by viewing them through a Prism, great multitudes of those Rings have discovered themselves, and in like manner plates of Muscovy glass, and bubbles of glass blown at a Lamp furnace, which were not so thin as to exhibit any Colours to the naked eye, have through the Prism exhibited a great variety of them ranged irregularly up and down in the form of waves. And so bubbles of water, before they began to exhibit their Colours to the naked eye of a bystander, have appeared through a Prism girded about with many parallel and horizontal Rings, to produce which effect it was necessary to hold the Prism parallel, or very nearly parallel to the Horizon, and to dispose it so that the Rays might be refracted upwards. End of Section 21. Recorded by Pamela Krantz. Section 22 of Optics. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Pamela Krantz. Opticks by Isaac Newton. Book 2, Part 2, Section 1. Remarks upon the foregoing observations. Having given my observations of these Colours, before I make use of them to unfold the causes of the Colours of natural bodies, it is convenient that by the simplest of them, such as are the 2nd, 3rd, 4th, 9th, 12th, 18th, 20th, and 24th, I first explain the more compounded. And first, to show how the Colours in the 4th and 18th Observations are produced, let there be taken in any right line from the point Y, in Fig. 6, the lengths YA, YB, YC, YD, YE, YF, YG, YH, in proportion to one another, as the cube roots of the squares of the numbers 1/2, 9/16, 3/5, 2/3, 3/4, 5/6, 8/9, 1, whereby the lengths of a musical chord to sound all the notes in an eighth are represented, that is, in the proportion of the numbers 6300, 6814, 7114, 7631, 8255, 8855, 9243, 10,000. And at the points A, B, C, D, E, F, G, H, let perpendiculars A alpha, B beta, etc. be erected, by whose intervals the extent of the several Colours set underneath against them is to be represented. Then divide the line A alpha in such proportion as the numbers 1, 2, 3, 5, 6, 7, 9, 10, 11, etc. set at the points of division denote, and through those divisions from Y draw lines 1I, 2K, 3L, 5M, 6N, 7O, etc. Now if A2 be supposed to represent the thickness of any thin transparent body, at which the outmost violet is most copiously reflected in the first ring, or series of Colours, then by the 13th observation HK will represent its thickness, at which the utmost red is most copiously reflected in the same series. Also by the 5th and 16th observations A6 and HN will denote the thicknesses at which those extreme Colours are most copiously reflected in the second series, and A10 and HQ the thicknesses at which they are most copiously reflected in the third series, and so on. And the thickness at which any of the intermediate Colours are reflected most copiously will, according to the 14th observation, be defined by the distance of the line AH from the intermediate parts of the lines 2K, 6N, 10Q, etc., against which the names of those Colours are written below. But farther, to define the latitude of these Colours in each ring or series, let A1 design the least thickness and A3 the greatest thickness, at which the extreme violet in the first series is reflected, and let HI and HL design the like limits for the extreme red, and let the intermediate Colours be limited by the intermediate parts of the lines 1I and 3L, against which the names of those Colours are written, and so on. But yet with this caution, that the Reflexions be supposed strongest at the intermediate spaces 2K, 6N, 10Q, etc., and from thence to decrease gradually towards these limits 1I, 3L, 5M, 7O, etc. on either side, where you must not conceive them to be precisely limited, but to decay indefinitely. And whereas I have assigned the same latitude to every series, I did it because although the Colours in the first series seem to be a little broader than the rest, by reason of a stronger reflection there, yet that inequality is so insensible as scarcely to be determined by observation. Now according to this description, conceiving that the Rays originally of several Colours are by turns reflected at the spaces 1I, L3, 5M, O7, 9PR, 11, etc., and transmitted at the spaces AHI1, 3LM5, 7OP9, etc., it is easy to know what colour must be in the open air be exhibited at any thickness of a transparent thin body. For if a ruler be applied parallel to AH, at that distance from it by which the thickness of the body is represented, the alternate spaces 1IL3, 5MO7, etc., which it crosseth, will denote the reflected original Colours, of which the colour exhibited in the open air is compounded. Thus if the constitution of the green in the third series of Colours be desired, apply the ruler as you see at pi rho sigma phi, and by its passing through some of the blue at pi, and yellow at sigma, as well as through the green at rho, you may conclude that the green exhibited at that thickness of the body is principally constituted of original green, but not without a mixture of some blue and yellow. By this means you may know how the Colours from the center of the rings outward ought to succeed in order as they were described in the 4th and 18th Observations. For if you move the Ruler gradually from AH through all distances, having passed over the first space which denotes little or no reflection to be made by thinnest substances, it will first arrive at 1 the violet, and then very quickly at the blue and green, which together with that violet compound blue, and then at the yellow and red, by whose farther addition that blue is converted into whiteness, which whiteness continues during the transit of the edge of the Ruler from I to 3, and after that by the successive deficience of its component Colours turns first to compound yellow and then to red, and last of all the red ceaseth at L. Then begin the Colours of the second Series, which succeed in order during the transit of the edge of the Ruler from 5 to O, and are more lively than before, because more expanded and severed. And for the same reason, instead of the former white, there intercedes between the blue and yellow a mixture of orange, yellow, green, blue, and indigo, all which together ought to exhibit a dilute and imperfect green. So the Colours of the third Series all succeed in order, first the violet, which a little interferes with the red of the second order, and is thereby inclined to a reddish purple, then the blue and green, which are less mixed with other Colours, and consequently more lively than before, especially the green. Then follows the yellow, some of which towards the green is distinct and good, but that part of it towards the succeeding red, as also that red is mixed with the violet and blue of the fourth Series, whereby various degrees of red very much inclining to purple are compounded. This violet and blue, which should succeed this red, being mixed with and hidden in it, there succeeds a green. And this at first is much inclined to blue, but soon becomes a good green, the only unmixed and lively Colour in this fourth Series. For as it verges towards the yellow, it begins to interfere with the Colours of the fifth Series, by whose mixture the succeeding yellow and red are very much diluted and made dirty, especially the yellow, which being the weaker Colour is scarce able to show itself. After this, the several Series interfere more and more, and their Colours become more and more intermixed, till after 3 or 4 more revolutions in which the red and blue predominate by turns, all sorts of Colours are in all places pretty equally blended, and compound an even whiteness. And since by the 15th Observation the Rays endued with one Colour are transmitted, where those of another Colour are reflected, the reason of the Colours made by the transmitted Light in the 9th and 20th Observations is from hence evident. If not only the order and species of these Colours, but also the precise thickness of the Plate, or thin Body at which they are exhibited, be desired in parts of an Inch, that may be also obtained by assistance of the 6th or 16th Observations. For according to those Observations, the thickness of the thinned Air, which between two Glasses exhibited the most luminous parts of the first 6 Rings, were 1/178,000, 3/178,000, 5/178,000, 7/178,000, 9/178,000, 11/178,000 parts of an Inch. Suppose the Light reflected most copiously at these thicknesses be the bright citrine yellow, or confine of yellow and orange, and these thicknesses will be f lambda, f mu, f nu, f xi, f omicron, f iota, and this being known, it is easy to determine what thickness of air is represented by g phi, or by any other distance of the Ruler from AH. But farther, since by the 10th Observation the thickness of air was to the thickness of water, which between the same Glasses exhibited the same Colour as 4 to 3, and by the 21st Observation the Colours of thin Bodies are not varied by varying the ambient medium, the thickness of a bubble of water exhibiting any Colour will be 3/4 of the thickness of air producing the same Colour. And so according to the same 10th and 21st Observations, the thickness of a Plate of Glass, whose Refraction of the mean refrangible Ray is measured by the proportion of the Sines 31 to 20, may be 20/31 of the thickness of air producing the same Colours, and the like of other Mediums. I do not affirm that this proportion of 20 to 31 holds in all the Rays, for the Sines of other sorts of Rays have other proportions. But the differences of those proportions are so little that I do not here consider them. On these grounds I have composed the following Table, wherein the thickness of Air, Water, and Glass, at which each Colour is most intense and specific, is expressed in parts of an Inch divided into 10,100,000 equal parts. Now if this Table be compared with the sixth Scheme, you will there see the constitution of each Colour as to its Ingredients, or the original Colours of which it is compounded, and thence be enabled to judge of its intenseness or imperfection, which may suffice in explication of the 4th and 18th Observations, unless it be farther desired to delineate the manner how the Colours appear when the two Object glasses are laid upon one another. To do which, let there be described a large Arc of a Circle, and a straight Line which may touch that Arc, and parallel to that tangent several occult Lines, at such distances from it as the numbers set against the several Colours in the Table denote. For the Arc and its tangent will represent the Superficies of the Glasses terminating the interjacent Air, and the places where the occult Lines cut the Arc will show at what distances from the Center, or point of contact, each Colour is reflected. The thickness of coloured Plates and Particles of their Colours of the first Order. Very black, Air 1/2, Water 3/8, Glass 10/31. Black, Air 1, Water 3/4, Glass 20/31. Beginning of black, Air 2, Water 1 1/2, Glass 1 2/7. Blue, Air 2 2/5, Water 1 4/5, Glass 1 11/22. White, Air 5 1/4, Water 3 7/8, Glass 3 2/5. Yellow, Air 7 1/9, Water 5 1/3, Glass 4 3/5. Orange, Air 8, Water 6, Glass 5 1/6. Red, Air 9, Water 6 3/4, Glass 5 4/5. Of the second order. Violet, Air 11 1/6, Water 8 3/8, Glass 7 1/5. Indigo, Air 12 5/6, Water 9 5/8, Glass 8 2/11. Blue, Air 14, Water 10 1/2, Glass 9. Green, Air 15 1/8, Water 11 2/3, Glass 9 5/7. Yellow, Air 16 2/7, Water 12 1/5, Glass 10 2/5. Orange, Air 17 2/9, Water 13, Glass 11 1/9. Bright red, Air 18 1/3, Water 13 3/4, Glass 11 5/6. Scarlet, Air 19 2/3, Water 14 3/4, Glass 12 2/3. Of the third order. Indigo, Air 22 1/10, Water 16 4/7, Glass 14 1/4. Blue, Air 23 2/5, Water 17 11/20, Glass 15 1/10. Green, Air 25 1/5, Water 18 9/10, Glass 16 1/4. Yellow, Air 27 1/7, Water 20 1/3, Glass 17 1/2. Red, Air 29, Water 21 3/4, Glass 18 5/7. Bluish red, Air 32, Water 24, Glass 20 2/3. Of the fourth order. Green, Air 35 2/7, Water 26 1/2, Glass 22 3/4. Yellowish green, Air 36, Water 27, Glass 23 2/9. Red, Air 40 1/3, Water 30 1/4, Glass 26. Of the fifth order, greenish blue, air 46, water 34 1/2, glass 29 2/3. Red, air 52 1/2, water 39 3/8, glass 34. Of the sixth order, greenish blue, air 58 3/4, water 44, glass 38. Red, air 65, water 48 3/4, glass 42. Of the seventh order, greenish blue, air 71, water 53 1/4, glass 45 4/5. Ruddy white, air 77, water 57 3/4, glass 49 2/3. End of section 22. Recording by Pamela Krantz. Section 23 of Optics. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Pamela Krantz. Optics by Isaac Newton. Book 2, Part 2, Section 2. There are also other uses of this table, for by its assistance the thickness of the bubble in the 19th observation was determined by the Colours which it exhibited, and so the bigness of the parts of natural bodies may be conjectured by their Colours, as shall be hereafter shown. Also, if two or more very thin plates be laid one upon another, so as to compose one plate equalling them all in thickness, the resulting Colour may be hereby determined. For instance, Mr. Hooke observed, as is mentioned in his Micrographia, that a faint yellow plate of Muscovy glass laid upon a blue one constituted a very deep purple. The yellow of the first order is a faint one, and the thickness of the plate exhibiting it, according to the table, is 4 3/5, to which add 9, the thickness exhibiting blue of the second order, and the sum will be 13 3/5, which is the thickness exhibiting the purple of the third order. To explain, in the next place, the circumstances of the second and third observations, that is, how the rings of the Colours may, by turning the Prisms about their common axis the contrary way to that expressed in those observations, be converted into white and black rings, and afterwards into rings of Colours again, the Colours of each ring lying now in an inverted order, it must be remembered that those rings of Colours are dilated by the obliquation of the rays to the air which intercedes the glasses, and that according to the table in the seventh observation, their dilatation or increase of their diameter is most manifest and speedy when they are obliquest. Now the Rays of yellow being more refracted by the first Superficies of the said Air than those of red, are thereby made more oblique to the second Superficies, at which they are reflected to produce the coloured Rings, and consequently the yellow Circle in each Ring will be more dilated than the red, and the excess of its dilatation will be so much the greater, by how much the greater is the obliquity of the Rays, until at last it become of equal extent with the red of the same Ring. And for the same reason the green, blue, and violet will be also so much dilated by the still greater obliquity of their Rays, as to become all very nearly of equal extent with the red, that is, equally distant from the center of the Rings. And then all the Colours of the same Ring must be coincident, and by their mixture exhibit a white Ring. And these white Rings must have black and dark Rings between them, because they do not spread and interfere with one another as before. And for that reason also they must become distincter, and visible to far greater numbers. But yet the violet being obliquest will be something more dilated, in proportion to its extent, than the other Colours, and so very apt to appear at the exterior verges of the white. Afterwards, by a greater obliquity of the Rays, the violet and blue become more sensibly dilated than the red and yellow, and so being farther removed from the center of the Rings, the Colours must emerge out of the white in an order contrary to that which they had before, the violet and blue at the exterior limbs of each Ring, and the red and yellow at the interior. and the violet, by reason of the greatest obliquity of its Rays, being in proportion most of all expanded, will soonest appear at the exterior limb of each white Ring, and become more conspicuous than the rest. And the several Series of Colours belonging to the several Rings will, by their unfolding and spreading, begin again to interfere, and thereby render the Rings less distinct, and not visible to so great numbers. If, instead of the Prisms, the Object glasses be made use of, the Rings which they exhibit become not white and distinct by the obliquity of the eye, by reason that the Rays in their passage through that Air which intercedes the Glasses are very nearly parallel to those Lines in which they were first incident on the Glasses, and consequently the Rays endued with several Colours are not inclined one more than another to that Air, as it happens in the Prisms. There is yet another circumstance of these Experiments to be considered, and that is why the black and white Rings, which when viewed at a distance appear distinct, should not only become confused by viewing them near at hand, but also yield a violet Colour at both the edges of every white Ring. And the reason is, that the Rays which enter the Eye at several parts of the Pupil have several obliquities to the Glasses, and those which are most oblique, if considered apart, would represent the Rings bigger than those which are the least oblique. Whence the breadth of the Perimeter of every white Ring is expanded outwards by the obliquest Rays, and inwards by the least oblique. And this expansion is so much the greater by how much the greater is the difference of the obliquity, that is, by how much the Pupil is wider, or the Eye nearer to the Glasses. And the breadth of the violet must be most expanded, because the Rays, apt to excite a sensation of that Colour, are most oblique to a second or farther superficies of the thinned Air at which they are reflected, and have also the greatest variation of obliquity, which makes that Colour soonest emerge out of the edges of the white. And as the breadth of every Ring is thus augmented, the dark Intervals must be diminished, until the neighbouring Rings become continuous, and are blended, the exterior first and then those nearer the Center, so that they can no longer be distinguished apart, but seem to constitute an even and uniform whiteness. Among all the Observations there is none accompanied with so odd circumstances as the 24th. Of those the principal are, that in thin Plates, which to the naked eye seem of an even and uniform transparent whiteness, without any terminations of Shadows, the Refraction of a Prism should make Rings of Colours appear, whereas it usually makes Objects appear coloured only there where they are terminated with Shadows, or have parts unequally luminous, and that it should make those Rings exceedingly distinct and white, although it usually renders Objects confused and coloured. The cause of these things you will understand by considering that all the Rings of Colours are really in the Plate, when viewed with the naked eye, although by reason of the great breadth of their circumferences they so much interfere and are blended together, that they seem to constitute an uniform whiteness. But when the Rays pass through the Prism to the eye, the Orbits of the several Colours in every Ring are refracted, some more than others according to their degrees of refrangibility. By which means the Colours on one side of the Ring, that is, in the circumference on one side of its Center, become more unfolded and dilated, and those on the other side more complicated and contracted. And where by a due Refraction they are so much contracted, that the several Rings become narrower than to interfere with one another, they must appear distinct, and also white, if the constituent Colours be so much contracted as to be wholly coincident. But on the other side, where the Orbit of every Ring is made broader by the farther unfolding of its Colours, it must interfere more with other Rings than before, and so become less distinct. To explain this a little farther, suppose the concentric circles AV and BX in Fig. 7 represent the red and violet of any order, which, together with the intermediate Colours, constitute any one of these Rings. Now these being viewed through a Prism, the violet circle BX will by a greater Refraction be farther translated from its place than the red AV, and so approach nearer to it on that side of the circles, towards which the Refractions are made. For instance, if the red be translated to italics AV, the violet may be translated to italics BX, so as to approach nearer to it at italic X than before. And if the red be farther translated to AV, the violet may be so much farther translated to bx, as to convene with it at x. And if the red be yet farther translated to alpha chi, the violet may be still so much farther translated to beta xi, as to pass beyond it at xi, and convene with it at italic E and italic F. And this being understood not only of the red and violet, but of all the other intermediate Colours, and also of every revolution of those Colours, you will easily perceive how those of the same revolution or order, by their nearness at italics xv and chi xi, and their coincidence at xv, italic E and italic F, ought to constitute pretty distinct arcs of circles, especially at xv, or at italic E and italic F, and that they will appear severally at italics xv, and at xv exhibit whiteness by their coincidence, and again appear severally at chi xi, but yet in a contrary order to that which they had before, and still retain beyond italic E and italic F. But on the other side, at italics AB, ab, or alpha beta, these Colours must become much more confused by being dilated and spread so as to interfere with those of other orders. And the same confusion will happen at chi xi, between italic E and italic F, if the refraction be very great, or the prism very distant from the object glasses; in which case no parts of the rings will be seen, save only two little arcs at italic E and italic F, whose distance from one another will be augmented by removing the prism still farther from the object glasses. And these little arcs must be distinctest and whitest at their middle, and at their ends, where they begin to grow confused, they must be coloured. And the Colours at one end of every arc must be in a contrary order to those at the other end, by reason that they cross in the intermediate white, namely, their ends which verge towards chi xi will be red and yellow on that side next the center, and blue and violet on the other side. But their other ends which verge from chi xi will on the contrary be blue and violet on that side towards the center, and on the other side red and yellow. Now as all these things follow from the properties of light by a mathematical way of reasoning, so the truth of them may be manifested by experiments. For in a dark room, by viewing these rings through a prism, by reflection of the several prismatic Colours, which an assistant causes to move to and fro upon a wall or paper from whence they are reflected, whilst the spectator's eye, the prism, and the object glasses, as in the 13th observation, are placed steady, the position of the circles made successively by the several Colours will be found such, in respect of one another, as I have described in the figures italics ABXV, or abxv, or alpha beta xi chi. And by the same method the truth of the explications of other observations may be examined. By what hath been said, the like Phenomena of Water and thin Plates of Glass may be understood, but in small fragments of those Plates there is this farther observable, that where they lie flat upon a table, and are turned about their centers whilst they are viewed through a Prism, they will in some postures exhibit Waves of various Colours, and some of them exhibit these Waves in one or two positions only, but the most of them do in all positions exhibit them, and make them for the most part appear almost all over the Plates. The reason is, that the Superficies of such Plates are not even, but have many cavities and swellings, which, how shallow soever, do a little vary the thickness of the Plate. For at the several sides of those cavities, for the reasons newly described, there ought to be produced Waves in several postures of the Prism. Now though it be but some very small and narrower parts of the Glass, by which these Waves for the most part are caused, yet they may seem to extend themselves over the whole Glass, because from the narrowest of those parts there are Colours of several orders, that is, of several rings, confusedly reflected, which by refraction of the Prism are unfolded, separated, and according to their degrees of refraction dispersed to several places, so as to constitute so many several Waves, as there were divers orders of Colours promiscuously reflected from that part of the Glass. These are the principal Phenomena of thin Plates or Bubbles, whose Explications depend on the Properties of Light which I have heretofore delivered. And these, you see, do necessarily follow from them and agree with them, even to their very least circumstances, and not only so, but do very much tend to their proof. Thus by the 24th Observation it appears that the Rays of several Colours, made as well by thin Plates or Bubbles as by Refractions of a Prism, have several degrees of Refrangibility, whereby those of each order, which at the reflection from the Plate or Bubble are intermixed with those of other orders, are separated from them by refraction, and associated together so as to become visible by themselves like arcs of circles. For if the Rays were all alike refrangible, 'tis impossible that the whiteness, which to the naked sense appears uniform, should by refraction have its parts transposed and ranged into those black and white arcs. It appears also that the unequal Refractions of difform Rays proceed not from any contingent Irregularities, such as are veins and uneven polish, or fortuitous position of the Pores of Glass, unequal and casual motions in the Air or Æther, the spreading, breaking, or dividing the same Ray into many diverging parts, or the like. For, admitting any such Irregularities, it would be impossible for Refractions to render those Rings so very distinct and well defined as they do in the 24th Observation. It is necessary therefore that every Ray have its proper and constant degree of Refrangibility connate with it, according to which its Refraction is ever justly and regularly performed, and that several Rays have several of those degrees. And what is said of their Refrangibility may be also understood of their Reflexibility, that is, of their dispositions to be reflected, some at a greater and others at a less thickness of thin Plates or Bubbles; namely, that those dispositions are also connate with the Rays and immutable, as may appear by the 13th, 14th, and 15th Observations, compared with the 4th and 18th. By the precedent Observations it appears also, that whiteness is a dissimilar mixture of all Colours, and that light is a mixture of Rays endued with all those Colours. For considering the multitude of the Rings of Colours in the 3rd, 12th, and 24th Observations, it is manifest that although in the 4th and 18th Observations there appear no more than 8 or 9 of those Rings, yet there are really a far greater number which so much interfere and mingle with one another, as after those 8 or 9 revolutions to dilute one another wholly, and constitute an even and sensibly uniform whiteness. And consequently that whiteness must be allowed a mixture of all Colours, and the light which conveys it to the eye must be a mixture of Rays endued with all those Colours. But farther, by the 24th Observation it appears that there is a constant relation between Colours and Refrangibility, the most refrangible Rays being violet, the least refrangible red, and those of intermediate Colours having proportionably intermediate degrees of Refrangibility. And by the 13th, 14th, and 15th Observations, compared with the 4th or 18th, there appears to be the same constant relation between Colour and Reflexibility, the violet being in like circumstances reflected at least thicknesses of any thin Plate or Bubble, the red at greatest thicknesses, and the intermediate Colours at intermediate thicknesses. Whence it follows that the colorific dispositions of Rays are also connate with them and immutable, and by consequence that all the productions and appearances of Colours in the world are derived, not from any physical change caused in light by refraction or reflection, but only from the various mixtures or separations of Rays, by virtue of their different refrangibility or reflexibility. And in this respect the science of Colours becomes a speculation as truly mathematical as any other part of Opticks. I mean, so far as they depend on the nature of light, and are not produced or altered by the power of imagination, or by striking or pressing the eye. End of Section 23. Recording by Pamela Krantz.
Section 24 of Optics. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Mark Michelson. Optics by Isaac Newton. Book 2, Part 3. Propositions 1 through 6. The second book of Optics. Part 3. Of the permanent Colours of natural bodies, and the analogy between them and the Colours of thin transparent plates. I am now come to another part of this design, which is to consider how the phenomena of thin transparent plates stand related to those of all other natural bodies. Of these bodies I have already told you that they appear of diverse Colours, accordingly as they are disposed to reflect most copiously the rays originally endued with those Colours, but their constitutions, whereby they reflect some rays more copiously than others, remain to be discovered, and these I shall endeavour to manifest in the following propositions. Proposition 1. Those superficies of transparent bodies reflect the greatest quantity of light, which have the greatest refracting power, that is, which intercede mediums that differ most in their refractive densities, and in the confines of equally refracting mediums there is no reflection. The analogy between reflection and refraction will appear by considering that when light passeth obliquely out of one medium into another which refracts from the perpendicular, the greater is the difference of their refractive density, the less obliquity of incidence is requisite to cause a total reflection. For as the sines are which measure the refraction, so is the sine of incidence at which the total reflection begins to the radius of the circle, and consequently that angle of incidence is least where there is the greatest difference of the sines. Thus in the passing of light out of water into air, where the refraction is measured by the ratio of the sines 3 to 4, the total reflection begins when the angle of incidence is about 48 degrees 35 minutes. In passing out of glass into air, where the refraction is measured by the ratio of the sines 20 to 31, the total reflection begins when the angle of incidence is 40 degrees 10 minutes. And so in passing out of crystal, or more strongly refracting mediums into air, there is still a less obliquity requisite to cause a total reflection. Superficies therefore which refract most do soonest reflect all the light which is incident on them, and so must be allowed most strongly reflexive. But the truth of this proposition will farther appear by observing, that in the superficies interceding two transparent mediums, such as are air, water, oil, common glass, crystal, metalline glasses, island glasses, white transparent arsenic, diamonds, etc., the reflection is stronger or weaker accordingly, as the superficies hath a greater or less refracting power. For in the confine of air and sal gem, 'tis stronger than in the confine of air and water, and still stronger in the confine of air and common glass or crystal, and stronger in the confine of air and a diamond. If any of these, and such like transparent solids, be immerged in water, its reflection becomes much weaker than before, and still weaker if they be immerged in the more strongly refracting liquors of well rectified oil of vitriol or spirit of turpentine. If water be distinguished into two parts by any imaginary surface, the reflection in the confine of those two parts is none at all. In the confine of water and ice 'tis very little, in that of water and oil 'tis something greater, in that of water and sal gem still greater, and in that of water and glass, or crystal, or other denser substances still greater, accordingly as those mediums differ more or less in their refracting powers. Hence, in the confine of common glass and crystal, there ought to be a weak reflection, and a stronger reflection in the confine of common and metalline glass, though I have not yet tried this. But in the confine of two glasses of equal density, there is not any sensible reflection, as was shown in the first observation. And the same may be understood of the superficies interceding two crystals, or two liquors, or any other substances in which no refraction is caused. So then, the reason why uniform pellucid mediums, such as water, glass, or crystal, have no sensible reflection but in their external superficies, where they are adjacent to other mediums of a different density, is because all their contiguous parts have one and the same degree of density. Proposition 2. The least parts of almost all natural bodies are in some measure transparent, and the opacity of those bodies ariseth from the multitude of reflections caused in their internal parts. That this is so has been observed by others, and will easily be granted by them that have been conversant with microscopes. And it may be also tried by applying any substance to a hole through which some light is emitted into a dark room. For how opaque soever that substance may seem in the open air, it will by that means appear very manifestly transparent, if it be of a sufficient thinness. Only white metalline bodies must be excepted, which by reason of their excessive density seem to reflect almost all the light incident on their first superficies, unless by solution in menstruums they be reduced into very small particles, and then they become transparent. Proposition 3. Between the parts of opaque and colored bodies are many spaces, either empty or replenished with mediums of other densities, as water between the tinging corpuscles wherewith any liquor is impregnated, air between the aqueous globules that constitute clouds or mists, and for the most part spaces void of both air and water, but yet perhaps not wholly void of all substance, between the parts of hard bodies. The truth of this is evinced by the two precedent propositions. For by the second proposition there are many reflections made by the internal parts of bodies, which by the first proposition would not happen if the parts of those bodies were continued without any such interstices between them, because reflections are caused only in superficies, which intercede mediums of a differing density, by proposition 1. But farther, that this discontinuity of parts is the principal cause of the opacity of bodies, will appear by considering that opaque substances become transparent by filling their pores with any substance of equal or almost equal density with their parts. Thus, paper dipped in water or oil, the oculus mundi stone steeped in water, linen cloth oiled or varnished, and many other substances soaked in such liquors as will intimately pervade their little pores, become by that means more transparent than otherwise. So, on the contrary, the most transparent substances may, by evacuating their pores, or separating their parts, be rendered sufficiently opaque, as salts or wet paper, or the oculus mundi stone by being dried, horn by being scraped, glass by being reduced to powder, or otherwise flawed, turpentine by being stirred about with water till they mix imperfectly, and water by being formed into many small bubbles, either alone in the form of froth, or by shaking it together with oil of turpentine, or oil olive, or with some other convenient liquor, with which it will not perfectly incorporate. And to the increase of the opacity of these bodies, it conduces something, that by the 23rd observation the reflections of very thin transparent substances are considerably stronger than those made by the same substances of a greater thickness. Proposition 4. The parts of bodies and their interstices must not be less than of some definite bigness to render them opaque and colored. For the opacest bodies, if their parts be subtly divided, as metals, by being dissolved in acid menstruums, etc., become perfectly transparent. And you may also remember that in the 8th observation there was no sensible reflection at the superficies of the object glasses, where they were very near one another, though they did not absolutely touch. And in the 17th observation the reflection of the water bubble, where it became thinnest, was almost insensible, so as to cause very black spots to appear on the top of the bubble, by the want of reflected light. On these grounds I perceive it is that water, salt, glass, stones, and such like substances are transparent, for upon diverse considerations, they seem to be as full of pores or interstices between their parts as other bodies are, but yet their parts and interstices to be too small to cause reflections in their common surfaces. Proposition 5. The transparent parts of bodies, according to their several sizes, reflect rays of one color, and transmit those of another, on the same grounds that thin plates or bubbles do reflect or transmit those rays, and this I take to be the ground of all their colors. For if a thinned or plated body, which being of an even thickness, appears all over of one uniform color, should be slit into threads or broken into fragments of the same thickness with the plate, I see no reason why every thread or fragment should not keep its color, and by consequence why a heap of those threads or fragments should not constitute a mass or powder of the same color, which the plate exhibited before it was broken. And the parts of all natural bodies being like so many fragments of a plate, must on the same grounds exhibit the same colors. Now that they do so will appear by the affinity of their properties. The finely colored feathers of some birds, and particularly those of peacocks' tails, do, in the very same part of the feather, appear of several colors in several positions of the eye, after the very same manner that thin plates were found to do in the 7th and 19th observations, and therefore their colors arise from the thinness of the transparent parts of the feathers, that is, from the slenderness of the very fine hairs, or capillamenta, which grow out of the sides of the grosser lateral branches or fibers of those feathers. And to the same purpose it is, that the webs of some spiders, by being spun very fine, have appeared colored, as some have observed, and that the colored fibers of some silks, by varying the position of the eye, do vary their color. Also the colors of silks, cloths, and other substances, which water or oil can intimately penetrate, become more faint and obscure by being immerged in those liquors, and recover their vigor again by being dried, much after the manner declared of thin bodies in the 10th and 21st observations. Leaf gold, some sorts of painted glass, the infusion of lignum nephriticum, and some other substances, reflect one color, and transmit another, like thin bodies in the 9th and 20th observations. And some of those colored powders which painters use, may have their colors a little changed, by being very elaborately and finely ground, where I see not what can be justly pretended for those changes, besides the breaking of their parts into less parts by that contrition, after the same manner that the color of a thin plate is changed by varying its thickness. For which reason also it is, that the colored flowers of plants and vegetables, by being bruised, usually become more transparent than before, or at least in some degree or other change their colors. Nor is it much less to my purpose that by mixing diverse liquors, very odd and remarkable productions and changes of colors may be effected, of which no cause can be more obvious and rational than that the saline corpuscles of one liquor do variously act upon or unite with the tinging corpuscles of another, so as to make them swell or shrink, whereby not only their bulk but their density also may be changed, or to divide them into smaller corpuscles, whereby a colored liquor may become transparent, or to make many of them associate into one cluster, whereby two transparent liquors may compose a colored one. For we see how apt those saline menstruums are to penetrate and dissolve substances to which they are applied, and some of them to precipitate what others dissolve. In like manner, if we consider the various phenomena of the atmosphere, we may observe, that when vapors are first raised, they hinder not the transparency of the air, being divided into parts too small to cause any reflection in their superficies. But when in order to compose drops of rain, they begin to coalesce and constitute globules of all intermediate sizes, those globules, when they become of convenient size to reflect some Colours and transmit others, may constitute Clouds of various Colours, according to their sizes. And I see not what can be rationally conceived in so transparent a substance as water for the production of these Colours, besides the various sizes of its fluid and globular parcels. Proposition 6. The parts of bodies on which their Colours depend are denser than the medium which pervades their interstices. This will appear by considering, that the colour of a body depends not only on the rays which are incident perpendicularly on its parts, but on those also which are incident at all other angles, and that, according to the 7th observation, a very little variation of obliquity will change the reflected colour, where the thin body, or small particles, is rarer than the ambient medium, insomuch that such a small particle will at diversely oblique incidences reflect all sorts of Colours, in so great a variety that the Colour resulting from them all, confusedly reflected from a heap of such particles, must rather be a white or grey than any other colour, or at best it must be but a very imperfect and dirty colour. Whereas if the thin body or small particle be much denser than the ambient medium, the colours, according to the 19th observation, are so little changed by the variation of obliquity, that the rays which are reflected least obliquely may predominate over the rest, so much as to cause a heap of such particles to appear very intensely of their colour. It conduces also something to the confirmation of this proposition, that according to the 22nd observation, the colours exhibited by the denser thin body within the rarer are more brisk than those exhibited by the rarer within the denser. End of section 24.
Section 25 of Optics. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Smith A.J. Optics by Isaac Newton, Book 2, Part 3, Proposition 7. Proposition 7. The bigness of the component parts of natural bodies may be conjectured by their colours. For since the parts of these bodies by Proposition 5 do most probably exhibit the same Colours with a plate of equal thickness, provided they have the same refractive density, and since their parts seem for the most part to have much the same density with water or glass, as by many circumstances is obvious to collect, to determine the sizes of those parts, you need only have recourse to the precedent tables, in which the thickness of water or glass exhibiting any colour is expressed. Thus, if it be desired to know the diameter of a corpuscle, which being of equal density with glass shall reflect green of the third order, the number 16 1/4 shews it to be 16 1/4 10,000th parts of an inch. The greatest difficulty is here to know of what order the colour of any body is, and for this end we must have recourse to the 4th and 18th observations, from whence may be collected these particulars. Scarlets and other reds, oranges and yellows, if they be pure and intense, are most probably of the second order. Those of the first and third order also may be pretty good, only the yellow of the first order is faint, and the orange and red of the third order have a great mixture of violet and blue. There may be good greens of the fourth order, but the purest are of the third, and of this order the green of all vegetables seems to be, partly by reason of the intenseness of their colours, and partly because when they wither some of them turn to a greenish yellow, and others to a more perfect yellow or orange, or perhaps to red, passing first through all the aforesaid intermediate colours, which changes seem to be effected by the exhaling of the moisture, which may leave the tinging corpuscles more dense, and something augmented by the accretion of the oily and earthy part of that moisture. Now the green, without doubt, is of the same order with those colours into which it changeth, because the changes are gradual, and those colours, though usually not very full, yet are often too full and lively to be of the fourth order. Blues and purples may be either of the second or third order, but the best are of the third. Thus the colour of violets seems to be of that order, because their syrup by acid liquors turns red, and by Uranus an alkalizite turns green. For since it is of the nature of acids to dissolve or attenuate, and of alkalis to precipitate or increasate, if the purple colour of the syrup was of the second order, an acid liquor by attenuating its tinging corpuscles would change it to a red of the first order, and an alkali by increasating them would change it to a green of the second order, which red and green, especially the green, seem too imperfect to be the colours produced by these changes. But if the said purple be supposed of the third order, its change to red of the second and green of the third may without any inconvenience be allowed. If there be found any body of a deeper and less reddish purple than that of the violets, its colour most probably is of the second order. But yet there being no body commonly known whose colour is constantly more deep than theirs, I have made use of their name to denote the deepest and least reddish purples, such as manifestly transcend their colour in purity. The blue of the first order, though very faint and little, may possibly be the colour of some substances, and particularly the azure colour of the skies seems to be of this order. For all vapours, when they begin to condense and coalesce into small parcels, become first of that bigness, whereby such an azure must be reflected before they can constitute clouds of other colours. And so this being the first colour which vapours begin to reflect, it ought to be the colour of the finest and most transparent skies, in which vapours are not arrived to that grossness requisite to reflect other colours, as we find it is by experience. Whiteness, if most intense and luminous, is that of the first order; if less strong and luminous, a mixture of the colours of several orders. Of this last kind is the whiteness of froth, paper, linen, and most white substances. Of the former I reckon that of white metals to be, for whilst the densest of metals, gold, if foliated, is transparent, and all metals become transparent if dissolved in menstruums or vitrified, the opacity of white metals ariseth not from their density alone. They being less dense than gold would be more transparent than it, did not some other cause concur with their density to make them opaque. And this cause I take to be such a bigness of their particles as fits them to reflect the white of the first order. For if they be of other thicknesses, they may reflect other colours, as is manifest by the colours which appear upon hot steel in tempering it, and sometimes upon the surface of melted metals in the skin, or scoria, which arises upon them in their cooling. And as the white of the first order is the strongest, which can be made by plates of transparent substances, so it ought to be stronger in the denser substances of metals than in the rarer of air, water, and glass. Nor do I see but that metallic substances of such a thickness as may fit them to reflect the white of the first order, may, by reason of their great density, according to the tenor of the first of these propositions, reflect all the light incident upon them, and so be as opaque and splendent as it's possible for any body to be. Gold or copper mixed with less than half their weight of silver or tin or regulus of antimony in fusion, or amalgamated with a very little mercury, become white, which shows both that the particles of white metals have much more superficies, and so are smaller than those of gold and copper, and also that they are so opaque as not to suffer the particles of gold or copper to shine through them. Now it is scarce to be doubted but that the Colours of Gold and Copper are of the second and third order, and therefore the Particles of white Metals cannot be much bigger than is requisite to make them reflect the white of the first order. The volatility of mercury argues that they are not much bigger, nor may they be much less, lest they lose their opacity and become either transparent, as they do when attenuated by vitrification or by solution in menstruums, or black, as they do when ground smaller by rubbing silver or tin or lead upon other substances to draw black lines. The first and only colour which white metals take by grinding their particles smaller is black, and therefore their white ought to be that which borders upon the black spot in the center of the rings of colours, that is the white of the first order. But if you would hence gather the bigness of metallic particles, you must allow for their density, for were mercury transparent, its density is such that the sine of incidence upon it, by my computation, would be to the sine of its refraction as 71 to 20 or 7 to 2, and therefore the thickness of its particles, that they may exhibit the same colours with those of bubbles of water, ought to be less than the thickness of the skin of those bubbles in the proportion of 2 to 7. Whence it's possible that the particles of mercury may be as little as the particles of some transparent and volatile fluids, and yet reflect the white of the first order. Lastly, for the production of black, the corpuscles must be less than any of those which exhibit colours, for at all greater sizes there is too much light reflected to constitute this colour. But if they be supposed a little less than is requisite to reflect the white and very faint blue of the first order, they will, according to the 4th, 8th, 17th and 18th observations, reflect so very little light as to appear intensely black, and yet may perhaps variously refract it to and fro within themselves so long until it happen to be stifled and lost, by which means they will appear black in all positions of the eye without any transparency. And from hence may be understood why fire and the more subtle dissolver, putrefaction, by dividing the particles of substances turn them to black; why small quantities of black substances impart their colour very freely and intensely to other substances to which they are applied, the minute particles of these, by reason of their very great number, easily overspreading the gross particles of others; why glass ground very elaborately with sand on a copper plate, till it be well polished, makes the sand together with what is worn off from the glass and copper become very black; why black substances do soonest of all others become hot in the sun's light and burn, which effect may proceed partly from the multitude of refractions in a little room, and partly from the easy commotion of so very small corpuscles; and why blacks are usually a little inclined to a bluish colour, for that they are so may be seen by illuminating the white paper by light reflected from black substances. For the paper will usually appear of a bluish white, and the reason is that black borders in the obscure blue of the order described in the 18th observation, and therefore reflects more rays of that colour than of any other. In these descriptions I have been the more particular, because it is not impossible but that microscopes may at length be improved to the discovery of the particles of bodies on which their colours depend, if they are not already in some measure arrived to that degree of perfection. For if those instruments are or can be so far improved as with sufficient distinctness to represent objects 500 or 600 times bigger than at a foot distance they appear to our naked eyes, I should hope that we might be able to discover some of the greatest of those corpuscles, and by one that would magnify 3,000 or 4,000 times, perhaps they might all be discovered, but those which produce blackness. In the meanwhile I see nothing material in this discourse that may rationally be doubted of, excepting this position, that transparent corpuscles of the same thickness and density with a plate do exhibit the same colour. And this I would have understood not without some latitude as well, because those corpuscles may be of irregular figures, and many rays must be obliquely incident on them, and so have a shorter way through them than the length of their diameters, as because the straightness of the medium put in on all sides within such corpuscles may a little alter its motions or other qualities on which the reflection depends. But yet I cannot much suspect the last, because I have observed of some small plates of Muscovy glass, which were of an even thickness, that through a microscope they have appeared of the same colour at their edges and corners where the included medium was terminated, which they appeared of in other places. However, it will add much to our satisfaction if those corpuscles can be discovered with microscopes, which if we shall at length attain to, I fear it will be the utmost improvement of this sense. For it seems impossible to see the more secret and noble works of nature within the corpuscles by reason of their transparency. End of section 25. Section number 26 of Optics. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Smith A.J. Optics by Isaac Newton. Book 2, Part 3, Propositions 8 to 9. Proposition 8. The cause of reflection is not the impinging of light on the solid or impervious parts of bodies, as is commonly believed. This will appear by the following considerations. First, that in the passage of light out of glass into air, there is a reflection as strong as in its passage out of air into glass, or rather a little stronger, and by many degrees stronger than in its passage out of glass into water. And it seems not probable that air should have more strongly reflecting parts than water or glass. But if that should possibly be supposed, yet it will avail nothing. For the reflection is as strong or stronger when the air is drawn away from the glass, supposed by the air pump invented by Otto Guerier, and improved and made useful by Mr. Boyle, as when it is adjacent to it. Secondly, if light in its passage out of glass into air be incident more obliquely than at an angle of 40 or 41 degrees, it is wholly reflected. If less obliquely, it is in great measure transmitted. Now it is not to be imagined that light at 1 degree of obliquity should meet with pores enough in the air to transmit the greater part of it, and at another degree of obliquity should meet with nothing but parts to reflect it wholly, especially considering that in its passage out of air into glass, how oblique soever be its incidence, it finds pores enough in the glass to transmit a great part of it. If any man suppose that it is not reflected by the air, but by the outmost superficial parts of the glass, there is still the same difficulty. Besides that such a supposition is unintelligible, and will also appear to be false by applying water behind some part of the glass instead of air. For so in a convenient obliquity of the rays, suppose of 45 or 46 degrees, at which they are all reflected where the air is adjacent to the glass, they shall be in great measure transmitted where the water is adjacent to it, which argues that their reflection or transmission depends on the constitution of the air and water behind the glass, and not on the striking of the rays upon the parts of the glass. Thirdly, if the colours made by a prism placed at the entrance of a beam of light into a darkened room be successively cast on a second prism placed at a greater distance from the former, in such manner that they are all alike incident upon it, the second prism may be so inclined to the incident rays that those which are of a blue colour shall be all reflected by it, and yet those of a red colour pretty copiously transmitted. Now if the reflection be caused by the parts of air or glass, I would ask, why at the same obliquity of incidence the blue should wholly impinge on those parts so as to be all reflected, and yet the red find pores enough to be in a great measure transmitted. Fourthly, Where two glasses touch one another, there is no sensible reflection, as was declared in the first observation, and yet I see no reason why the rays should not impinge on the parts of the glass as much when contiguous to other glass as when contiguous to air. Fifthly, when the top of a water bubble in the 17th observation, by the continual subsiding and exhaling of the water, grew very thin, there was such a little and almost insensible quantity of light reflected from it, that it appeared intensely black, whereas round about that black spot, where the water was thicker, the reflection was so strong as to make the water seem very white. Nor is it only at the least thickness of thin plates or bubbles that there is no manifest reflection, but at many other thicknesses continually greater and greater. For in the 15th observation the rays of the same colour will by turns transmitted at one thickness, and reflected at another thickness for an indeterminate number of successions, and yet in the superficies of the thinned body, where it is of any one thickness, there are as many parts for the rays to impinge on as where it is of any other thickness. Sixthly, if reflection were caused by the parts of reflecting bodies, it would be impossible for thin plates or bubbles at one and the same place to reflect the rays of one colour and transmit those of another, as they do according to the 13th and 15th observations. For it is not to be imagined that at one place the rays, which for instance exhibit a blue colour, should have the fortune to dash upon the parts, and those which exhibit a red to hit upon the pores of the body, and then at another place where the body is either a little thicker or a little thinner, that on the contrary the blue should hit upon its pores and the red upon its parts. Lastly, were the rays of light reflected by impinging on the solid parts of bodies, their reflections from polished bodies could not be so regular as they are. For in polishing glass with sand, putty or tripoli, it is not to be imagined that those substances can, by grating and fretting the glass, bring all its least particles to an accurate polish, so that all their surfaces shall be truly plane or truly spherical, and look all the same way, so as together to compose one even surface. The smaller the particles of those substances are, the smaller will be the scratches by which they continually fret and wear away the glass until it be polished. But be they never so small, they can wear away the glass no otherwise than by grating and scratching it, and breaking the protuberances, and therefore polish it no otherwise than by bringing its roughness to a very fine grain, so that the scratches and frettings of the surface become too small to be visible. And therefore, if light were reflected by impinging upon the solid parts of the glass, it would be scattered as much by the most polished glass as by the roughest. So then it remains a problem, how glass polished by fretting substances can reflect light so regularly as it does. And this problem is scarce otherwise to be solved than by saying that the reflection of a ray is effected not by a single point of the reflecting body, but by some power of the body which is evenly diffused all over its surface, and by which it acts upon the ray without immediate contact. For that the parts of bodies do act upon light at a distance shall be shewn hereafter. Now, if light be reflected not by impinging on the solid parts of bodies, but by some other principle, it's probable that as many of its rays as impinge on the solid parts of bodies are not reflected but stifled and lost in the bodies. For otherwise we must allow two sorts of reflections. Should all the rays be reflected which impinge on the internal parts of clear water or crystal, those substances would rather have a cloudy colour than a clear transparency. To make bodies look black, it's necessary that many rays be stopped, retained and lost in them, and it seems not probable that any rays can be stopped and stifled in them which do not impinge on their parts. And hence we may understand that bodies are much more rare and porous than is commonly believed. Water is 19 times lighter, and by consequence 19 times rarer than gold, and gold is so rare as very readily and without the least opposition to transmit the magnetic effluvia and easily to admit quicksilver into its pores, and to let water pass through it. For a concave sphere of gold filled with water and soldered up has, upon pressing the sphere with great force, let the water squeeze through it, and stand all over its outside in multitudes of small drops, like dew, without bursting or cracking the body of the gold, as I have been informed by an eye witness. From all which we may conclude that gold has more pores than solid parts, and by consequence that water has above 40 times more pores than parts. And he that shall find out an hypothesis by which water may be so rare, and yet not be capable of compression by force, may doubtless by the same hypothesis make gold and water and all other bodies as much rarer as he pleases, so that light may find a ready passage through transparent substances. The magnet acts upon iron through all dense bodies, not magnetic nor red hot, without any diminution of its virtue, as for instance through gold, silver, lead, glass, water. The gravitating power of the sun is transmitted through the vast bodies of the planets without any diminution, so as to act upon all their parts to their very centers with the same force and according to the same laws, as if the part upon which it acts were not surrounded with the body of the planet. The rays of light, whether they be very small bodies projected, or only motion or force propagated, are moved in right lines, and whenever a ray of light is by any obstacle turned out of its rectilinear way, it will never return into the same rectilinear way, unless perhaps by a very great accident. And yet light is transmitted through pellucid solid bodies in right lines to very great distances. How bodies can have a sufficient quantity of pores for producing these effects is very difficult to conceive, but perhaps not altogether impossible. For the colours of bodies arise from the magnitudes of the particles which reflect them, as was explained above. Now if we conceive these particles of bodies to be so disposed amongst themselves that the intervals or empty spaces between them may be equal in magnitude to them all, and that these particles may be composed of other particles much smaller, which have as much empty space between them as equals all the magnitudes of these smaller particles, and that in like manner these smaller particles are again composed of others much smaller, all which together are equal to all the pores or empty spaces between them, and so on perpetually till you come to solid particles, such as have no pores or empty spaces within them. And if in any gross body there be, for instance, 3 such degrees of particles, the least of which are solid, this body will have 7 times more pores than solid parts. But if there be 4 such degrees of particles, the least of which are solid, the body will have 15 times more pores than solid parts. If there be 5 degrees, the body will have 130 times more pores than solid parts. If 6 degrees, the body will have 63 times more pores than solid parts, and so on perpetually. And there are other ways of conceiving how bodies may be exceeding porous, but what is really their inward frame is not yet known to us. Proposition 9. Bodies reflect and refract light by one and the same power, variously exercised in various circumstances. This appears by several considerations. First, because when light goes out of glass into air as obliquely as it can possibly do, if its incidence be made still more oblique, it becomes totally reflected. For the power of the glass, after it has refracted the light as obliquely as is possible, if the incidence be still made more oblique, becomes too strong to let any of its rays go through, and by consequence causes total reflections. Secondly, because light is alternately reflected and transmitted by thin plates of glass for many successions, accordingly as the thickness of the plate increases in an arithmetical progression. For here the thickness of the glass determines whether that power by which glass acts upon light shall cause it to be reflected, or suffer it to be transmitted, and thirdly, because those surfaces of transparent bodies which have the greatest refracting power reflect the greatest quantity of light, as was shown in the first proposition. End of section 26. Section 27 of Optics. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Smith A.J. Optics by Isaac Newton. Book number 2, part 3, propositions 10 to 11. Proposition 10. If light be swifter in bodies than in vacuo, in the proportion of the signs which measure the refraction of the bodies, the forces of the bodies to reflect and refract light are very nearly proportional to the densities of the same bodies, excepting that unctuous and sulphureous bodies refract more than others of this same density. Let AB represent the refracting plane surface of any body, and IC a ray incident very obliquely upon the body in C, so that the angle ACI may be infinitely little, and let CR be the refracted ray. From a given point B perpendicular to the refracting surface erect BR, meeting with the refracting ray CR in R, and if CR represent the motion of the refracted ray, and this motion be distinguished into two motions CB and BR, whereof CB is parallel to the refracting plane and BR perpendicular to it, CB shall represent the motion of the incident ray, and BR the motion generated by the refraction, as opticians have of late explained. Now, if any body or thing in moving through any space of a given breadth, terminated on both sides by two parallel planes, be urged forward in all parts of that space by forces tending directly forwards towards the last plane, and before its incidence on the first plane had no motion towards it, or but an infinitely little one, and if the forces in all parts of that space between the planes be at equal distances from the planes equal to one another, but at several distances be bigger or less in any given proportion, the motion generated by the forces in the whole passage of the body or thing through that space shall be in a subduplicate proportion of the forces, as mathematicians will easily understand. And therefore, if the space of activity of the refracting superficies of the body be considered as such a space, the motion of the ray generated by the refracting force of the body during its passage through that space, that is, the motion BR, must be in subduplicate proportion of that refracting force. I say therefore that the square of the line BR, and by consequence the refracting force of the body, is very nearly as the density of the same body. For this will appear by the following table, wherein the proportion of the signs which measure the refractions of several bodies, the square of BR, supposing CB an unity, the densities of the bodies estimated by their specific gravities, and the refractive power in respect of their densities are set down in several columns. The refracting bodies are pseudo-topazeous, being a natural pellucid brittle hairy stone of a yellow colour. The proportion of the sines of incidence and refraction of yellow light 23 to 14. The square of BR to which the refracting force of the body is proportionate 1.699. The density and specific gravity of the body 4.27. The refractive power of the body in respect of its density 3979. The refracting bodies: air. The proportion of the sines of incidence and refraction of yellow light 3201 to 3200. The square of BR to which the refracting force of the body is proportionate 0.000625. The density and specific gravity of the body 0.0012. The refractive power of the body in respect of its density 5208. The refracting bodies: glass of antimony. The proportion of the sines of incidence and refraction of yellow light 17 to 9. The square of BR to which the refracting force of the body is proportionate 2.568. The density and specific gravity of the body 5.28. The refractive power of the body in respect of its density 4864. The refracting bodies: a selenitis. The proportion of the sines of incidence and refraction of yellow light 61 to 41. The square of BR to which the refracting force of the body is proportionate 1.213. The density and specific gravity of the body 2.252. The refractive power of the body in respect of its density 5386. The refracting bodies: glass vulgar. The proportion of the sines of incidence and refraction of yellow light 31 to 20. The square of BR to which the refracting force of the body is proportionate 1.4025. The density and specific gravity of the body 2.58. The refractive power of the body in respect of its density 5436. The refracting bodies: crystal of the rock. The proportion of the sines of incidence and refraction of yellow light 25 to 16. The square of BR to which the refracting force of the body is proportionate 1.445. The density and specific gravity of the body 2.65. The refractive power of the body in respect of its density 5450. The refracting bodies: island crystal. The proportion of the sines of incidence and refraction of yellow light 5 to 3. The square of BR to which the refracting force of the body is proportionate 1.778. The density and specific gravity of the body 2.72. The refractive power of the body in respect of its density 6 6536. The refracting bodies Saint-Germain. The proportion of the sines of incidence and refraction of yellow light 17 to 11. The square of BR to which the refracting force of the body is proportionate 1.388. The density and specific gravity of the body 2.143. The refractive power of the body in respect of its density 6477. The refracting bodies alum. The proportion of the sines of incidence and refraction of yellow light 35 to 24. The square of BR to which the refracting force of the body is proportionate 1.1267. The density and specific gravity of the body 1.714. The refractive power of the body in respect of its density 6570. The refracting bodies borax. The proportion of the sines of incidence and refraction of yellow light 22 to 15. The square of BR to which the refracting force of the body is proportionate 1.1511. The density and specific gravity of the body 1.714. The refractive power of the body in respect of its density 6716. The refracting bodies nitre. The proportion of the sines of incidence and refraction of yellow light 32 to 21. The square of BR to which the refracting force of the body is proportionate 1.345. The density and specific gravity of the body 1.9. The refractive power of the body in respect of its density 7079. The refracting bodies Dantzig vitriol. The proportion of the sines of incidence and refraction of yellow light 303 to 200. The square of BR to which the refracting force of the body is proportionate 1.295. The density and specific gravity of the body 1.715. The refractive power of the body in respect of its density 7551. The refracting bodies oil of vitriol. The proportion of the sines of incidence and refraction of yellow light 10 to 7. The square of BR to which the refracting force of the body is proportionate 1.041. The density and specific gravity of the body 1.7. The refractive power of the body in respect of its density 6124. The refracting bodies rainwater. The proportion of the sines of incidence and refraction of yellow light 529 to 396. The square of BR to which the refracting force of the body is proportionate 0.7845. The density and specific gravity of the body 1. The refractive power of the body in respect of its density 7845. The refracting bodies: gum arabic. The proportion of the sines of incidence and refraction of yellow light 31 to 21. The square of BR, to which the refracting force of the body is proportionate, 1.179. The density and specific gravity of the body, 1.375. The refractive power of the body in respect of its density, 8574. The refracting bodies: spirit of wine well rectified. The proportion of the sines of incidence and refraction of yellow light, 100 to 73. The square of BR, to which the refracting force of the body is proportionate, 0.8765. The density and specific gravity of the body, 0.866. The refractive power of the body in respect of its density, 10121. The refracting bodies: camphire. The proportion of the sines of incidence and refraction of yellow light, 3 to 2. The square of BR, to which the refracting force of the body is proportionate, 1.25. The density and specific gravity of the body, 0.996. The refractive power of the body in respect of its density, 12551. The refracting bodies: oil, olive. The proportion of the sines of incidence and refraction of yellow light, 22 to 15. The square of BR, to which the refracting force of the body is proportionate, 1.1511. The density and specific gravity of the body, 0.913. The refractive power of the body in respect of its density, 12607. The refracting bodies: linseed oil. The proportion of the sines of incidence and refraction of yellow light, 40 to 27. The square of BR, to which the refracting force of the body is proportionate, 1.1948. The density and specific gravity of the body, 0.932. The refractive power of the body in respect of its density, 12819. The refracting bodies: spirit of turpentine. The proportion of the sines of incidence and refraction of yellow light, 25 to 17. The square of BR, to which the refracting force of the body is proportionate, 1.1626. The density and specific gravity of the body, 0.874. The refractive power of the body in respect of its density, 13222. The refracting bodies: amber. The proportion of the sines of incidence and refraction of yellow light, 14 to 9. The square of BR, to which the refracting force of the body is proportionate, 1.42. The density and specific gravity of the body 1.04. The refractive power of the body in respect of its density 13654. The refracting bodies, a diamond. The proportion of the signs of incidence and refraction of yellow light 100 to 41. The square of BR to which the refracting force of the body is proportionate 4.949. The density and specific gravity of the body 3.4. The refractive power of the body in respect of its density 14556. The refraction of the air in this table is determined by that of the atmosphere observed by astronomers. For if light pass through many refracting substances or mediums gradually denser and denser, and terminated with parallel surfaces, the sum of all the refractions will be equal to the single refraction which it would have suffered in passing immediately out of the first medium into the last. And this holds true though the number of the refracting substances be increased to infinity, and the distances from one another as much decreased, so that the light may be refracted in every point of its passage, and by continual refractions bent into a curve line. And therefore the whole refraction of light in passing through the atmosphere from the highest and rarest part thereof down to the lowest and densest part must be equal to the refraction which it would suffer in passing at like obliquity out of a vacuum immediately into air of equal density with that in the lowest part of the atmosphere. Now, although a pseudo topaz, a selenitis, rock crystal, island crystal, vulgar glass, that is, sand melted together, and glass of antimony, which are terrestrial, stony, alkalizite concretes, and air, which probably arises from such substances by fermentation, be substances very differing from one another in density, yet by this table they have their refractive powers almost in the same proportion to one another as their densities are, excepting that the refraction of that strange substance, island crystal, is a little bigger than the rest, and particularly air, which is 3500 times rarer than the pseudo topaz, and 4400 times rarer than glass of antimony, and 2000 times rarer than the selenitis, glass vulgar, or crystal of the rock, has, notwithstanding its rarity, the same refractive power in respect of its density, which those very dense substances have in respect of theirs, excepting so far as those differ from one another. Again, the refraction of camphire, oil olive, linseed oil, spirit of turpentine, and amber, which are fat, sulphurous, unctuous bodies, and a diamond, which probably is an unctuous substance coagulated, have their refractive powers in proportion to one another as their densities, without any considerable variation. but the refractive powers of these unctuous substances are 2 or 3 times greater in respect of their densities than the refractive powers of the former substances in respect of theirs. Water has a refractive power in a middle degree between those two sorts of substances, and probably is of a middle nature. For out of it grow all vegetable and animal substances, which consist as well of sulphurous fat and inflammable parts, as of earthy, lean, and alkalizite ones. Salts and vitriols have refractive powers in a middle degree between those of earthy substances and water, and accordingly are composed of those two sorts of substances. For by distillation and rectification of their spirits, a great part of them goes into water, and a great part remains behind in the form of a dry fixed earth capable of vitrification. Spirit of wine has a refractive power in a middle degree between those of water and oily substances, and accordingly seems to be composed of both, united by fermentation, the water by means of some saline spirits with which 'tis impregnated, dissolving the oil and volatilizing it by the action. For spirit of wine is inflammable by means of its oily parts, and being distilled often from salt of tartar, grow by every distillation more and more aqueous and phlegmatic. And chemists observe that vegetables, as lavender, rue, marjoram, etc., distilled per se, before fermentation yield oils without any burning spirits, but after fermentation yield ardent spirits without oils, which shews that their oil is by fermentation converted into spirit. They find also that if oils be poured in a small quantity upon fermentating vegetables, they distill over after fermentation in the form of spirits. So then, by the foregoing table, all bodies seem to have their refractive powers proportional to their densities, or very nearly, excepting so far as they partake more or less of sulphurous oily particles, and thereby have their refractive power made greater or less. Whence it seems rational to attribute the refractive power of all bodies chiefly, if not wholly, to the sulphurous parts with which they abound. For it's probable that all bodies abound more or less with sulphurs, and as light congregated by a burning glass acts most upon sulphurous bodies to turn them into fire and flame, so, since all action is mutual, sulphurs ought to act most upon light. For that the action between light and bodies is mutual may appear from this consideration, that the densest bodies, which refract and reflect light most strongly, grow hottest in the summer sun by the action of the refracted or reflected light. I have hitherto explained the power of bodies to reflect and refract, and showed that thin transparent plates, fibers, and particles do, according to their several thicknesses and densities, reflect several sorts of rays, and thereby appear of several colours, and by consequence that nothing more is requisite for producing all the colours of natural bodies than the several sizes and densities of their transparent particles. But whence it is that these plates, fibres, and particles do, according to their several thicknesses and densities, reflect several sorts of rays, I have not yet explained. To give some insight into this matter, and make way for understanding the next part of this book, I shall conclude this part with a few more propositions. Those which preceded respect the nature of bodies, these the nature of light, for both must be understood before the reason of their actions upon one another can be known. And because the last proposition depended upon the velocity of light, I will begin with a proposition of that kind. Proposition 11. Light is propagated from luminous bodies in time and spends about 7 or 8 minutes of an hour in passing from the sun to the earth. This was observed first by Romer and then by others by means of the eclipses of the satellites of Jupiter. For these eclipses, when the earth is between the sun and Jupiter, happen about 7 or 8 minutes sooner than they ought to do by the tables, and when the earth is beyond the sun, they happen about 7 or 8 minutes later than they ought to do, the reason being that the light of the satellites has further to go in the latter case than in the former by the diameter of the earth's orbit. Some inequalities of time may arise from the eccentricities of the orbs of the satellites, but those cannot answer in all the satellites, and at all times, to the position and distance of the earth from the sun. The mean motions of Jupiter's satellites is also swifter in his descent from his aphelium to his perihelium than in his ascent in the other half of his orb. But this inequality has no respect to the position of the earth, and in the 3 interior satellites is insensible, as I find by computation from the theory of their gravity. End of section 27.
Section 28 of Optics. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Sachin. Optics by Isaac Newton. Book 2, Part 3, Propositions 12 to 20. Proposition 12. Every ray of light in its passage through any refracting surface is put into a certain transient constitution or state, which in the progress of the ray returns at equal intervals and disposes the ray at every return to be easily transmitted through the next refracting surface, and between the returns to be easily reflected by it. This is manifest by the 5th, 9th, 12th, and 15th observations. For by those observations it appears that one and the same sort of rays at equal angles of incidence on any thin transparent plate is alternately reflected and transmitted for many successions, accordingly as the thickness of the plate increases in arithmetical progression of the numbers 0, 1, 2, 3, 4, 5, 6, 7, 8, etc. So that if the first reflection, that which makes the first or innermost of the rings of colours there described, be made at the thickness 1, the rays shall be transmitted at the thicknesses 0, 2, 4, 6, 8, 10, 12, etc., and thereby make the central spot and rings of light which appear by transmission and be reflected at the thickness 1, 3, 5, 7, 9, 11, etc., and thereby make the rings which appear by reflection. And this alternate reflection and transmission, as I gather by the 24th observation, continues for above 100 vicissitudes, and by the observations in the next part of this book, for many thousands being propagated from one surface of a glass plate to the other, though the thickness of the plate be 1/4 of an inch or above, so that this alternation seems to be propagated from every refracting surface to all distances without end or limitation. This alternate reflection and refraction depends on both the surfaces of every thin plate, because it depends on their distance. By the 21st observation, if either surface of a thin plate of Muscovy glass be wetted, the colours caused by the alternate reflection and refraction grow faint, and therefore it depends on them both. It is therefore performed at the second surface, for if it were performed at the first, before the rays arrive at the second, it would not depend on the second. It is also influenced by some action or disposition propagated from the first to the second, because otherwise at the second it would not depend on the first. And this action or disposition in its propagation intermits and returns by equal intervals, because in all its progress it inclines the ray at one distance from the first surface to be reflected by the second, at another to be transmitted by it, and that by equal intervals for innumerable vicissitudes. And because the ray is disposed to reflection at the distances 1, 3, 5, 7, 9, etc., and to transmission at the distances 0, 2, 4, 6, 8, 10, etc., for its transmission through the first surface is at the distance 0, and it is transmitted through both together, if their distance be infinitely little or much less than 1. The disposition to be transmitted at the distances 2, 4, 6, 8, 10, etc. is to be accounted a return of the same disposition which the ray first had at the distance 0, that is, at its transmission through the first refracting surface, all which is the thing I would prove. What kind of action or disposition this is, whether it consists in a circulating or a vibrating motion of the ray, or of the medium, or something else, I do not here inquire. Those that are averse from assenting to any new discoveries, but such as they can explain by an hypothesis, may for the present suppose that as stones by falling upon water put the water into an undulating motion, and all bodies by percussion excite vibrations in the air, so the rays of light, by impinging on any refracting or reflecting surface, excite vibrations in the refracting or reflecting medium or substance, and by exciting them agitate the solid parts of the refracting or reflecting body, and by agitating them cause the body to grow warm or hot, that the vibrations thus excited are propagated in the refracting or reflecting medium or substance, much after the manner that vibrations are propagated in the air for causing sound, and move faster than the rays so as to overtake them, and that when any ray is in that part of the vibration which conspires with its motion, it easily breaks through a refracting surface, but when it is in the contrary part of the vibration, which impedes its motion, it is easily reflected, and by consequence that every ray is successively disposed to be easily reflected or easily transmitted by every vibration which overtakes it. But whether this hypothesis be true or false, I do not here consider. I content myself with the bare discovery that the rays of light are by some cause or other alternately disposed to be reflected or refracted, for many vicissitudes. Definition. The returns of the disposition of any ray to be reflected I will call its fits of easy reflection, and those of its disposition to be transmitted its fits of easy transmission, and the space it passes between every return and the next return the interval of its fits. Proposition 13. The reason why the surfaces of all thick transparent bodies reflect part of the light incident on them and refract the rest is that some rays at their incidence are in fits of easy reflection and others in fits of easy transmission. This may be gathered from the 24th observation, where the light reflected by thin plates of air and glass, which to the naked eye appeared evenly white all over the plate, did through a prism appear waved with many successions of light and darkness made by alternate fits of easy reflection and easy transmission. The prism severing and distinguishing the waves of which the white reflected light was composed, as was explained above. And hence light is in fits of easy reflection and easy transmission before its incidence on transparent bodies, and probably it is put into such fits at its first emission from luminous bodies and continues in them during all its progress, for these fits are of a lasting nature, as will appear by the next part of this book. In this proposition I suppose the transparent bodies to be thick, because if the thickness of the body be much less than the interval of the fits of easy reflection and transmission of the rays, the body loseth its reflecting power. For if the rays, which at their entering into the body are put into fits of easy transmission, arrive at the farthest surface of the body before they be out of those fits, they must be transmitted, and this is the reason why bubbles of water lose their reflecting power when they grow very thin, and why all opaque bodies, when reduced into very small parts, become transparent. Proposition 14. Those surfaces of transparent bodies, which if the ray be in a fit of refraction, do refract it most strongly, if the ray be in a fit of reflection, do reflect it most easily. For we showed above in Proposition 8 that the cause of reflection is not the impinging of light on the solid impervious parts of bodies, but some other power by which those solid parts act on light at a distance. We showed also in Proposition 9 that bodies reflect and refract light by one and the same power, variously exercised in various circumstances, and in Proposition 1 that the most strongly refracting surfaces reflect the most light, all which compared together evince and rarefy both this and the last proposition. Proposition 15. In any one and the same sort of rays emerging in any angle out of any refracting surface into one and the same medium, the interval of the following fits of easy reflection and transmission are either accurately or very nearly as the rectangle of the secant of the angle of refraction, and of the secant of another angle whose sine is the first of 106 arithmetical mean proportionals between the sines of incidence and refraction, counted from the sine of refraction. This is manifest by the 7th and 19th observations. Proposition 16. In several sorts of rays emerging in equal angles out of any refracting surface into the same medium, the intervals of the following fits of easy reflection and easy transmission are either accurately or very nearly as the cube roots of the squares of the lengths of a chord which found the notes in an 8, sol la fa sol la mi fa sol, with all their intermediate degrees answering to the colours of those raised according to the analogy described in the 7th experiment of the second part of the first book. This is manifest by the 13th and 14th observations. Proposition 17. If rays of any sort pass perpendicularly into several mediums, the intervals of the fits of easy reflection and transmission in any one medium are to those intervals in any other as the sine of incidence to the sine of refraction when the rays pass out of the first of those two mediums into the second. This is manifest by the 10th observation. Proposition 18. If the rays which paint the colour in the confine of yellow and orange pass perpendicularly out of any medium into air, the intervals of their fits of easy reflection are the 1/89,000th part of an inch, and of the same length are the intervals of their fits of easy transmission. This is manifest by the 6th observation. From these propositions it is easy to collect the intervals of the fits of easy reflection and easy transmission of any sort of rays refracted in any angle into any medium, and thence to know whether the rays shall be reflected or transmitted at their subsequent incidence upon any other pellucid medium, which thing being useful for understanding the next part of this book was here to be set down. And for the same reason I add the two following propositions. Proposition 19. If any sort of rays falling on the polite surface of any pellucid medium be reflected back, the fits of easy reflection which they have at the point of reflection shall still continue to return, and the returns shall be at distances from the point of reflection in the arithmetical progression of the numbers 2, 4, 6, 8, 10, 12, etc. And between these fits the rays shall be in fits of easy transmission. For since the fits of easy reflection and easy transmission are of a returning nature, there is no reason why these fits, which continued till the ray arrived at the reflecting medium, and there inclined the ray to reflection, should there cease. And if the ray at the point of reflection was in a fit of easy reflection, the progression of the distances of these fits from that point must begin from 0, and so be of the numbers 0, 2, 4, 6, 8, etc. And therefore the progression of the distances of the intermediate fits of easy transmission, reckoned from the same point, must be in the progression of the odd numbers 1, 3, 5, 7, 9, etc., contrary to what happens when the fits are propagated from points of refraction. Proposition 20. The intervals of the fits of easy reflection and easy transmission propagated from points of reflection into any medium are equal to the intervals of the like fits which the same rays would have if refracted into the same medium in angles of refraction equal to their angles of reflection. For when light is reflected by the second surface of thin plates, it goes out afterwards freely at the first surface to make the rings of colours which appear by reflection, and by the freedom of its egress makes the colours of these rings more vivid and strong than those which appear on the other side of the plates by the transmitted light. The reflected rays are therefore in fits of easy transmission at their egress, which would not always happen if the intervals of the fits within the plate after reflection were not equal, both in length and number, to their intervals before it, and this confirms also the proportions set down in the former proposition. For if the rays, both in going in and out at the first surface, be in fits of easy transmission, and the intervals and numbers of those fits between the first and second surface, before and after reflection, be equal, the distances of the fits of easy transmission from either surface must be in the same progression after reflection as before, that is, from the first surface which transmitted them in the progression of the even numbers 0, 2, 4, 6, 8, etc., and from the second which reflected them in that of the odd numbers 1, 3, 5, 7, etc. But these two propositions will become much more evident by the observations in the following part of this book. End of section 28. Recording by Sachin, London.
Section 29 of Optics. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Pamela Krantz. Optics by Isaac Newton. Book 2, Part 4. Observations 1 through 6. Observations concerning the reflections and colors of thick, transparent, polished plates. There is no glass or speculum, how well soever polished, but besides the light which it refracts or reflects regularly, scatters every way irregularly a faint light, by means of which the polished surface, when illuminated in a dark room by a beam of the sun's light, may be easily seen in all positions of the eye. There are certain phenomena of this scattered light, which, when I first observed them, seemed very strange and surprising to me. My observations were as follows. Observation 1. The sun shining into my darkened chamber through a hole 1/3 of an inch wide, I let the intromitted beam of light fall perpendicularly upon a glass speculum, ground concave on one side and convex on the other, to a sphere of 5 feet and 11 inches radius, and quicksilvered over on the convex side, and holding a white opaque chart or a quire of paper at the center of the spheres, to which the speculum was ground, that is, at the distance of about 5 feet and 11 inches from the speculum, in such manner that the beam of light might pass through a little hole made in the middle of the chart to the speculum, and thence be reflected back to the same hole. I observed upon the chart 4 or 5 concentric irises or rings of colours, like rainbows, encompassing the whole much after the manner that those, which in the fourth and following observations of the first part of this book appeared between the object glasses, encompassed the black spot, but yet larger and fainter than those. These rings, as they grew larger and larger, became diluter and fainter, so that the fifth was scarce visible. Yet sometimes, when the sun shone very clear, there appeared faint lineaments of a sixth and seventh. If the distance of the chart from the speculum was much greater or much less than that of 6 feet, the rings became dilute and vanished. And if the distance of the Speculum from the window was much greater than that of 6 Feet, the reflected beam of Light would be so broad at the distance of 6 Feet from the Speculum where the rings appeared, as to obscure 1 or 2 of the innermost rings. And therefore I usually placed the Speculum at about 6 Feet from the window, so that its Focus might there fall in with the Center of its concavity at the rings upon the Chart. And this posture is always to be understood in the following Observations where no other is expressed. Observation 2. The Colours of these Rainbows succeeded one another from the Center outwards, in the same form and order with those which were made in the 9th Observation of the first part of this book by Light not reflected, but transmitted through the 2 Object glasses. For first, there was in their common Center a white round spot of faint Light, something broader than the reflected beam of Light, which beam sometimes fell upon the middle of the spot, and sometimes by a little inclination of the Speculum receded from the middle, and left the spot white to the Center. This white spot was immediately encompassed with a dark gray or russet, and that dark gray with the Colours of the first Iris, which Colours on the inside next the dark gray were a little violet and indigo, and next to that a blue, which on the outside grew pale, and then succeeded a little greenish yellow, and after that a brighter yellow, and then on the outward edge of the Iris a red, which on the outside inclined to purple. This Iris was immediately encompassed with a second, whose Colours were in order from the inside outwards, purple, blue, green, yellow, light red, a red mixed with purple. Then immediately followed the Colours of the third Iris, which were in order outwards a green inclining to purple, a good green, and a red more bright than that of the former Iris. The fourth and fifth Iris seemed of a bluish green within and red without, but so faintly that it was difficult to discern the Colours. Observation 3. Measuring the diameters of these rings upon the Chart as accurately as I could, I found them also in the same proportion to one another with the rings made by light transmitted through the 2 Object glasses. For the diameters of the 4 first of the bright rings, measured between the brightest parts of their orbits, at the distance of 6 Feet from the Speculum, were 1 11/16, 2 3/8, 2 11/12, 3 3/8 inches, whose squares are in arithmetical progression of the numbers 1, 2, 3, 4. If the white circular spot in the middle be reckoned amongst the rings, and its central light, where it seems to be most luminous, be put equipollent to an infinitely little ring, the squares of the diameters of the rings will be in the progression 0, 1, 2, 3, 4, etc. I measured also the diameters of the dark circles between these luminous ones, and found their squares in the progression of the numbers 1/2, 1 1/2, 2 1/2, 3 1/2, etc. The diameters of the first 4 at the distance of 6 Feet from the Speculum being 1 3/16, 2 1/16, 2 2/3, 3 3/20 inches. If the distance of the Chart from the Speculum was increased or diminished, the diameters of the circles were increased or diminished proportionally. Observation 4. By the analogy between these rings and those described in the observations of the first part of this book, I suspected that there were many more of them which spread into one another, and by interfering mixed their Colours, and diluted one another so that they could not be seen apart. I viewed them therefore through a Prism, as I did those in the 24th Observation of the first part of this book. And when the Prism was so placed as by refracting the Light of their mixed Colours to separate them, and distinguish the rings from one another as it did those in that observation, I could then see them distincter than before, and easily number 8 or 9 of them, and sometimes 12 or 13. And had not their Light been so very faint, I question not but that I might have seen many more. Observation 5. Placing a Prism at the window to refract the intromitted beam of light and cast the oblong spectrum of Colours on the Speculum, I covered the Speculum with a black paper which had in the middle of it a hole to let any one of the Colours pass through to the Speculum, whilst the rest were intercepted by the paper. and now I found rings of that Colour only which fell upon the Speculum. If the Speculum was illuminated with red, the rings were totally red with dark intervals. If with blue, they were totally blue, and so of the other Colours. And when they were illuminated with any one Colour, the squares of their diameters, measured between their most luminous parts, were in the arithmetical progression of the numbers 0, 1, 2, 3, 4, and the squares of the diameters of their dark intervals in the progression of the intermediate numbers 1/2, 1 1/2, 2 1/2, 3 1/2. But if the Colour was varied, they varied their magnitude. In the red they were largest, in the indigo and violet least, and in the intermediate Colours yellow, green, and blue, they were of several intermediate bignesses answering to the Colour, that is, greater in yellow than in green, and greater in green than in blue. And hence I knew that when the Speculum was illuminated with white Light, the red and yellow on the outside of the rings were produced by the least refrangible Rays, and the blue and violet by the most refrangible, and that the Colours of each ring spread into the Colours of the neighbouring rings on either side, after the manner explained in the first and second part of this book, and by mixing diluted one another, so that they could not be distinguished, unless near the Center where they were least mixed. For in this observation I could see the rings more distinctly, and to a greater number than before, being able in the yellow Light to number 8 or 9 of them, besides a faint shadow of a 10th. To satisfy myself how much the Colours of the several rings spread into one another, I measured the diameters of the second and third rings, and found them when made by the confine of the red and orange to be to the same diameters when made by the confine of blue and indigo, as 9 to 8 or thereabouts. For it was hard to determine this proportion accurately. Also the circles made successively by the red, yellow, and green differed more from one another than those made successively by the green, blue, and indigo. For the circle made by the violet was too dark to be seen. To carry on the computation, let us therefore suppose that the differences of the diameters of the circles made by the outmost red, the confine of red and orange, the confine of orange and yellow, the confine of yellow and green, the confine of green and blue, the confine of blue and indigo, the confine of indigo and violet, and outmost violet, are in proportion as the differences of the lengths of a monochord, which sound the tones in an 8, sol, la, fa, sol, la, mi, fa, sol; that is, as the numbers 1/9, 1/18, 1/12, 1/12, 2/27, 1/27, 1/18. And if the diameter of the circle made by the confine of red and orange be 9a, and that of the circle made by the confine of blue and indigo be 8a as above, their difference, 9a minus 8a, will be to the difference of the diameters of the circles made by the outmost red, and by the confine of red and orange, as 1/18 plus 1/12 plus 1/12 plus 2/27 to 1/9, that is, as 8/27 to 1/9, or 8 to 3. And to the difference of the circles made by the outmost violet and by the confine of blue and indigo, as 1/18 plus 1/12 plus 1/12 plus 2/27 to 1/27 plus 1/18, that is, as 8/27 to 5/54, or as 16 to 5. And therefore these differences will be 3/8 a and 5/16 a. Add the first to 9a and subduct the last from 8a, and you will have the diameters of the circles made by the least and most refrangible rays, 75/8 a and 61½ a. These diameters are therefore to one another as 75 to 61½ or 50 to 41, and their squares as 2500 to 1681. That is, as 3 to 2 very nearly, which proportion differs not much from the proportion of the diameters of the circles made by the outmost red and outmost violet in the 13th observation of the first part of this book. Observation 6. Placing my eye where these rings appeared plainest, I saw the Speculum tinged all over with waves of Colours, red, yellow, green, blue, like those which in the observations of the first part of this book appeared between the object glasses and upon bubbles of water, but much larger. And after the manner of those, they were of various magnitudes in various positions of the eye, swelling and shrinking as I moved my eye this way and that way. They were formed like arcs of concentric circles, as those were. And when my eye was over against the Center of the concavity of the Speculum, that is 5 feet and 10 inches distant from the Speculum, their common Center was in a right line with that Center of concavity, and with the hole in the window. But in other postures of my eye their Center had other positions. They appeared by the light of the clouds propagated to the Speculum through the hole in the window. And when the Sun shone through that hole upon the Speculum, his light upon it was of the Colour of the ring whereon it fell, but by its splendor obscured the rings made by the light of the clouds, unless when the Speculum was removed to a great distance from the window, so that his light upon it might be broad and faint. By varying the position of my eye, and moving it nearer to or farther from the direct beam of the Sun's light, the Colour of the Sun's reflected light constantly varied upon the Speculum, as it did upon my eye, the same Colour always appearing to a bystander upon my eye which to me appeared upon the Speculum. And thence I knew that the rings of Colours upon the chart were made by these reflected Colours propagated thither from the Speculum in several angles, and that their production depended not upon the termination of light and shadow. End of Section 29. Recorded by Pamela Krantz. Section 30 of Optics. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Pamela Krantz. Opticks by Isaac Newton, Book 2, Part 4, Observations 7 through 9. Observation 7. By the analogy of all these phenomena with those of the like rings of Colours described in the first part of this book, it seemed to me that these Colours were produced by this thick plate of glass, much after the manner that those were produced by very thin plates. For upon trial I found that if the quicksilver were rubbed off from the back side of the Speculum, the glass alone would cause the same rings of Colours, but much more faint than before. And therefore the phenomenon depends not upon the quicksilver, unless so far as the quicksilver by increasing the reflection of the back side of the glass increases the light of the rings of Colours. I found also that a Speculum of metal without glass, made some years since for optical uses, and very well wrought, produced none of those rings, and thence I understood that these rings arise not from one specular surface alone, but depend upon the two surfaces of the plate of glass whereof the Speculum was made, and upon the thickness of the glass between them. For as in the 7th and 19th observations of the first part of this book, a thin plate of air, water, or glass of an even thickness appeared of one Colour when the Rays were perpendicular to it, of another when they were a little oblique, of another when more oblique, of another when still more oblique, and so on. So here in the 6th observation the light which emerged out of the glass in several obliquities made the glass appear of several Colours, and being propagated in those obliquities to the chart, there painted rings of those Colours. And as the reason why a thin plate appeared of several Colours in several obliquities of the Rays, was that the Rays of one and the same sort are reflected by the thin plate at one obliquity and transmitted at another, and those of other sorts transmitted where these are reflected, and reflected where these are transmitted. So the reason why the thick plate of glass whereof the Speculum was made did appear of various Colours in various obliquities, and in those obliquities propagated those Colours to the chart, was, that the Rays of one and the same sort did at one obliquity emerge out of the glass, at another did not emerge, but were reflected back towards the quicksilver by the hither surface of the glass, and accordingly as the obliquity became greater and greater, emerged and were reflected alternately from many successions, and that in one and the same obliquity the Rays of one sort were reflected, and those of another transmitted. This is manifest by the 5th observation of this part of this book. For in that observation, when the Speculum was illuminated by any one of the prismatic Colours, that Light made many Rings of the same Colour upon the Chart with dark Intervals, and therefore at its emergence out of the Speculum was alternately transmitted, and not transmitted from the Speculum to the Chart for many successions, according to the various Obliquities of its emergence. And when the Colour cast on the Speculum by the Prism was varied, the Rings became of the Colour cast on it, and varied their bigness with their Colour, and therefore the Light was now alternately transmitted, and not transmitted from the Speculum to the Chart at other Obliquities than before. It seemed to me therefore that these Rings were of one and the same original with those of thin Plates, but yet with this difference, that those of thin Plates are made by the alternate Reflexions and Transmissions of the Rays at the second Surface of the Plate, after one passage through it, but here the Rays go twice through the Plate before they are alternately reflected and transmitted. First they go through it from the first Surface to the Quicksilver, and then return through it from the Quicksilver to the first Surface, and there are either transmitted to the Chart or reflected back to the Quicksilver, accordingly as they are in their fits of easy reflection or transmission when they arrive at that Surface. For the Intervals of the fits of the Rays which fall perpendicularly on the Speculum, and are reflected back in the same perpendicular lines, by reason of the equality of these angles and lines, are of the same length and number within the Glass after reflection as before, by the 19th Proposition of the 3rd part of this book. And therefore, since all the Rays that enter through the first Surface are in their fits of easy transmission at their entrance, and as many of these as are reflected by the second are in their fits of easy reflection there, all these must be again in their fits of easy transmission at their return to the first, and by consequence there go out of the Glass to the Chart, and form upon it the white spot of light in the center of the Rings. For the reason holds good in all sorts of Rays, and therefore all sorts must go out promiscuously to that spot, and by their mixture cause it to be white. But the Intervals of the fits of those Rays which are reflected more obliquely than they enter, must be greater after reflection than before, by the 15th and 20th Propositions. And thence it may happen that the Rays at their return to the first Surface may in certain Obliquities be in fits of easy reflection, and return back to the Quicksilver, and in other intermediate Obliquities be again in fits of easy transmission, and so go out to the Chart, and paint on it the Rings of Colours about the white spot. And because the Intervals of the fits at equal Obliquities are greater and fewer in the less refrangible Rays, and less and more numerous in the more refrangible, therefore the less refrangible at equal Obliquities shall make fewer Rings than the more refrangible, and the Rings made by those shall be larger than the like number of Rings made by these. That is, the red Rings shall be larger than the yellow than the green than the blue, and the blue than the violet, as they were really found to be in the 5th observation. And therefore the first Ring of all Colours encompassing the white spot of light shall be red without any violet within, and yellow and green and blue in the middle, as it was found in the 2nd observation. And these Colours in the 2nd Ring and those that follow shall be more expanded, till they spread into one another and blend one another by interfering. These seem to be the reasons of these Rings in general, and this put me upon observing the thickness of the Glass, and considering whether the dimensions and proportions of the Rings may be truly derived from it by computation. Observation 8. I measured therefore the thickness of this concavo convex Plate of Glass, and found it everywhere 1/4 of an Inch precisely. Now by the 6th observation of the first part of this book, a thin plate of air transmits the brightest light of the first Ring, that is, the bright yellow, when its thickness is 1/89,000th part of an Inch, and by the 10th observation of the same part, a thin plate of glass transmits the same light of the same Ring, when its thickness is less in proportion of the sine of refraction to the sine of incidence, that is, when its thickness is the 1,513,000th or 1/137,545th part of an Inch, supposing the sines are as 11 to 17. And if this thickness be doubled, it transmits the same bright light of the second ring. If tripled, it transmits that of the third, and so on, the bright yellow light in all these cases being in its fits of transmission. And therefore if its thickness be multiplied 34,386 times, so as to become 1/4 of an inch, it transmits the same bright light of the 34,386th ring. Suppose this be the bright yellow light transmitted perpendicularly from the reflecting convex side of the glass through the concave side to the white spot in the center of the rings of colours on the chart, and by a rule in the 7th and 19th observations in the first part of this book, and by the 15th and 20th propositions of the third part of this book, if the rays be made oblique to the glass, the thickness of the glass requisite to transmit the same bright light of the same ring in any obliquity is to this thickness of 1/4 of an inch as the secant of a certain angle to the radius, the sine of which angle is the first of 106 arithmetical means between the sines of incidence and refraction, counted from the sine of incidence when the refraction is made out of any plated body into any medium encompassing it, that is, in this case, out of glass into air. Now if the thickness of the glass be increased by degrees so as to bear to its first thickness, that is, that of 1/4 of an inch, the proportions which 34,386, the number of fits of the perpendicular rays in going through the glass towards the white spot in the center of the rings, hath to 34,385, 34,384, 34,383, and 34,382, the numbers of the fits of the oblique rays in going through the glass towards the first, second, third, and fourth rings of colours, and if the first thickness be divided into 100,000,000 equal parts, the increased thicknesses will be 100,002,908, 100,005,816, 100,008,725, and 100,011,633, and the angles of which these thicknesses are secants will be 26 minutes 13 seconds, 37 minutes 5 seconds, 45 minutes 6 seconds, and 52 minutes 26 seconds, the radius being 100,000,000, and the sines of these angles are 762, 1079, 1321, and 1525, and the proportional sines of refraction 1172, 1659, 2031, and 2345, the radius being 100,000. For since the sines of incidence out of glass into air are to the sines of refraction as 11 to 17, and to the above mentioned secants as 11 to the first of 106 arithmetical means between 11 and 17, that is, as 11 to 11 and 6/106, those secants will be to the sines of refraction as 11 and 6/106 to 17, and by this analogy will give these sines. So then, if the obliquities of the rays to the concave surface of the glass be such that the sines of their refraction in passing out of the glass through that surface into the air be 1172, 1659, 2031, 2345, the bright light of the 34,386th ring shall emerge at the thicknesses of the glass, which are to 1/4 of an inch, as 34,386 to 34,385, 34,384, 34,383, 34,382, respectively. And therefore, if the thickness in all these cases be 1/4 of an inch, as it is in the glass of which the speculum was made, the bright light of the 34,385th ring shall emerge where the sine of refraction is 1172, and that of the 34,384th, 34,383rd, and 34,382nd ring where the sine is 1659, 2031, and 2345 respectively. And in these angles of refraction the light of these rings shall be propagated from the speculum to the chart, and there paint rings about the white central round spot of light which we said was the light of the 34,386th ring, and the semi-diameters of these rings shall subtend the angles of refraction made at the concave surface of the speculum, and by consequence their diameters shall be to the distance of the chart from the speculum as those sines of refraction doubled are to the radius, that is, as 1172, 1659, 2031, and 2345 doubled are to 100,000. And therefore, if the distance of the chart from the concave surface of the speculum be 6 feet, as it was in the third of these observations, the diameters of the rings of this bright yellow light upon the chart shall be 1.688, 2.389, 2.925, 3.375 inches. For these diameters are to 6 feet as the above mentioned sines doubled are to the radius. Now these diameters of the bright yellow rings thus found by computation are the very same with those found in the third of these observations by measuring them, that is, with 1 11/16, 2 3/8, 2 11/12, and 3 3/8 inches. And therefore the theory of deriving these rings from the thickness of the plate of glass of which the speculum was made and from the obliquity of the emerging rays agrees with the observation. In this computation I have equalled the diameters of the bright rings made by light of all colours to the diameters of the rings made by the bright yellow. For this yellow makes the brightest part of the rings of all colours. If you desire the diameters of the rings made by the light of any other unmixed colour, you may find them readily by putting them to the diameters of the bright yellow ones in a subduplicate proportion of the intervals of the fits of the rays of those colours, when equally inclined to the refracting or reflecting surface which caused those fits. That is, by putting the diameters of the rings made by the rays in the extremities and limits of the 7 colours, red, orange, yellow, green, blue, indigo, violet, proportional to the cube roots of the numbers 1, 8/9, 5/6, 3/4, 2/3, 3/5, 9/16, 1/2, which express the lengths of a monochord sounding the notes in an eighth. For by this means the diameters of the rings of these colours will be found pretty nearly in the same proportion to one another, which they ought to have by the fifth of these observations. And thus I satisfied myself that these rings were of the same kind and original with those of thin plates, and by consequence that the fits or alternate dispositions of the rays to be reflected and transmitted are propagated to great distances from every reflecting and refracting surface. But yet to put the matter out of doubt, I added the following observation. Observation 9. If these rings thus depend on the thickness of the plate of glass, their diameters at equal distances from several speculums made of such concavo-convex plates of glass as are ground on the same sphere ought to be reciprocally in a subduplicate proportion of the thicknesses of the plates of glass. And if this proportion be found true by experience, it will amount to a demonstration that these rings, like those formed in thin plates, do depend on the thickness of the glass. I procured therefore another concavo-convex plate of glass ground on both sides to the same sphere with the former plate. Its thickness was 5/62 parts of an inch, and the diameters of the 3 first bright rings measured between the brightest parts of their orbits at the distance of 6 feet from the glass were 3, 4 1/6, 5 1/8 inches. Now the thickness of the other glass being 1/4 of an inch was to the thickness of this glass as 1/4 to 5/62, that is, as 31 to 10, or 310,000,000 to 100,000,000. And the roots of these numbers are 17,607 and 10,000. And in the proportion of the first of these roots to the second are the diameters of the bright rings made in this observation by the thinner glass. 3, 4 1/6, 5 1/8 to the diameters of the same rings made in the third of these observations by the thicker Glass 1 11/16, 2 3/8, 2 11/12, that is, the diameters of the rings are reciprocally in a subduplicate proportion of the thicknesses of the Plates of Glass. So then in Plates of Glass which are alike concave on one side and alike convex on the other side, and alike quicksilvered on the convex sides, and differ in nothing but their thickness, the diameters of the rings are reciprocally in a subduplicate proportion of the thicknesses of the plates. And this shows sufficiently that the rings depend on both the surfaces of the glass. They depend on the convex surface because they are more luminous when that surface is quicksilvered over than when it is without quicksilver. They depend also upon the concave surface because without that surface a speculum makes them not. They depend on both surfaces and on the distances between them, because their bigness is varied by varying only that distance, and this dependence is of the same kind with that which the colours of thin plates have on the distance of the surfaces of those plates, because the bigness of the rings and their proportion to one another, and the variation of their bigness arising from the variation of the thickness of the glass, and the orders of their colours, is such as ought to result from the propositions in the end of the third part of this book, derived from the Phenomena of the Colours of thin Plates set down in the first part. There are yet other Phenomena of these rings of Colours, but such as follow from the same propositions, and therefore confirm both the truth of those propositions, and the analogy between these rings and the rings of Colours made by very thin Plates. I shall subjoin some of them. End of Section 30. Recording by Pamela Krantz. Section 31 of Optics. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Pamela Krantz. Optics by Isaac Newton. Book 2, Part 4, Observations 10 through 13. Observation 10. When the beam of the sun's light was reflected back from the speculum not directly to the hole in the window, but to a place a little distant from it, the common centre of that spot, and of all the rings of colours fell in the middle way between the beam of the incident light and the beam of the reflected light, and by consequence in the centre of the spherical concavity of the speculum, whenever the chart on which the rings of colours fell was placed at that centre. And as the beam of reflected light by inclining the speculum receded more and more from the beam of incident light and from the common centre of the coloured rings between them, those rings grew bigger and bigger, and so also did the white round spot, and new rings of colours emerged successively out of their common centre, and the white spot became a white ring encompassing them. And the incident and reflected beams of light always fell upon the opposite parts of this white ring, illuminating its perimeter like two mock suns in the opposite parts of an iris. So then the diameter of this ring, measured from the middle of its light on one side to the middle of its light on the other side, was always equal to the distance between the middle of the incident beam of light and the middle of the reflected beam measured at the chart on which the rings appeared. And the rays which formed this ring were reflected by the speculum in angles equal to their angles of incidence, and by consequence to their angles of refraction at their entrance into the glass. But yet their angles of reflection were not in the same planes with their angles of incidence. Observation 11. The colours of the new rings were in a contrary order to those of the former, and arose after this manner. The white round spot of light in the middle of the rings continued white to the centre, till the distance of the incident and reflected beams of the chart was about 7/8 parts of an inch, and then it began to grow dark in the middle. And when that distance was about 1 3/16 of an inch, the white spot was become a ring encompassing a dark round spot, which in the middle inclined to violet and indigo. And the luminous rings encompassing it were grown equal to those dark ones which in the 4 first observations encompassed them. That is to say, the white spot was grown a white ring equal to the first of those dark rings, and the first of those luminous rings was now grown equal to the second of those dark ones, and the second of those luminous ones to the third of those dark ones, and so on. For the diameters of the luminous rings were now 1 3/16, 2 1/16, 2 2/3, 3 3/20, etc. inches. When the distance between the incident and reflected beams of light became a little bigger, there emerged out of the middle of the dark spot after the indigo a blue, and then out of that blue a pale green, and soon after a yellow and red. And when the Colour at the center was brightest, being between yellow and red, the bright rings were grown equal to those rings which in the 4 first observations next encompassed them. That is to say, the white spot in the middle of those rings was now become a white ring equal to the first of those bright rings, and the first of those bright ones was now become equal to the second of those, and so on. For the diameters of the white ring, and of the other luminous rings encompassing it, were now 1 11/16, 2 3/8, 2 11/12, 3 3/8, etc., or thereabouts. When the distance of the two beams of light at the chart was a little more increased, there emerged out of the middle in order after the red, a purple, a blue, a green, a yellow, and a red inclining much to purple. And when the Colour was brightest, being between yellow and red, the former indigo, blue, green, yellow, and red were become an iris, or ring of colours, equal to the first of those luminous rings which appeared in the 4 first observations. And the white ring, which was now become the second of the luminous rings, was grown equal to the second of those, and the first of those, which was now become the third ring, was become equal to the third of those, and so on. For their diameters were 1 11/16, 2 3/8, 2 11/12, 3 3/8 inches, the distance of the two beams of light and the diameter of the white ring being 2 3/8 inches. When these two beams became more distant, there emerged out of the middle of the purplish red, first a darker round spot, and then out of the middle of that spot a brighter. And now the former Colours, purple, blue, green, yellow, and purplish red, were become a ring equal to the first of the bright rings mentioned in the 4 first observations, and the rings about this ring were grown equal to the rings about that respectively, the distance between the two beams of light and the diameter of the white ring, which was now become the third ring, being about 3 inches. The Colours of the rings in the middle began now to grow very dilute, and if the distance between the two beams was increased half an inch, or an inch more, they vanished, whilst the white ring, with one or two of the rings next it on either side, continued still visible. But if the distance of the two beams of light was still more increased, these also vanished, for the light which coming from several parts of the hole in the window fell upon the speculum in several angles of incidence, made rings of several bignesses which diluted and blotted out one another, as I knew by intercepting some part of that light. For if I intercepted that part which was nearest to the axis of the speculum, the rings would be less; if the other part which was remotest from it, they would be bigger. Observation 12. When the Colours of the Prism were cast successively on the speculum, that ring, which in the 2 last observations was white, was of the same bigness in all the Colours, but the rings without it were greater in the green than in the blue, and still greater in the yellow, and greatest in the red. And on the contrary, the rings within that white circle were less in the green than in the blue, and still less in the yellow, and least in the red. For the angles of reflection of those rays which made this ring, being equal to their angles of incidence, the fits of every reflected ray within the glass after reflection are equal in length and number to the fits of the same ray within the glass before its incidence on the reflecting surface. And therefore, since all the rays of all sorts at their entrance into the glass were in a fit of transmission, they were also in a fit of transmission at their returning to the same surface after reflection, and by consequence were transmitted and went out to the white ring on the chart. This is the reason why that ring was of the same bigness in all the Colours, and why in a mixture of all it appears white. But in rays which are reflected in other angles, the intervals of the fits of the least refrangible being greatest, make the rings of their Colour in their progress from this white Ring, either outwards or inwards, increase or decrease by the greatest steps, so that the rings of this Colour without are greatest, and within least. And this is the reason why in the last Observation, when the Speculum was illuminated with white Light, the exterior Rings made by all Colours appeared red without and blue within, and the interior blue without and red within. These are the Phenomena of thick convexo concave Plates of Glass, which are everywhere of the same thickness. There are yet other Phenomena when these Plates are a little thicker on one side than on the other, and others when the Plates are more or less concave than convex, or plano-convex, or double convex. For in all these cases the Plates make Rings of Colours, but after various manners, all which, so far as I have yet observed, follow from the Propositions in the end of the third part of this book, and so conspire to confirm the truth of those Propositions. But the Phenomena are too various, and the calculations whereby they follow from those Propositions too intricate to be here prosecuted. I content myself with having prosecuted this kind of Phenomena so far as to discover their cause, and by discovering it to ratify the Propositions in the third part of this book. Observation 13. As Light reflected by a Lens quicksilvered on the back side makes the Rings of Colours above described, so it ought to make the like Rings of Colours in passing through a drop of water. At the first reflection of the Rays within the drop, some Colours ought to be transmitted, as in the case of a Lens, and others to be reflected back to the eye. For instance, if the diameter of a small drop or globule of water be about the 500th part of an inch, so that a red making Ray in passing through the middle of this globule has 250 fits of easy transmission within the globule, and that all the red making Rays which are at a certain distance from this middle Ray round about it have 249 fits within the globule, and all the like Rays at a certain farther distance round about it have 248 fits, and all those at a certain farther distance 247 fits, and so on, these concentric circles of Rays, after their transmission, falling on a white paper, will make concentric rings of red upon the paper, supposing the light which passes through one single globule strong enough to be sensible. And in like manner the Rays of other Colours will make rings of other Colours. Suppose now that in a fair day the Sun shines through a thin cloud of such globules of water or hail, and that the globules are all of the same bigness, and the Sun seen through this cloud shall appear encompassed with the like concentric rings of Colours, and the diameter of the first ring of red shall be 7 1/4 degrees, that of the second 10 1/4 degrees, that of the third 12 degrees 33 minutes. And accordingly as the globules of water are bigger or less, the rings shall be less or bigger. This is the theory, and experience answers it. For in June 1692 I saw by reflection in a vessel of stagnating water 3 halos, crowns, or rings of Colours about the Sun, like 3 little rainbows concentric to his body. The Colours of the first or innermost crown were blue next the Sun, red without, and white in the middle between the blue and red. Those of the second crown were purple and blue within, and pale red without, and green in the middle. And those of the third were pale blue within and pale red without. These crowns enclosed one another immediately, so that their Colours proceeded in this continual order from the Sun outward: blue, white, red, purple, blue, green, pale yellow and red, pale blue, pale red. The diameter of the second crown measured from the middle of the yellow and red on one side of the Sun to the middle of the same Colour on the other side was 9 1/3 degrees, or thereabouts. The diameters of the first and third I had not time to measure, but that of the first seemed to be about 5 or 6 degrees, and that of the third about 12. The like crowns appear sometimes about the Moon, for in the beginning of the year 1664, February 19th at night, I saw 2 such crowns about her. The diameter of the first or innermost was about 3 degrees, and that of the second about 5 degrees and an half. Next about the moon was a circle of white, and next about that the inner crown, which was of a bluish green within next the white, and of a yellow and red without, and next about these Colours were blue and green on the inside of the outward crown, and red on the outside of it. At the same time there appeared a Halo about 22 degrees 35 minutes distant from the Center of the Moon. It was elliptical, and its long diameter was perpendicular to the Horizon, verging below farthest from the Moon. I am told that the Moon has sometimes 3 or more concentric Crowns of Colours encompassing one another next about her body. The more equal the globules of Water or Ice are to one another, the more Crowns of Colours will appear, and the Colours will be the more lively. The Halo at the distance of 22½ degrees from the Moon is of another sort. By its being oval and remoter from the Moon below than above, I conclude that it was made by refraction in some sort of hail or snow floating in the air in an horizontal posture, the refracting angle being about 58 or 60 degrees. End of section 31. Recording by Pamela Krantz.
Section 32 of Opticks. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Avai in February 2012. Opticks by Isaac Newton. Book 3, Part 1, Observations 1 through 5. Observations concerning the inflections of the rays of light and the colors made thereby. Grimaldo has informed us that if a beam of the sun's light be let into a dark room through a very small hole, the shadows of things in this light will be larger than they ought to be if the rays went on by the bodies in straight lines, and that these shadows have 3 parallel fringes, bands, or ranks of colored light adjacent to them. But if the hole be enlarged, the fringes grow broad and run into one another, so that they cannot be distinguished. These broad shadows and fringes have been reckoned by some to proceed from the ordinary refraction of the air, but without due examination of the matter. For the circumstances of the phenomenon, so far as I have observed them, are as follows. Observation 1. I made in a piece of lead a small hole with a pin, whose breadth was the 42nd part of an inch. For 21 of those pins laid together took up the breadth of half an inch. Through this hole I let into my darkened chamber a beam of the sun's light, and found that the shadows of hairs, thread, pins, straws, and such like slender substances placed in this beam of light were considerably broader than they ought to be, if the rays of light passed on by these bodies in right lines. And particularly a hair of a man's head, whose breadth was but the 280th part of an inch, being held in this light at the distance of about 12 feet from the hole, did cast a shadow which at the distance of 4 inches from the hair was the 60th part of an inch broad, that is, above 4 times broader than the hair, and at the distance of 2 feet from the hair was about the 8 and 20th part of an inch broad, that is, 10 times broader than the hair, and at a distance of 10 feet was the 8th part of an inch broad, that is, 35 times broader. Nor is it material whether the hair be encompassed with air or with any other pellucid substance. For I wetted a polished plate of glass, and laid the hair in the water upon the glass, and then laying another polished plate of glass upon it, so that the water might fill up the space between the glasses, I held them in the aforesaid beam of light, so that the light might pass through them perpendicularly, and the shadow of the hair was at the same distances as big as before. The shadows of scratches made in polished plates of glass were also much broader than they ought to be, and the veins in polished plates of glass did also cast the like broad shadows. And therefore the great breadth of these shadows proceeds from some other cause than the refraction of the air. Let the circle X in figure 1 represent the middle of the hair. ADG, BEH, CFI, 3 rays passing by one side of the hair at several distances. KNQ, LOR, MPS, 3 other rays passing by the other side of the hair at the like distances. D, E, F, and N, O, P, the places where the rays are bent in their passage by the hair. G, H, I, and Q, R, S, the places where the rays fall on a paper GQ. IS, the breadth of the shadow of the hair cast on the paper, and TI, VS, 2 rays passing to the points I and S without bending when the hair is taken away. And it's manifest that all the light between these 2 rays TI and VS is bent in passing by the hair, and turned aside from the shadow IS, because if any part of this light were not bent, it would fall on the paper within the shadow, and there illuminate the paper, contrary to experience. And because when the paper is at a great distance from the hair, the shadow is broad, and therefore the rays TI and VS are at a great distance from one another, it follows that the hair acts upon the rays of light at a good distance in their passing by it. But the action is strongest on the rays which pass by at least distances, and grows weaker and weaker accordingly as the rays pass by at distances greater and greater, as is represented in the scheme. For thence it comes to pass that the shadow of the hair is much broader in proportion to the distance of the paper from the hair, when the paper is nearer the hair, than when it is at a great distance from it. Observation 2. The shadows of all bodies, metals, stones, glass, wood, horn, ice, etc., in this light were bordered with 3 parallel fringes or bands of coloured light, whereof that which was contiguous to the shadow was broadest and most luminous, and that which was remotest from it was narrowest, and so faint as not easily to be visible. It was difficult to distinguish the colours, unless when the light fell very obliquely upon a smooth paper, or some other smooth white body, so as to make them appear much broader than they would otherwise do. And then the colours were plainly visible in this order. The first or innermost fringe was violet and deep blue next the shadow, and then light blue, green, and yellow in the middle, and red without. The second fringe was almost contiguous to the first, and the third to the second, and both were blue within, and yellow and red without, but their colours were very faint, especially those of the third. The colours therefore proceeded in this order from the shadow: violet, indigo, pale blue, green, yellow, red; blue, yellow, red; pale blue, pale yellow, and red. The shadows made by scratches and bubbles in polished plates of glass were bordered with the like fringes of coloured light. And if plates of looking glass slooped off near the edges with a diamond cut be held in the same beam of light, the light which passes through the parallel planes of the glass will be bordered with the like fringes of colours where those planes meet with the diamond cut, and by this means there will sometimes appear 4 or 5 fringes of colours. Let AB, CD, in figure 2, represent the parallel planes of a looking glass, and BD the plane of the diamond cut, making at B a very obtuse angle with the plane AB. And let all the light between the rays ENI and FBM pass directly through the parallel planes of the glass, and fall upon the paper between I and M, and all the light between the rays GO and HD be refracted by the oblique plane of the diamond cut BD, and fall upon the paper between K and L, and the light which passes directly through the parallel planes of the glass and falls upon the paper between I and M will be bordered with 3 or more fringes at M. So, by looking on the sun through a feather or black riband held close to the eye, several rainbows will appear, the shadows which the fibers or threads cast on the tunica retina being bordered with the like fringes of colors. Observation 3. When the hair was 12 feet distant from this hole, and its shadow fell obliquely upon a flat white scale of inches and parts of an inch placed half a foot beyond it, and also when the shadow fell perpendicularly upon the same scale placed 9 feet beyond it, I measured the breadth of the shadow and fringes as accurately as I could, and found them in parts of an inch as follows. The breadth of the shadow at the distance of half a foot, 1/54 parts of an inch. At the distance of 9 feet, 1/9 parts of an inch. The breadth between the middles of the brightest light of the innermost fringes on either side the shadow, at the distance of half a foot, 1/38 or 1/39 parts of an inch. At the distance of 9 feet, 7/50 parts of an inch. The breadth between the middles of the brightest light of the middlemost fringes on either side the shadow, at the distance of half a foot, 1/23½ parts of an inch. At the distance of 9 feet, 4/17 parts of an inch. The breadth between the middles of the brightest light of the outmost fringes on either side the shadow, at the distance of half a foot, 1/18 parts of an inch, or 1/18½ parts of an inch. At the distance of 9 feet, 3/10 parts of an inch. The distance between the middles of the brightest light of the first and second fringes, at the distance of half a foot, 1/120 parts of an inch. At the distance of 9 feet, 1/21 parts of an inch. The distance between the middles of the brightest light of the second and third fringes, at the distance of half a foot, 1/170 parts of an inch. At the distance of 9 feet, 1/31 parts of an inch. The breadth of the luminous part, green, white, yellow, and red, of the first fringe, at the distance of half a foot, 1/170 parts of an inch. At the distance of 9 feet, 1/32 parts of an inch. The breadth of the darker space between the first and second fringes, at the distance of half a foot, 1/240 parts of an inch. At the distance of 9 feet, 1/45 parts of an inch. The breadth of the luminous part of the second fringe, at the distance of half a foot, 1/290 parts of an inch. At the distance of 9 feet, 1/55 parts of an inch. The breadth of the darker space between the second and third fringes, at the distance of half a foot, 1/340 parts of an inch. At the distance of 9 feet, 1/63 parts of an inch. These measures I took by letting the shadow of the hair at half a foot distance fall so obliquely on the scale as to appear 12 times broader than when it fell perpendicularly on it at the same distance, and setting down in this table the 12th part of the measures I then took. Observation 4. When the shadow and fringes were cast obliquely upon a smooth white body, and that body was removed farther and farther from the hair, the first fringe began to appear and look brighter than the rest of the light at the distance of less than 1/4 of an inch from the hair, and the dark line or shadow between that and the second fringe began to appear at a less distance from the hair than that of the third part of an inch. the second fringe began to appear at a distance from the hair of less than half an inch, and the shadow between that and the third fringe at a distance less than an inch, and the third fringe at a distance less than 3 inches. At greater distances they became much more sensible, but kept very nearly the same proportion of their breadths and intervals which they had at their first appearing. For the distance between the middle of the first and middle of the second fringe was to the distance between the middle of the second and middle of the third fringe as 3 to 2, or 10 to 7. And the last of these two distances was equal to the breadth of the bright light or luminous part of the first fringe. And this breadth was to the breadth of the bright light of the second fringe as 7 to 4, and to the dark interval of the first and second fringe as 3 to 2, and to the like dark interval between the second and third as 2 to 1. For the breadths of the fringes seemed to be in the progression of the numbers 1, square root of 1/3, square root of 1/5, and their intervals to be in the same progression with them, that is, the fringes and their intervals together to be in the continual progression of the numbers 1, square root of 1/2, square root of 1/3, square root of 1/4, square root of 1/5, or thereabouts. And these proportions held the same very nearly at all distances from the hair, the dark intervals of the fringes being as broad in proportion to the breadth of the fringes at their first appearance as afterwards at great distances from the hair, though not so dark and distinct. Observation 5. The sun shining into my darkened chamber through a hole 1/4 of an inch broad, I placed at the distance of 2 or 3 feet from the hole a sheet of pasteboard, which was blacked all over on both sides, and in the middle of it had a hole about 3/4 of an inch square for the light to pass through. And behind the hole I fastened to the pasteboard with pitch the blade of a sharp knife, to intercept some part of the light which passed through the hole. The planes of the pasteboard and blade of the knife were parallel to one another, and perpendicular to the rays. And when they were so placed that none of the sun's light fell on the pasteboard, but all of it passed through the hole to the knife, and there part of it fell upon the blade of the knife, and part of it passed by its edge, I let this part of the light which passed by fall on a white paper 2 or 3 feet beyond the knife, and there saw 2 streams of faint light shoot out both ways from the beam of light into the shadow, like the tails of comets. But because the sun's direct light by its brightness upon the paper obscured these faint streams so that I could scarce see them, I made a little hole in the midst of the paper for that light to pass through and fall on a black cloth behind it, and then I saw the 2 streams plainly. They were like one another and pretty nearly equal in length and breadth and quantity of light. Their light at that end next the sun's direct light was pretty strong for the space of about 1/4 of an inch, or half an inch, and in all its progress from that direct light decreased gradually till it became insensible. The whole length of either of these streams measured upon the paper at the distance of 3 feet from the knife was about 6 or 8 inches, so that it subtended an angle at the edge of the knife of about 10 or 12, or at most 14 degrees. Yet sometimes I thought I saw it shoot 3 or 4 degrees farther, but with a light so very faint that I could scarce perceive it, and suspected it might, in some measure at least, arise from some other cause than the 2 streams did. For placing my eye in that light beyond the end of that stream which was behind the knife, and looking towards the knife, I could see a line of light upon its edge, and that not only when my eye was in the line of the streams, but also when it was without that line, either towards the point of the knife or towards the handle. This line of light appeared contiguous to the edge of the knife, and was narrower than the light of the innermost fringe, and narrowest when my eye was farthest from the direct light, and therefore seemed to pass between the light of that fringe and the edge of the knife, and that which passed nearest the edge to be most bent, though not all of it. End of section 32. Section 33 of Opticks. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Avai in February 2012. Opticks by Isaac Newton. Book 3, Part 1. Observations 6 through 11. Observation 6. I placed another knife by this, so that their edges might be parallel and look towards one another, and that the beam of light might fall upon both the knives, and some part of it pass between their edges. And when the distance of their edges was about the 400th part of an inch, the stream parted in the middle and left a shadow between the two parts. This shadow was so black and dark that all the light which passed between the knives seemed to be bent and turned aside to the one hand or to the other. And as the knives still approached one another, the shadow grew broader and the streams shorter at their inwards ends, which were next the shadow, until upon the contact of the knives the whole light vanished, leaving its place to the shadow. And hence I gather that the light which is least bent and goes to the inward ends of the streams passes by the edges of the knives at the greatest distance, and this distance, when the shadow begins to appear between the streams, is about the 800th part of an inch. And the light, which passes by the edges of the knives at distances still less and less, is more and more bent, and goes to those parts of the streams which are farther and farther from the direct light, because when the knives approach one another till they touch, those parts of the streams vanish last which are farthest from the direct light. Observation 7. In the fifth observation the fringes did not appear, but by reason of the breadth of the hole in the window became so broad as to run into one another, and by joining to make one continued light in the beginning of the streams. But in the sixth, as the knives approached one another, a little before the shadow appeared between the two streams, the fringes began to appear on the inner sides of the streams on either side of the direct light, 3 on one side made by the edge of one knife, and 3 on the other side made by the edge of the other knife. They were distinctest when the knives were placed at the greatest distance from the hole in the window, and still became more distinct by making the hole less, insomuch that I could sometimes see a faint lineament of a 4th fringe beyond the 3 above mentioned. And as the knives continually approached one another, the fringes grew distincter and larger, until they vanished. The outmost fringe vanished first, and the middlemost next, and the innermost last. And after they were all vanished, and the line of light which was in the middle between them was grown very broad, enlarging itself on both sides into the streams of light described in the fifth observation, the above-mentioned shadow began to appear in the middle of this line, and divided along the middle into 2 lines of light, and increased until the whole light vanished. This enlargement of the fringes was so great that the rays which go to the innermost fringe seemed to be bent above 20 times more when this fringe was ready to vanish than when one of the knives was taken away. And from this and the former observation compared, I gather that the light of the first fringe passed by the edge of the knife at a distance greater than the 800th part of an inch, and the light of the second fringe passed by the edge of the knife at a greater distance than the light of the first fringe did, and that of the third at a greater distance than that of the second, and that of the streams of light described in the fifth and sixth observations passed by the edges of the knives at less distances than that of any of the fringes. Observation 8. I caused the edges of 2 knives to be ground truly straight, and pricking their points into a board so that their edges might look towards one another, and meeting near their points contain a rectilinear angle, I fastened their handles together with pitch to make this angle invariable. The distance of the edges of the knives from one another at the distance of 4 inches from the angular point where the edges of the knives met was the 1/8 part of an inch, and therefore the angle contained by the edges was about 1 degree 54. The knives thus fixed together I placed in a beam of the sun's light, let into my darkened chamber to a hole the 42nd part of an inch wide, at the distance of 10 or 15 feet from the hole, and let the light which passed between their edges fall very obliquely upon a smooth white ruler at the distance of half an inch, or an inch, from the knives, and there saw the fringes by the 2 edges of the knives run along the edges of the shadows of the knives in lines parallel to those edges, without growing sensibly broader, till they met in angles equal to the angle contained by the edges of the knives, and where they met and joined they ended without crossing one another. But if the ruler was held at a much greater distance from the knives, the fringes where they were farther from the place of their meeting were a little narrower, and became something broader and broader as they approached nearer and nearer to one another, and after they met they crossed one another, and then became much broader than before. Whence I gather that the distances at which the fringes pass by the knives are not increased nor altered by the approach of the knives, but the angles in which the rays are there bent are much increased by that approach, and that the knife which is nearest any ray determines which way the ray shall be bent, and the other knife increases the bent. Observation 9. When the rays fall very obliquely upon the ruler at the distance of the 3rd part of an inch from the knives, the dark line between the first and second fringe of the shadow of one knife, and the dark line between the first and second fringe of the shadow of the other knife, met with one another, at the distance of the 5th part of an inch from the end of the light which passed between the knives at the concourse of their edges. And therefore the distance of the edges of the knives at the meeting of these dark lines was the 160th part of an inch. For as 4 inches to the 1/8 part of an inch, so is any length of the edges of the knives measured from the point of their concourse to the distance of the edges of the knives at the end of that length, and so is the 5th part of an inch to the 160th part. So then the dark lines above mentioned meet in the middle of the light which passes between the knives where they are distant the 160th part of an inch, and the 1/2 of that light passes by the edge of one knife at a distance not greater than the 320th part of an inch, and falling upon the paper makes the fringes of the shadow of that knife. And the other half passes by the edge of the other knife, at a distance not greater than the 320th part of an inch, and falling upon the paper makes the fringes of the shadow of the other knife. But if the paper be held at a distance from the knives greater than the 3rd part of an inch, the dark lines above mentioned meet at a greater distance than the 5th part of an inch from the end of the light which passed between the knives at the concourse of their edges, and therefore the light which falls upon the paper where those dark lines meet passes between the knives where the edges are distant above the 160th part of an inch. For at another time, when the two knives were distant 8 feet and 5 inches from the little hole in the window, made with a small pin as above, the light which fell upon the paper where the aforesaid dark lines met, passed between the knives, where the distance between their edges was as in the following table, when the distance of the paper from the knives was also as follows. Distance of the paper from the knives, 1/1/2 inch. Distance between the edges of the knives, 0.012 parts of an inch. Distance of the paper from the knives, 3 1/3 inches. Distance between the edges of the knives, 0.020 parts of an inch. Distance of the paper from the knives, 8 3/5 inches. Distance between the edges of the knives, 0.034 parts of an inch. Distance of the paper from the knives, 32 inches. Distance between the edges of the knives, 0.057 parts of an inch. Distance of the paper from the knives, 96 inches. Distance between the edges of the knives, 0.081 parts of an inch. Distance of the paper from the knives, 131 inches. Distance between the edges of the knives, 0.087 parts of an inch. And hence I gather that the light which makes the fringes upon the paper is not the same light at all distances of the paper from the knives, but when the paper is held near the knives, the fringes are made by light which passes by the edges of the knives at a less distance, and is more bent than when the paper is held at a greater distance from the knives. Observation 10. When the fringes of the shadows of the knives fell perpendicularly upon a paper at a great distance from the knives, they were in the form of hyperbolas, and their dimensions were as follows. Let C A, C B, in Fig. 3, represent lines drawn upon the paper parallel to the edges of the knives, and between which all the light would fall, if it passed between the edges of the knives without inflection. D, E, a right line drawn through C, making the angles A, C, D, B, C, E, equal to one another, and terminating all the light which falls upon the paper from the point where the edges of the knives meet, e, I, s, f, k, t, and g, l, v, 3 hyperbolical lines representing the terminus of the shadow of one of the knives, the dark line between the first and second fringes of that shadow, and the dark line between the second and third fringes of the same shadow. X, I, p, y, k, q, and z, l, r, 3 other hyperbolical lines representing the terminus of the shadow of the other knife, the dark line between the first and second fringes of that shadow, and the dark line between the second and third fringes of the same shadow. And conceive that these 3 hyperbolas are like and equal to the former 3, and cross them in the points I, k, and l, and that the shadows of the knives are terminated and distinguished from the first luminous fringes by the lines e, I, s, and x, I, p, until the meeting and crossing of the fringes, and then those lines cross the fringes in the form of dark lines, terminating the first luminous fringes within side, and distinguishing them from another light which begins to appear at I, and illuminates all the triangular space i, p, capital D, capital E, lowercase s, comprehended by these dark lines, and the right line capital D, capital E. Of these hyperbolas one asymptote is the line capital D, capital E, and their other asymptotes are parallel to the lines capital C, capital A, and capital C, capital B. Let lowercase r, lowercase v represent a line drawn anywhere upon the paper parallel to the asymptote capital D, capital E, and let this line cross the right lines capital A, capital C in lowercase m, and capital B, capital C in lowercase n, and the 6 dark hyperbolical lines in lowercase p, lowercase q, lowercase r, lowercase s, lowercase t, lowercase v, and by measuring the distances lowercase p, lowercase s, lowercase q, lowercase t, lowercase r, lowercase v, and thence collecting the lengths of the ordinates lowercase n, lowercase p, lowercase n, lowercase q, lowercase n, lowercase r, or lowercase m, lowercase s, lowercase m, lowercase t, lowercase m, lowercase v, and doing this at several distances of the line lowercase r, lowercase v from the asymptote capital D, capital D, you may find as many points of these hyperbolas as you please, and thereby know that these curve lines are hyperbolas differing little from the conical hyperbola. And by measuring the lines capital C, lowercase I, capital C, lowercase k, capital C, lowercase l, you may find other points of these curves. For instance, when the knives were distant from the hole in the window 10 feet, and the paper from the knives 9 feet, and the angle contained by the edges of the knives to which the angle A, C, B is equal, was subtended by a chord which was to the radius as 1 to 32, and the distance of the line r, v from the asymptote D, E was half an inch, I measured the lines p, s, q, t, r, v, and found them 0.35, 0.65, 0.98 inches respectively, and by adding to their halves the line 1/2 m, n, which here was the 128th part of an inch, or 0.0078 inches, the sums n, p, n, q, n, r were 0.1828, 0.3328, 0.4978 inches. I measured also the distances of the brightest parts of the fringes, which run between p, q, and s, t, q, r, and t, v, and next beyond r and v, and found them 0.5, 0.8, and 1.17 inches. Observation 11. The sun shining into my darkened room through a small round hole made in a plate of lead with a slender pin as above, I placed at the hole a prism to refract the light, and form on the opposite wall the spectrum of colours, described in the third experiment of the first book. And then I found that the shadows of all bodies held in the coloured light between the prism and the wall were bordered with fringes of the colour of that light in which they were held. In the full red light they were totally red without any sensible blue or violet, and in the deep blue light they were totally blue without any sensible red or yellow, and so in the green light they were totally green, excepting a little yellow and blue, which were mixed in the green light of the prism. And comparing the fringes made in the several coloured lights, I found that those made in the red light were largest, those made in the violet were least, and those made in the green were of a middle bigness. For the fringes with which the shadow of a man's hair were bordered, being measured cross the shadow at the distance of 6 inches from the hair, the distance between the middle and most luminous part of the first or innermost fringe on one side of the shadow, and that of the like fringe on the other side of the shadow, was in the full red light 1/37¼ of an inch, and in the full violet 7/46. And the like distance between the middle and most luminous parts of the second fringes on either side the shadow was in the full red light 1/22, and in the violet 1/27 of an inch. And these distances of the fringes held the same proportion at all distances from the hair, without any sensible variation. So then, the rays which made these fringes in the red light passed by the hair at a greater distance than those did which made the like fringes in the violet, and therefore the hair in causing these fringes acted alike upon the red light or least refrangible rays at a greater distance, and upon the violet or most refrangible rays at a less distance, and by those actions disposed the red light into larger fringes, and the violet into smaller, and the lights of intermediate colours into fringes of intermediate bignesses, without changing the colour of any sort of light. When therefore the hair in the first and second of these observations was held in the white beam of the sun's light, and cast a shadow which was bordered with 3 fringes of coloured light, those colours arose not from any new modifications impressed upon the rays of light by the hair, but only from the various inflections whereby the several sorts of rays were separated from one another, which before separation, by the mixture of all their colours, composed the white beam of the sun's light, but whenever separated compose lights of the several colours, which they are originally disposed to exhibit. In this 11th observation, where the colours are separated before the light passes by the hair, the least refrangible rays, which when separated from the rest make red, were inflected at a greater distance from the hair, so as to make 3 red fringes at a greater distance from the middle of the shadow of the hair, and the most refrangible rays, which when separated make violet, were inflected at a less distance from the hair, so as to make 3 violet fringes at a less distance from the middle of the shadow of the hair. And other rays of intermediate degrees of refrangibility were inflicted at intermediate distances from the hair, so as to make fringes of intermediate colours at intermediate distances from the middle of the shadow of the hair. And in the second observation, where all the colours are mixed in the white light which passes by the hair, these colours are separated by the various inflections of the rays, and the fringes which they make appear all together, and the innermost fringes being contiguous make one broad fringe composed of all the colours in due order, the violet lying on the inside of the fringe next the shadow, the red on the outside, farthest from the shadow, and the blue, green, and yellow in the middle. And, in like manner, the middlemost fringes of all the Colours lying in order, and being contiguous, make another broad fringe composed of all the Colours, and the outmost fringes of all the Colours lying in order and being contiguous, make a third broad fringe composed of all the Colours. These are the 3 fringes of coloured light with which the shadows of all bodies are bordered in the second observation. End of section 33.
Section 34 of Optics. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information, or to volunteer, please visit LibriVox.org. Optics, by Isaac Newton. Book 3, Part 1, Queries 1 to 15. When I made the foregoing observations, I designed to repeat most of them with more care and exactness, and to make some new ones for determining the manner how the rays of light are bent in their passage by bodies, for making the fringes of colours with the dark lines between them. But I was then interrupted, and cannot now think of taking these things into farther consideration. And since I have not finished this part of my design, I shall conclude with proposing only some queries, in order to a farther search to be made by others. Query 1. Do not bodies act upon light at a distance, and by their action bend its rays? And is not this action, ceteris paribus, strongest at the least distance? Query 2. Do not the rays which differ in refrangibility differ also in flexibility? And are they not by their different inflections separated from one another, so as after separation to make the colours in the 3 fringes above described? And after what manner are they inflected to make those fringes? Query 3. Are not the rays of light in passing by the edges and sides of bodies, bent several times backwards and forwards, with a motion like that of an eel? And do not the 3 fringes of coloured light above mentioned arise from 3 such bendings? Query 4. Do not the rays of light which fall upon bodies, and are reflected or refracted, begin to bend before they arrive at the bodies? And are they not reflected, refracted, and inflected, by one and the same principle, acting variously in various circumstances? Query 5. Do not bodies and light act mutually upon one another, that is to say, bodies upon light in emitting, reflecting, refracting and inflecting it, and light upon bodies for heating them, and putting their parts into a vibrating motion wherein heat consists? Query 6. Do not black bodies conceive heat more easily from light than those of other colours do, by reason that the light falling on them is not reflected outwards, but enters the bodies, and is often reflected and refracted within them, until it be stifled and lost? Query 7. Is not the strength and vigour of the action between light and sulphurous bodies observed above, one reason why sulphurous bodies take fire more readily, and burn more vehemently than other bodies do? Query 8. Do not all fixed bodies, when heated beyond a certain degree, emit light and shine? And is not this emission performed by the vibrating motions of their parts? And do not all bodies which abound with terrestrial parts, and especially with sulphurous ones, emit light as often as those parts are sufficiently agitated, whether that agitation be made by heat, or by friction, or percussion, or putrefaction, or by any vital motion, or any other cause? As for instance, sea water in a raging storm, quicksilver agitated in vacuo, the back of a cat, or neck of a horse, obliquely struck or rubbed in a dark place, wood, flesh and fish while they putrefy, vapours arising from putrefied waters, usually called ignis fatui, stacks of moist hay or corn growing hot by fermentation, glow worms, and the eyes of some animals by vital motions; the vulgar phosphorus agitated by the attrition of any body, or by the acid particles of the air; amber and some diamonds by striking, pressing or rubbing them; scrapings of steel struck off with a flint; iron hammered very nimbly till it becomes so hot as to kindle sulphur thrown upon it; the axle-trees of chariots taking fire by the rapid rotation of the wheels, and some liquors mixed with one another whose particles come together with an impetus, as oil of vitriol distilled from its weight of nitre, and then mixed with twice its weight of oil of aniseeds. So also a globe of glass about 8 or 10 inches in diameter, being put into a frame where it may be swiftly turned round its axis, will in turning shine where it rubs against the palm of one's hand applied to it; and if at the same time a piece of white paper or white cloth, or the end of one's finger be held at the distance of about 1/4 of an inch or half an inch from that part of the glass where it is most in motion, the electric vapour which is excited by the friction of the glass against the hand, will by dashing against the white paper, cloth or finger, be put into such an agitation as to emit light, and make the white paper, cloth or finger, appear lucid like a glowworm; and in rushing out of the glass will sometimes push against the finger so as to be felt. And the same things have been found by rubbing a long and large cylinder or glass or amber with a paper held in one's hand, and continuing the friction till the glass grew warm. Query 9. Is not fire a body heated so hot as to emit light copiously? For what else is a red hot iron than fire? And what else is a burning coal than red hot wood? Query 10. Is not flame a vapour, fume or exhalation heated red hot, that is, so hot as to shine? For bodies do not flame without emitting a copious fume, and this fume burns in the flame. The ignis fatuus is a vapour shining without heat, and is there not the same difference between this vapour and flame, as between rotten wood shining without heat and burning coals of fire? In distilling hot spirits, if the head of the still be taken off, the vapour which ascends out of the still will take fire at the flame of a candle, and turn into flame, and the flame will run along the vapour from the candle to the still. Some bodies heated by motion, or fermentation, if the heat grow intense, fume copiously, and if the heat be great enough the fumes will shine and become flame. Metals in fusion do not flame for want of a copious fume, except spelter, which fumes copiously, and thereby flames. All flaming bodies, as oil, tallow, wax, wood, fossil coals, pitch, sulphur, by flaming waste and vanish into burning smoke, which smoke, if the flame be put out, is very thick and visible, and sometimes smells strongly, but in the flame loses its smell by burning, and according to the nature of the smoke the flame is of several colours, as that of sulphur blue, that of copper opened with sublimate green, that of tallow yellow, that of camphire white. Smoke passing through flame cannot but grow red hot, and red hot smoke can have no other appearance than that of flame. When gunpowder takes fire, it goes away into flaming smoke. For the charcoal and sulphur easily take fire, and set fire to the nitre, and the spirit of the nitre being thereby rarefied into vapour, rushes out with explosion much after the manner that the vapour of water rushes out of an aeolipile. The sulphur also being volatile is converted into vapour, and augments the explosion. And the acid vapour of sulphur, namely that which distills under a bell into oil of sulphur, entering violently into the fixed body of the nitre, sets loose the spirit of the nitre, and excites a great fermentation, whereby the heat is further augmented, and the fixed body of the nitre is also rarefied into fume, and the explosion is thereby made more vehement and quick. For if salt of tartar be mixed with gunpowder, and that mixture be warmed till it takes fire, the explosion will be more violent and quick than that of gunpowder alone. which cannot proceed from any other cause than the action of the vapour of the gunpowder upon the salt of tartar, whereby the salt is rarefied. The explosion of gunpowder arises therefore from the violent action whereby all the mixture being quickly and vehemently heated, is rarefied and converted into fume and vapour, which vapour, by the violence of that action, becoming so hot as to shine, appears in the form of flame. Query 11. Do not great bodies conserve their heat the longest, their parts heating one another, and may not great dense and fixed bodies, when heated beyond a certain degree, emit light so copiously, as by the emission and reaction of its light, and the reflections and refractions of its rays within its pores to grow still hotter, till it comes to a certain period of heat, such as is that of the sun? And are not the sun and the fixed stars great earths vehemently hot, whose heat is conserved by the greatness of the bodies, and the mutual action and reaction between them, and the light which they emit, and whose parts are kept from fuming away, not only by their fixity, but also by the vast weight and density of the atmospheres incumbent upon them, and very strongly compressing them, and condensing the vapours and exhalations which arise from them? For if water be made warm in any pellucid vessel emptied of air, that water in the vacuum will bubble and boil as vehemently as it would in the open air in a vessel set upon the fire till it conceives a much greater heat. For the weight of the incumbent atmosphere keeps down the vapours, and hinders the water from boiling, until it grows much hotter than is requisite to make it boil in vacuo. Also a mixture of tin and lead being put upon a red hot iron in vacuo emits a fume and flame, but the same mixture in the open air, by reason of the incumbent atmosphere, does not so much as emit any fume which can be perceived by sight. In like manner the great weight of the atmosphere which lies upon the globe of the sun may hinder bodies there from rising up and going away from the sun in the form of vapours and fumes, unless by means of a far greater heat than that which on the surface of our earth would very easily turn them into vapours and fumes. And the same great weight may condense those vapours and exhalations as soon as they shall at any time begin to ascend from the sun, and make them presently fall back again into him, and by that action increase his heat much after the manner that in our earth the air increases the heat of a culinary fire. And the same weight may hinder the globe of the sun from being diminished, unless by the emission of light, and a very small quantity of vapours and exhalations. Query 12. Do not the rays of light in falling upon the bottom of the eye excite vibrations in the tunica retina? Which vibrations, being propagated along the solid fibres of the optic nerves into the brain, cause the sense of seeing. For because dense bodies conserve their heat a long time, and the densest bodies conserve their heat the longest, the vibrations of their parts are of a lasting nature, and therefore may be propagated along solid fibres of uniform dense matter to a great distance, for conveying into the brain the impressions made upon all the organs of sense. For that motion which can continue long in one and the same part of a body, can be propagated a long way from one part to another, supposing the body homogeneal, so that the motion may not be reflected, refracted, interrupted or disordered by any unevenness of the body. Query 13. Do not several sorts of rays make vibrations of several bignesses, which according to their bignesses excite sensations of several colours, much after the manner that the vibrations of the air, according to their several bignesses excite sensations of several sounds? And particularly do not the most refrangible rays excite the shortest vibrations for making a sensation of deep violet, the least refrangible the largest for making a sensation of deep red, and the several intermediate sorts of rays, vibrations of several intermediate bignesses to make sensations of the several intermediate colours? Query 14. May not the harmony and discord of colours arise from the proportions of the vibrations propagated through the fibres of the optic nerves into the brain, as the harmony and discord of sounds arise from the proportions of the vibrations of the air? For some colours, if they be viewed together, are agreeable to one another, as those of gold and indigo, and others disagree. Query 15. Are not the species of objects seen with both eyes united where the optic nerves meet before they come into the brain, the fibres on the right side of both nerves uniting there, and after union going thence into the brain in the nerve which is on the right side of the head, and the fibres on the left side of both nerves uniting in the same place, and after union going into the brain in the nerve which is on the left side of the head, and these two nerves meeting in the brain in such a manner that their fibres make but one entire species or picture, half of which on the right side of the sensorium comes from the right side of both eyes through the right side of both optic nerves to the place where the nerves meet, and from thence on the right side of the head into the brain, and the other half on the left side of the sensorium comes in like manner from the left side of both eyes. For the optic nerves of such animals as look the same way with both eyes, as of men, dogs, sheep, oxen, and so on, meet before they come into the brain, but the optic nerves of such animals as do not look the same way with both eyes, as of fishes and of the chameleon, do not meet, if I am rightly informed. End of section 34.
Section 35, Optics. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. This recording is by Mark Smith of Simpsonville, South Carolina. Optics by Isaac Newton. Book 3, Part 1, Queries 16 through 24. Query 16. When a man in the dark presses either corner of his eye with his finger, and turns his eye away from his finger, he will see a circle of colors like those in the feather of a peacock's tail. If the eye and the finger remain quiet, these colors vanish in a second minute of time, but if the finger be moved with a quavering motion, they appear again. Do not these colors arise from such motions excited in the bottom of the eye by the pressure and motion of the finger, as, at other times, are excited there by light for causing vision? And do not the motions once excited continue about a second of time before they cease? And when a man by a stroke upon his eye sees a flash of light, are not the like motions excited in the retina by the stroke? And when a coal of fire moved nimbly in the circumference of a circle makes the whole circumference appear like a circle of fire, is it not because the motions excited in the bottom of the eye by the rays of light are of a lasting nature, and continue till the coal of fire in going round returns to its former place? And considering the lastingness of the motions excited in the bottom of the eye by light, are they not of a vibrating nature? Query 17. If a stone be thrown into stagnating water, the waves excited thereby continue some time to arise in the place where the stone fell into the water, and are propagated from thence in concentric circles upon the surface of the water to great distances. And the vibrations or tremors excited in the air by percussion continue a little time to move from the place of percussion in concentric spheres to great distances. And in like manner, when a ray of light falls upon the surface of any pellucid body, and is there refracted or reflected, may not waves of vibrations or tremors be thereby excited in the refracting or reflecting medium at the point of incidence, and continue to arise there, and to be propagated from thence as long as they continue to arise and be propagated, when they are excited in the bottom of the eye by the pressure or motion of the finger, or by the light which comes from the coal of fire in the experiments above mentioned? And are not these vibrations propagated from the point of incidence to great distances? And do they not overtake the rays of light, and by overtaking them successively, do they not put them into the fits of easy reflection and easy transmission described above? For if the rays endeavour to recede from the densest part of the vibration, they may be alternately accelerated and retarded by the vibrations overtaking them. Query 18. If in two large tall cylindrical vessels of glass inverted, two little thermometers be suspended so as not to touch the vessels, and the air be drawn out of one of these vessels, and these vessels thus prepared be carried out of a cold place into a warm one, the thermometer in vacuo will grow warm as much, and almost as soon as the thermometer which is not in vacuo. And when the vessels are carried back into the cold place, the thermometer in vacuo will grow cold almost as soon as the other thermometer. Is not the heat of the warm room conveyed through the vacuum by the vibrations of a much subtler medium than air, which after the air was drawn out remained in the vacuum? And is not this medium the same with that medium by which light is refracted and reflected, and by whose vibrations light communicates heat to bodies, and is put into fits of easy reflection and easy transmission? And do not the vibrations of this medium in hot bodies contribute to the intenseness and duration of their heat? And do not hot bodies communicate their heat to contiguous cold ones by the vibrations of this medium propagated from them into the cold ones? And is not this medium exceedingly more rare and subtle than the air, and exceedingly more elastic and active? And doth it not readily pervade all bodies? And is it not, by its elastic force, expanded through all the heavens? Query 19. Doth not the refraction of light proceed from the different density of this ethereal medium in different places, the light receding always from the denser parts of the medium? And is not the density thereof greater in free and open spaces void of air and other grosser bodies, than within the pores of water, glass, crystal, gems, and other compact bodies? For when light passes through glass or crystal, and falling very obliquely upon the farther surface thereof, is totally reflected, the total reflection ought to proceed rather from the density and vigor of the medium without and beyond the glass, than from the rarity and weakness thereof. Query 20. Doth not this ethereal medium in passing out of water, glass, crystal, and other compact and dense bodies into empty spaces, grow denser and denser by degrees, and by that means refract the rays of light not in a point, but by bending them gradually in curved lines? And doth not the gradual condensation of this medium extend to some distance from the bodies, and thereby cause the inflections of the rays of light, which pass by the edges of dense bodies, at some distance from the bodies? Query 21. Is not this medium much rarer within the dense bodies of the sun, stars, planets, and comets, than in the empty celestial spaces between them? And in passing from them to great distances, doth it not grow denser and denser perpetually, and thereby cause the gravity of those great bodies towards one another, and of their parts towards the bodies, every body endeavouring to go from the denser parts of the medium towards the rarer? For if this medium be rarer within the sun's body than at its surface, and rarer there than at the 100th part of an inch from its body, and rarer there than at the 50th part of an inch from its body, and rarer there than at the orb of Saturn, I see no reason why the increase of density should stop anywhere, and not rather be continued through all distances from the sun to Saturn, and beyond. And though this increase of density may at great distances be exceeding slow, yet if the elastic force of this medium be exceeding great, it may suffice to impel bodies from the denser parts of the medium towards the rarer, with all that power which we call gravity. And that the elastic force of this medium is exceeding great, may be gathered from the swiftness of its vibrations. Sounds move about 1140 English feet in a second minute of time, and in 7 or 8 minutes of time they move about 100 English miles. Light moves from the sun to us in about 7 or 8 minutes of time, which distance is about 70 million English miles, supposing the horizontal parallax of the sun to be about 12 seconds. And the vibrations or pulses of this medium, that they may cause the alternate fits of easy transmission and easy reflection, must be swifter than light, and by consequence above 700,000 times swifter than sounds. And therefore the elastic force of this medium, in proportion to its density, must be above 700,000 times 700,000, that is, above 490 billion times greater than the elastic force of the air is in proportion to its density. For the velocities of the pulses of elastic mediums are in a subduplicate ratio of the elasticities and the rarities of the mediums taken together. As attraction is stronger in small magnets than in great ones in proportion to their bulk, and gravity is greater in the surfaces of small planets than in those of great ones in proportion to their bulk, and small bodies are agitated much more by electric attraction than great ones, so the smallness of the rays of light may contribute very much to the power of the agent by which they are refracted. And so, if any one should suppose that ether, like our air, may contain particles which endeavour to recede from one another, for I do not know what this ether is, and that its particles are exceedingly smaller than those of air, or even than those of light, the exceeding smallness of its particles may contribute to the greatness of the force by which those particles may recede from one another, and thereby make that medium exceedingly more rare and elastic than air, and by consequence exceedingly less able to resist the motions of projectiles, and exceedingly more able to press upon gross bodies by endeavouring to expand itself. Query 22. May not planets and comets, and all gross bodies, perform their motions more freely, and with less resistance in this ethereal medium than in any fluid, which fills all space adequately without leaving any pores, and by consequence is much denser than quicksilver or gold? And may not its resistance be so small as to be inconsiderable? For instance, if this ether, for so I will call it, should be supposed 700,000 times more elastic than our air, and above 700,000 times more rare, its resistance would be above 600 million times less than that of water. And so small a resistance would scarce make any sensible alteration in the motions of the planets in 10,000 years. If any one would ask how a medium can be so rare, let him tell me how the air, in the upper parts of the atmosphere, can be above 100,000 times rarer than gold. Let him also tell me how an electric body can by friction emit an exhalation so rare and subtle, and yet so potent, as by its emission to cause no sensible diminution of the weight of the electric body, and to be expanded through a sphere, whose diameter is above 2 feet, and yet to be able to agitate and carry up leaf copper or leaf gold at the distance of above a foot from the electric body. And how the effluvia of a magnet can be so rare and subtle as to pass through a plate of glass without any resistance or diminution of their force, and yet so potent as to turn a magnetic needle beyond the glass? Query 23. Is not vision performed chiefly by the vibrations of this medium, excited in the bottom of the eye by the rays of light, and propagated through the solid, pellucid, and uniform capillamenta of the optic nerves into the place of sensation, And is not hearing performed by the vibrations either of this or some other medium, excited in the auditory nerves by the tremors of the air, and propagated through the solid, pellucid, and uniform capillamenta of those nerves into the place of sensation? And so of the other senses. Query 24. Is not animal motion performed by the vibrations of this medium, excited in the brain by the power of the will, and propagated from thence through the solid, pellucid, and uniform capillamenta of the nerves into the muscles, for contracting and dilating them? I suppose that the capillamenta of the nerves are each of them solid and uniform, that the vibrating motion of the ethereal medium may be propagated along them from one end to the other uniformly, and without interruption. For obstructions in the nerves create palsies, and that they may be sufficiently uniform, I suppose them to be pellucid when viewed singly, though the reflections in their cylindrical surfaces may make the whole nerve, composed of many capillamenta, appear opaque and white. For opacity arises from reflecting surfaces, such as may disturb and interrupt the motions of this medium. End of Section 35 of Optics by Sir Isaac Newton.
Section 36 of Optics. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Optics by Isaac Newton. Book 3, Part 1, Queries 25 to 27. Query 25. Are there not other original properties of the rays of light, besides those already described? An instance of another original property we have in the refraction of island crystal, described first by Erasmus Bartholin, and afterwards more exactly by Hugenius in his book De la Lumière. This crystal is a pellucid fissile stone, clear as water or crystal of the rock, and without color, enduring a red heat without losing its transparency, and in a very strong heat calcining without fusion. Steeped a day or two in water, it loses its natural polish. Being rubbed on cloth, it attracts pieces of straws and other light things, like amber or glass, and with aqua fortis it makes an ebullition. It seems to be a sort of talk, and is found in form of an oblique parallelepiped, with 6 parallelogram sides, and 8 solid angles. The obtuse angles of the parallelograms are each of them 101 degrees and 52 minutes, the acute ones 78 degrees and 8 minutes. 2 of the solid angles opposite to one another, as C and E, are compassed each of them with 3 of these obtuse angles, and each of the other 6 with 1 obtuse and 2 acute ones. It cleaves easily in planes parallel to any of its sides, and not in any other planes. It cleaves with a glossy polite surface, not perfectly plain, but with some little unevenness. It is easily scratched, and by reason of its softness it takes a polish very difficultly. It polishes better upon polished looking glass than upon metal, and perhaps better upon pitch, leather, or parchment. Afterwards it must be rubbed with a little oil or white of an egg, to fill up its scratches, whereby it will become very transparent and polite. But for several experiments it is not necessary to polish it. If a piece of this crystalline stone be laid upon a book, every letter of the book seen through it will appear double, by means of a double refraction, and if any beam of light falls either perpendicularly or in any oblique angle upon any surface of this crystal, it becomes divided into 2 beams by means of the same double refraction, which beams are of the same color with the incident beam of light, and seem equal to one another in the quantity of their light, or very nearly equal. One of these refractions is performed by the usual rule of optics, the sine of incidence out of air into this crystal being to the sine of refraction, as 5 to 3. The other refraction, which may be called the unusual refraction, is performed by the following rule. Let A, D, B, C represent the refracting surface of the crystal, C the biggest solid angle at that surface, G, E, H, F the opposite surface, and C, K a perpendicular on that surface. This perpendicular makes with the edge of the crystal CF an angle of 19 degrees 3 minutes. Join KF and in it take KL, so that the angle KCL be 6 degrees 40 minutes, and the angle LCF 12 degrees 23 minutes. And if ST represent any beam of light incident at T in any angle upon the refracting surface ADBC, let TV be the refracted beam determined by the given portion of the sines 5 to 3, according to the usual rule of optics. Draw VX parallel and equal to KL. Draw it the same way from V in which L lieth from K, and joining TX, this line TX shall be the other refracted beam carried from T to X by the unusual refraction. If therefore the incident beam ST be perpendicular to the refracting surface, the two beams TV and TX, into which it shall become divided, shall be parallel to the lines CK and CL, one of those beams going through the crystal perpendicularly, as it ought to do by the usual laws of optics, and the other TX by an unusual refraction diverging from the perpendicular, and making with it an angle VTX of about 6 2/3 degrees, as is found by experience. And hence the plane VTX and such like planes which are parallel to the plane CFK may be called the planes of perpendicular refraction, and the coast towards which the lines KL and VX are drawn may be called the coast of unusual refraction. In like manner, crystal of the rock has a double refraction, but the difference of the two refractions is not so great and manifest as in island crystal. When the beam ST incident on island crystal is divided into two beams TV and TX, and these two beams arrive at the farther surface of the glass, the beam TV, which was refracted at the first surface after the usual manner, shall be again refracted entirely after the usual manner at the second surface, and the beam TX, which was refracted after the unusual manner in the first surface, shall be again refracted entirely after the unusual manner in the second surface, so that both these beams shall emerge out of the second surface in lines parallel to the first incident beam ST. And if two pieces of island crystal be placed one after another, in such manner that all the surfaces of the latter be parallel to all the corresponding surfaces of the former, the rays which are refracted after the usual manner in the first surface of the first crystal shall be refracted after the usual manner in all the following surfaces, and the rays which are refracted after the unusual manner in the first surface shall be refracted after the unusual manner in all the following surfaces, and the same thing happens, though the surfaces of the crystals be any ways inclined to one another, provided that their planes of perpendicular refraction be parallel to one another. And therefore there is an original difference in the rays of light, by means of which some rays are in this experiment constantly refracted after the usual manner, and others constantly after the unusual manner. For if the difference be not original, but arises from new modifications impressed on the rays at their first refraction, it would be altered by new modifications in the 3 following refractions, whereas it suffers no alteration, but is constant, and has the same effect upon the rays in all the refractions. The unusual refraction is therefore performed by an original property of the rays, and it remains to be inquired whether the rays have not more original properties than are yet discovered. Query 26. Have not the rays of light several sides, endued with several original properties? For if the planes of perpendicular refraction of the second crystal be at right angles with the planes of perpendicular refraction of the first crystal, the rays which are refracted after the usual manner in passing through the first crystal will be all of them refracted after the unusual manner in passing through the second crystal, and the rays which are refracted after the unusual manner in passing through the first crystal will be all of them refracted after the usual manner in passing through the second crystal. And therefore there are not 2 sorts of rays differing in their nature from one another, one of which is constantly and in all positions refracted after the usual manner, and the other constantly and in all positions after the unusual manner. The difference between the 2 sorts of rays in the experiment mentioned in the 25th question was only in the positions of the sides of the rays to the planes of perpendicular refraction. For one and the same ray is here refracted sometimes after the usual and sometimes after the unusual manner, according to the position which its sides have to the crystals. If the sides of the ray are posited the same way to both crystals, it is refracted after the same manner in them both. But if that side of the ray which looks towards the coast of the unusual refraction of the first crystal be 90 degrees from that side of the same ray which looks toward the coast of the unusual refraction of the second crystal, which may be effected by varying the position of the second crystal to the first, and by consequence to the rays of light, the ray shall be refracted after several manners in the several crystals. There is nothing more required to determine whether the rays of light which fall upon the second crystal shall be refracted after the usual or after the unusual manner, but to turn about this crystal so that the coast of this crystal's unusual refraction may be on this or on that side of the ray, and therefore every ray may be considered as having 4 sides or quarters, 2 of which, opposite to one another, incline the ray to be refracted after the unusual manner, as often as either of them are turned towards the coast of unusual refraction, and the other 2, whenever either of them are turned towards the coast of unusual refraction, do not incline it to be otherwise refracted than after the usual manner. The 2 first may therefore be called the sides of unusual refraction, and since these dispositions were in the rays before their incidence on the second, third, and fourth surfaces of the 2 crystals, and suffered no alteration, so far as appears, by the refraction of the rays in their passage through those surfaces, and the rays were refracted by the same laws in all the 4 surfaces, it appears that those dispositions were in the rays originally, and suffered no alteration by the first refraction, and that by means of those dispositions the rays were refracted at their incidence on the first surface of the first crystal, some of them after the usual and some of them after the unusual manner, accordingly as their sides of unusual refraction were then turned towards the coast of the unusual refraction of that crystal, or sideways from it. Every ray of light has therefore 2 opposite sides, originally endued with a property on which the unusual refraction depends, and the other 2 opposite sides not endued with that property, and it remains to be inquired whether there are not more properties of light by which the sides of the rays differ, and are distinguished from one another. In explaining the difference of the sides of the rays above mentioned, I have supposed that the rays fall perpendicularly on the first crystal, but if they fall obliquely on it, the success is the same. Those rays which are refracted after the usual manner in the first crystal will be refracted after the unusual manner in the second crystal, supposing the planes of perpendicular refraction to be at right angles with one another as above, and on the contrary. If the planes of the perpendicular refraction of the two crystals be neither parallel nor perpendicular to one another, but contain an acute angle, the two beams of light which emerge out of the first crystal will be each of them divided into two more at their incidence on the second crystal. For in this case the rays in each of the two beams will some of them have their sides of unusual refraction, and some of them their other sides turned towards the coast of the unusual refraction of the second crystal. Query 27. Are not all hypotheses erroneous which have hitherto been invented for explaining the phenomena of light by new modifications of the rays? For those phenomena depend not upon new modifications, as has been supposed, but upon the original and unchangeable properties of the rays. End of section 36. Section 37 of Optics. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Optics by Isaac Newton. Book 3, Part 1, Queries 28 to 29. Query 28. Are not all hypotheses erroneous, in which light is supposed to consist in pression or motion propagated through a fluid medium? For in all these hypotheses the phenomena of light have been hitherto explained by supposing that they arise from new modifications of the rays, which is an erroneous supposition. If light consisted only in pression propagated without actual motion, it would not be able to agitate and heat the bodies which refract and reflect it. If it consisted in motion propagated to all distances in an instant, it would require an infinite force every moment, in every shining particle, to generate that motion. And if it consisted in pression or motion, propagated either in an instant or in time, it would bend into the shadow. For pression or motion cannot be propagated in a fluid in right lines, beyond an obstacle which stops part of the motion, but will bend and spread every way into the quiescent medium which lies beyond the obstacle. Gravity tends downwards, but the pressure of water arising from gravity tends every way with equal force, and is propagated as readily, and with as much force sideways as downwards, and through crooked passages as through straight ones. The waves on the surface of stagnating water, passing by the sides of a broad obstacle which stops part of them, bend afterwards and dilate themselves gradually into the quiet water behind the obstacle. The waves, pulses or vibrations of the air, wherein sounds consist, bend manifestly, though not so much as the waves of water. For a bell or a cannon may be heard beyond a hill which intercepts the sight of the sounding body, and sounds are propagated as readily through crooked pipes as through straight ones. But light is never known to follow crooked passages, nor to bend into the shadow. For the fixed stars by the interposition of any of the planets cease to be seen, and so do the parts of the sun by the interposition of the moon, Mercury, or Venus. The rays which pass very near to the edges of any body are bent a little by the action of the body, as we showed above, but this bending is not towards but from the shadow, and is performed only in the passage of the ray by the body, and at a very small distance from it. So soon as the ray is past the body, it goes right on. To explain the unusual refraction of island crystal by pression or motion propagated has not hitherto been attempted, to my knowledge, except by Huygens, who, for that end, supposed 2 several vibrating mediums within that crystal. But when he tried the refractions in 2 successive pieces of that crystal, and found them such as is mentioned above, he confessed himself at a loss for explaining them. For pressions or motions, propagated from a shining body through an uniform medium, must be on all sides alike, whereas by those experiments it appears that the rays of light have different properties in their different sides. He suspected that the pulses of ether in passing through the first crystal might receive certain new modifications, which might determine them to be propagated in this or that medium within the second crystal, according to the position of that crystal. But what modifications those might be he could not say, nor think of anything satisfactory in that point. And if he had known that the unusual refraction depends not on new modifications, but on the original and unchangeable dispositions of the rays, he would have found it as difficult to explain how those dispositions which he supposed to be impressed on the rays by the first crystal could be in them before their incidence on that crystal, and, in general, how all rays emitted by shining bodies can have those dispositions in them from the beginning. To me, at least, this seems inexplicable, if light be nothing else than pression or motion propagated through ether. And it is as difficult to explain by these hypotheses how rays can be alternately in fits of easy reflection and easy transmission, unless perhaps one might suppose that there are in all space 2 ethereal vibrating mediums, and that the vibrations of one of them constitute light, and the vibrations of the other are swifter, and as often as they overtake the vibrations of the first, put them into those fits. But how 2 ethers can be diffused through all space, one of which acts upon the other, and by consequence is reacted upon, without retarding, shattering, dispersing, and confounding one another's motions, is inconceivable. And, against filling the heavens with fluid mediums, unless they be exceeding rare, a great objection arises from the regular and very lasting motions of the planets and comets in all manner of courses through the heavens. For thence it is manifest that the heavens are void of all sensible resistance, and by consequence of all sensible matter. For the resisting power of fluid mediums arises partly from the attrition of the parts of the medium, and partly from the vis inertiae of the matter. That part of the resistance of a spherical body which arises from the attrition of the parts of the medium is very nearly as the diameter, or at the most as the factum of the diameter, and the velocity of the spherical body together. And that part of the resistance which arises from the vis inertiae of the matter is as the square of that factum. And by this difference the 2 sorts of resistance may be distinguished from one another in any medium, and these being distinguished, it will be found that almost all the resistance of bodies of a competent magnitude moving in air, water, quicksilver, and such like fluids with a competent velocity arises from the vis inertiae of the parts of the fluid. Now, that part of the resisting power of any medium which arises from the tenacity, friction, or attrition of the parts of the medium may be diminished by dividing the matter into smaller parts, and making the parts more smooth and slippery. But that part of the resistance which arises from the vis inertiae is proportional to the density of the matter, and cannot be diminished by dividing the matter into smaller parts, nor by any other means than by decreasing the density of the medium. And for these reasons the density of fluid mediums is very nearly proportional to their resistance. Liquors which differ not much in density, as water, spirit of wine, spirit of turpentine, hot oil, differ not much in resistance. Water is 13 or 14 times lighter than quicksilver, and by consequence 13 or 14 times rarer, and its resistance is less than that of quicksilver, in the same proportion, or thereabouts, as I have found by experiments made with pendulums. The open air in which we breathe is 800 or 900 times lighter than water, and by consequence 800 or 900 times rarer, and accordingly its resistance is less than that of water in the same proportion or thereabouts, as I have also found by experiments made with pendulums. And in thinner air the resistance is still less, and at length, by ratifying the air, becomes insensible. For small feathers falling in the open air meet with great resistance, but in a tall glass well emptied of air they fall as fast as lead or gold, as I have seen tried several times. Whence the resistance seems still to decrease in proportion to the density of the fluid. For I do not find by any experiments that bodies moving in quicksilver, water, or air meet with any other sensible resistance than what arises from the density and tenacity of those sensible fluids, as they would do if the pores of those fluids and all other spaces were filled with a dense and subtle fluid. Now, if the resistance in a vessel well emptied of air was but 100 times less than in the open air, it would be about 1,000,000 of times less than in quicksilver. But it seems to be much less in such a vessel, and still much less in the heavens, at the height of 300 or 400 miles from the earth or above. For Mr. Boyle has showed that air may be rarefied above 10,000 times in vessels of glass, and the heavens are much emptier of air than any vacuum we can make below. For since the air is compressed by the weight of the incumbent atmosphere, and the density of air is proportional to the force compressing it, it follows by computation that at the height of about 7½ English miles from the earth, the air is 4 times rarer than at the surface of the earth, and at the height of 15 miles it is 16 times rarer than that at the surface of the earth, and at the height of 22½, 30, or 38 miles it is respectively 64, 256, or 1024 times rarer, or thereabouts, and at the height of 76, 152, 228 miles it is about 1,000,000, 10 to the 6th, 1,000,000,000,000, 10 to the 12th, or 1,000,000,000,000, 10 to the 18th times rarer, and so on. Heat promotes fluidity very much by diminishing the tenacity of bodies. It makes many bodies fluid which are not fluid in cold, and increases the fluidity of tenacious liquids, as of oil, balsam, and honey, and thereby decreases their resistance. But it decreases not the resistance of water considerably, as it would do if any considerable part of the resistance of water arose from the attrition or tenacity of its parts, and therefore the resistance of water arises principally and almost entirely from the vis inertiae of its matter, and by consequence, if the heavens were as dense as water, they would not have much less resistance than water. If as dense as quicksilver, they would not have much less resistance than quicksilver. If absolutely dense, or full of matter without any vacuum, let the matter be never so subtle and fluid, they would have a greater resistance than quicksilver. A solid globe in such a medium would lose above half its motion in moving 3 times the length of its diameter, and a globe not solid, such as are the planets, would be retarded sooner, and therefore to make way for the regular and lasting motions of the planets and comets, it's necessary to empty the heavens of all matter, except perhaps some very thin vapors, steams, or effluvia arising from the atmospheres of the earth, planets, and comets, and from such an exceedingly rare ethereal medium as we described above. A dense fluid can be of no use for explaining the phenomena of nature, the motions of the planets and comets being better explained without it. It serves only to disturb and retard the motions of those great bodies, and make the frame of nature languish. And in the pores of bodies it serves only to stop the vibrating motions of their parts, wherein their heat and activity consists. And as it is of no use, and hinders the operations of nature, and makes her languish, so there is no evidence for its existence, and therefore it ought to be rejected. And if it be rejected, the hypotheses that light consists in pression or motion propagated through such a medium are rejected with it. And for rejecting such a medium, we have the authority of those the oldest and most celebrated philosophers of Greece and Phoenicia, who made a vacuum and atoms and the gravity of atoms the first principles of their philosophy, tacitly attributing gravity to some other cause than dense matter. Later philosophers banished the consideration of such a cause out of natural philosophy, feigning hypotheses for explaining all things mechanically, and referring other causes to metaphysics, whereas the main business of natural philosophy is to argue from phenomena without feigning hypotheses, and to deduce causes from effects, till we come to the very first cause, which certainly is not mechanical, and not only to unfold the mechanism of the world, but chiefly to resolve these and such like questions. What is there in places almost empty of matter, and whence is it that the sun and planets gravitate towards one another, without dense matter between them? Whence is it that nature doth nothing in vain, and whence arises all that order and beauty which we see in the world? To what end are comets? And whence is it that planets move all one and the same way in orbs concentric, while comets move all manner of ways in orbs very eccentric? And what hinders the fixed stars from falling upon one another? How came the bodies of animals to be contrived with so much art, and for what ends were their several parts? Was the eye contrived without skill in optics, and the ear without knowledge of sounds? How do the motions of the body follow from the will, and whence is the instinct in animals? Is not the sensory of animals that place to which the sensitive substance is present, and into which the sensible species of things are carried through the nerves and brain, that there they may be perceived by their immediate presence to that substance? And these things being rightly dispatched, does it not appear from phenomena that there is a being incorporeal, living, intelligent, omnipresent, who in infinite space, as it were in his sensory, sees the things themselves intimately, and thoroughly perceives them, and comprehends them wholly by their immediate presence to himself? Of which things the images only carried through the organs of sense into our little sensoriums are there seen and beheld by that which in us perceives and thinks. And though every true step made in this philosophy brings us not immediately to the knowledge of the first cause, yet it brings us nearer to it, and on that account is to be highly valued. Query 29. Are not the rays of light very small bodies emitted from shining substances? For such bodies will pass through uniform mediums in right lines without bending into the shadow, which is the nature of the rays of light. They will also be capable of several properties, and be able to conserve their properties unchanged in passing through several mediums, which is another condition of the rays of light. Pellucid substances act upon the rays of light at a distance, in refracting, reflecting, and inflecting them, and the rays mutually agitate the parts of those substances at a distance for heating them. And this action and reaction at a distance very much resembles an attractive force between bodies. If refraction be performed by attraction of the rays, the sines of incidence must be to the sines of refraction in a given proportion, as we showed in our Principles of Philosophy. And this rule is true by experience. The rays of light in going out of glass into a vacuum are bent towards the glass, and if they fall too obliquely on the vacuum, they are bent backwards into the glass, and totally reflected. And this reflection cannot be ascribed to the resistance of an absolute vacuum, but must be caused by the power of the glass attracting the rays at their going out of it into the vacuum, and bringing them back. For if the farther surface of the glass be moistened with water, or clear oil, or liquid and clear honey, the rays which would otherwise be reflected will go into the water, oil, or honey, and therefore are not reflected before they arrive at the farther surface of the glass, and begin to go out of it. If they go out of it into the water, oil, or honey, they go on, because the attraction of the glass is almost balanced, and rendered ineffectual by the contrary attraction of the liquor. But if they go out of it into a vacuum, which has no attraction to balance that of the glass, the attraction of the glass either bends and refracts them, or brings them back and reflects them. And this is still more evident by laying together two prisms of glass, or two object glasses of very long telescopes, the one plane, the other a little convex, and so compressing them that they do not fully touch, nor are too far asunder. For the light which falls upon the farther surface of the first glass, where the interval between the glasses is not above the 10/100,000th part of an inch, will go through that surface, and through the air or vacuum between the glasses, and enter into the second glass, as was explained in the first, fourth, and eighth observations of the first part of the second book. But if the second glass be taken away, the light which goes out of the second surface of the first glass into the air or vacuum will not go on forwards, but turns back into the first glass, and is reflected, and therefore it is drawn back by the power of the first glass, there being nothing else to turn it back. Nothing more is requisite for producing all the variety of colors and degrees of refrangibility than that the rays of light be bodies of different sizes, the least of which may take violet, the weakest and darkest of the colors, and be more easily diverted by refracting surfaces from the right course, and the rest, as they are bigger and bigger, may make the stronger and more lucid colors, blue, green, yellow, and red, and be more and more difficultly diverted. Nothing more is requisite for putting the rays of light into fits of easy reflection and easy transmission, than that they be small bodies, which by their attractive powers or some other force stir up vibrations in what they act upon, which vibrations being swifter than the rays, overtake them successively, and agitate them so as by turns to increase and decrease their velocities, and thereby put them into those fits. And lastly, the unusual refraction of island crystal looks very much as if it were performed by some kind of attractive virtue lodged in certain sides both of the rays and of the particles of the crystal. For were it not for some kind of disposition or virtue lodged in some sides of the particles of the crystal, and not in their other sides, and which inclines and bends the rays towards the coast of unusual refraction, the rays which fall perpendicularly on the crystal would not be refracted towards that coast rather than towards any other coast, both at their incidence and at their emergence, so as to emerge perpendicularly by a contrary situation of the coast of unusual refraction at the second surface. The crystal, acting upon the rays after they have passed through it, and are emerging into the air, or, if you please, into a vacuum. And since the crystal, by this disposition or virtue, does not act upon the rays, unless when one of their sides of unusual refraction looks towards that coast, this argues a virtue or disposition in those sides of the rays, which answers to, and sympathizes with, that virtue or disposition of the crystal, as the poles of two magnets answer to one another. And as magnetism may be intended and remitted, and is found only in the magnet and in iron, so this virtue of refracting the perpendicular rays is greater in island crystal, less in crystal of the rock, and is not yet found in other bodies. I do not say that this virtue is magnetical. It seems to be of another kind. I only say that whatever it be, it's difficult to conceive how the rays of light, unless they be bodies, can have a permanent virtue in two of their sides, which is not in their other sides, and this without any regard to their position to the space or medium through which they pass. What I mean in this question by a vacuum, and by the attractions of the rays of light towards glass or crystal, may be understood by what was said in the 18th, 19th, and 20th questions. End of section 37.
Section 38 of Optics by Sir Isaac Newton. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. This recording is by Mark Smith of Simpsonville, South Carolina. Optics by Sir Isaac Newton, Book 3, Part 1, Queries 30 through 31. Question 30. Are not gross bodies and light convertible into one another, and may not bodies receive much of their activity from the particles of light which enter their composition? For all fixed bodies, being heated, emit light so long as they continue sufficiently hot, and light mutually stops in bodies as often as its rays strike upon their parts, as we showed above. I know no body less apt to shine than water, and yet water by frequent distillations changes into fixed earth, as Mr. Boyle has tried, and then this earth being enabled to endure a sufficient heat, shines by heat like other bodies. The changing of bodies into light, and light into bodies, is very conformable to the course of nature, which seems delighted with transmutations. Water, which is a very fluid, tasteless salt, she changes by heat into vapour, which is a sort of air, and by cold into ice, which is a hard, pellucid, brittle, fusible stone, and this stone returns into water by heat, and vapour returns into water by cold. Earth by heat becomes fire, and by cold returns into earth. Dense bodies by fermentation rarefy into several sorts of air, and this air by fermentation, and sometimes without it, returns into dense bodies. Mercury appears sometimes in the form of a fluid metal, sometimes in the form of a hard, brittle metal, sometimes in the form of a corrosive pellucid salt called sublimate, sometimes in the form of a tasteless, pellucid, volatile white earth called mercurius dulcis, or in that of a red opaque volatile earth called cinnabar, or in that of a red or white precipitate, or in that of a fluid salt, and in distillation it turns into vapour, and being agitated in vacuo, it shines like fire. And after all these changes it returns again into its first form of mercury. Eggs grow from insensible magnitudes and change into animals, tadpoles into frogs, and worms into flies. All birds, beasts and fishes, insects, trees and other vegetables, with their several parts, grow out of water and watery tinctures and salts, and by putrefaction return again into watery substances. And water standing a few days in the open air yields a tincture, which, like that of malt, by standing longer yields a sediment and a spirit, but before putrefaction is fit nourishment for animals and vegetables. And among such various and strange transmutations, why may not nature change bodies into light, and light into bodies? Question 31. Have not the small particles of bodies certain powers, virtues, or forces, by which they act at a distance, not only upon the rays of light for reflecting, refracting, and inflecting them, but also upon one another for producing a great part of the phenomena of nature? For it's well known, that bodies act one upon another by the attractions of gravity, magnetism, and electricity. And these instances show the tenor and course of nature, and make it not improbable but that there may be more attractive powers than these. For nature is very consonant and conformable to herself. How these attractions may be performed, I do not here consider. What I call attraction may be performed by impulse, or by some other means unknown to me. I use that word here to signify only in general any force by which bodies tend towards one another, whatsoever be the cause. For we must learn from the phenomena of nature what bodies attract one another, and what are the laws and properties of the attraction, before we can inquire the cause by which the attraction is performed. The attractions of gravity, magnetism, and electricity reach to very sensible distances, and so have been observed by vulgar eyes, and there may be others which reach to so small distances as hitherto escape observation, and perhaps electrical attraction may reach to such small distances even without being excited by friction. For when salt of tartar runs per deliquium, is not this done by an attraction between the particles of the salt of tartar and the particles of the water which float in the air in the form of vapours? And why does not common salt, or saltpetre, or vitriol, run per deliquium, but for want of such an attraction? Or why does not salt of tartar draw more water out of the air than in a certain proportion to its quantity, but for want of attractive force after it is satiated with water? And whence is it but from this attractive power, that water which alone distills with a gentle lukewarm heat, will not distill from salt of tartar without a great heat? And is it not from the like attractive power between the particles of oil of vitriol and the particles of water, that oil of vitriol draws to it a good quantity of water out of the air, and after it is satiated draws no more, and in distillation lets go the water very difficultly? And when water and oil of vitriol poured successively into the same vessel grow very hot in the mixing, does not this heat argue a great motion in the parts of the liquors? And does not this motion argue that the parts of the two liquors in mixing coalesce with violence, and by consequence rush towards one another with an accelerated motion? And when aqua fortis, or spirit of vitriol poured upon filings of iron dissolves the filings with a great heat and ebullition, is not this heat and ebullition effected by a violent motion of the parts? And does not that motion argue that the acid parts of the liquor rush towards the parts of the metal with violence, and run forcibly into its pores till they get between its outmost particles and the main mass of the metal, and surrounding those particles loosen them from the main mass, and set them at liberty to float off into the water? And when the acid particles, which alone would distill with an easy heat, will not separate from the particles of the metal without a very violent heat, does not this confirm the attraction between them? When spirit of vitriol poured upon common salt or saltpetre makes an ebullition with the salt, and unites with it, and in distillation the spirit of the common salt or saltpetre comes over much easier than it would do before, and the acid part of the spirit of vitriol stays behind, does not this argue that the fixed alkali of the salt attracts the acid spirit of the vitriol more strongly than its own spirit, and not being able to hold them both, lets go its own? And when oil of vitriol is drawn off from its weight of nitre, and from both the ingredients a compound spirit of nitre is distilled, and 2 parts of this spirit are poured on 1 part of oil of cloves or caraway seeds, or of any ponderous oil of vegetable or animal substances, or oil of turpentine thickened with a little balsam of sulphur, and the liquors grow so very hot in mixing, as presently to send up a burning flame, does not this very great and sudden heat argue that the 2 liquors mix with violence, and that their parts in mixing run towards one another with an accelerated motion, and clash with the greatest force? And is it not for the same reason that well rectified spirit of wine poured on the same compound spirit flashes, and that the pulvis fulminans, composed of sulphur, nitre, and salt of tartar, goes off with a more sudden and violent explosion than gunpowder, the acid spirits of the sulphur and nitre rushing towards one another, and towards the salt of tartar, with so great a violence, as by the shock to turn the whole at once into vapour and flame. Where the dissolution is slow, it makes a slow ebullition and a gentle heat, and where it is quicker, it makes a greater ebullition with more heat, and where it is done at once, the ebullition is contracted into a sudden blast or violent explosion, with a heat equal to that of fire and flame. So when a drachm of the above-mentioned compound spirit of nitre was poured upon half a drachm of oil of caraway seeds in vacuo, the mixture immediately made a flash like gunpowder, and burst the exhausted receiver, which was a glass 6 inches wide and 8 inches deep. And even the gross body of sulphur powdered, and with an equal weight of iron filings and a little water made into paste, acts upon the iron, and in 5 or 6 hours grows too hot to be touched, and emits a flame. And by these experiments compared with the great quantity of sulphur with which the earth abounds, and the warmth of the interior parts of the earth, and hot springs, and burning mountains, and with damps, mineral coruscations, earthquakes, hot suffocating exhalations, hurricanes, and spouts, we may learn that sulphurous steams abound in the bowels of the earth, and ferment with minerals, and sometimes take fire with a sudden coruscation and explosion, and if pent up in subterraneous caverns, burst the caverns with a great shaking of the earth, as in springing of a mine. And then the vapour, generated by the explosion, expiring through the pores of the earth, feels hot and suffocates, and makes tempests and hurricanes, and sometimes causes the land to slide, or the sea to boil, and carries up the water thereof in drops, which by their weight fall down again in spouts. Also some sulphurous steams, at all times when the earth is dry, ascending into the air, ferment there with nitrous acids, and sometimes taking fire, cause lightning and thunder, and fiery meteors. For the air abounds with acid vapours fit to promote fermentations, as appears by the rusting of iron and copper in it, the kindling of fire by blowing, and the beating of the heart by means of respiration. Now the above mentioned motions are so great and violent as to show that in fermentations the particles of bodies which almost rest are put into new motions by a very potent principle, which acts upon them only when they approach one another, and causes them to meet and clash with great violence, and grow hot with the motion, and dash one another into pieces, and vanish into air, and vapour, and flame. When salt of tartar per deliquium, being poured into the solution of any metal, precipitates the metal and makes it fall down to the bottom of the liquor in the form of mud, does not this argue that the acid particles are attracted more strongly by the salt of tartar than by the metal, and by the stronger attraction go from the metal to the salt of tartar? And so when a solution of iron in aqua fortis dissolves the lapis calaminaris and lets go the iron, or a solution of copper dissolves iron immersed in it and lets go the copper, or a solution of silver dissolves copper and lets go the silver, or a solution of mercury in aqua fortis being poured upon iron, copper, tin, or lead, dissolves the metal and lets go the mercury, does not this argue that the acid particles of the aqua fortis are attracted more strongly by the lapis calaminaris than by iron, and more strongly by iron than by copper, and more strongly by copper than by silver, and more strongly by iron, copper, tin, and lead than by mercury? And is it not for the same reason that iron requires more aqua fortis to dissolve it than copper, and copper more than the other metals, and that of all metals iron is dissolved most easily, and is most apt to rust, and next after iron, copper? When oil of vitriol is mixed with a little water, or is run per deliquium, and in distillation the water ascends difficultly, and brings over with it some part of the oil of vitriol in the form of spirit of vitriol, and this spirit, being poured upon iron, copper, or salt of tartar, unites with the body and lets go the water, doth not this show that the acid spirit is attracted by the water, and more attracted by the fixed body than by the water, and therefore lets go the water to close with the fixed body? And is it not for the same reason that the water and acid spirits, which are mixed together in vinegar, aqua fortis, and spirit of salt, cohere and rise together in distillation? But if the menstruum be poured on salt of tartar, or on lead, or iron, or any fixed body which it can dissolve, the acid by a stronger attraction adheres to the body, and lets go the water? And is it not also from a mutual attraction that the spirits of soot and sea salt unite and compose the particles of sal ammoniac, which are less volatile than before, because grosser and freer from water? And that the particles of sal ammoniac in sublimation carry up the particles of antimony, which will not sublime alone? And that the particles of mercury, uniting with the acid particles of spirit of salt, compose mercury sublimate, and with the particles of sulphur compose cinnabar, and that the particles of spirit of wine and spirit of urine well rectified unite, and letting go the water which dissolve them, compose a consistent body, and that in subliming cinnabar from salt of tartar, or from quicklime, the sulphur by a stronger attraction of the salt or lime lets go the mercury, and stays with the fixed body, and that when mercury sublimate is sublimed from antimony, or from regulus of antimony, the spirit of salt lets go the mercury, and unites with the antimonial metal which attracts it more strongly, and stays with it till the heat be great enough to make them both ascend together, and then carries up the metal with it in the form of a very fusible salt, called butter of antimony, although the spirit of salt alone be almost as volatile as water, and the antimony alone as fixed as lead? When aqua fortis dissolves silver and not gold, and aqua regia dissolves gold and not silver, may it not be said that aqua fortis is subtle enough to penetrate gold as well as silver, but wants the attractive force to give it entrance? And that aqua regia is subtle enough to penetrate silver as well as gold, but wants the attractive force to give it entrance? For aqua regia is nothing else than aqua fortis mixed with some spirit of salt, or with sal ammoniac, and even common salt dissolved in aqua fortis enables the menstruum to dissolve gold, though the salt be a gross body. When therefore spirit of salt precipitates silver out of aqua fortis, is it not done by attracting and mixing with the aqua fortis, and not attracting, or perhaps repelling silver? And when water precipitates antimony out of the sublimate of antimony and sal ammoniac, or out of butter of antimony, is it not done by its dissolving, mixing with, and weakening the sal ammoniac or spirit of salt, and its not attracting, or perhaps repelling the antimony? And is it not for want of an attractive virtue between the parts of water and oil, of quicksilver and antimony, of lead and iron, that these substances do not mix, and by a weak attraction, that quicksilver and copper mix difficultly, and from a strong one, that quicksilver and tin, antimony and iron, water and salts mix readily? And in general, is it not from the same principle that heat congregates homogeneal bodies, and separates heterogeneal ones? When arsenic with soap gives a regulus, and with mercury sublimate a volatile fusible salt, like butter of antimony, Doth not this show that arsenic, which is a substance totally volatile, is compounded of fixed and volatile parts, strongly cohering by a mutual attraction, so that the volatile will not ascend without carrying up the fixed? And so, when an equal weight of spirit of wine and oil of vitriol are digested together, and in distillation yield two fragrant and volatile spirits which will not mix with one another, and a fixed black earth remains behind, doth not this show that oil of vitriol is composed of volatile and fixed parts, strongly united by attraction, so as to ascend together in form of a volatile, acid, fluid salt, until the spirit of wine attracts and separates the volatile parts from the fixed? And therefore, since oil of sulphur per campanum is of the same nature with oil of vitriol, may it not be inferred, that sulphur is also a mixture of volatile and fixed parts so strongly cohering by attraction as to ascend together in sublimation? By dissolving flowers of sulphur in oil of turpentine, and distilling the solution, it is found that sulphur is composed of an inflammable thick oil or fat bitumen, an acid salt, a very fixed earth, and a little metal. The three first were found not much unequal to one another, the fourth in so small a quantity as scarce to be worth considering. The acid salt dissolved in water is the same with oil of sulphur per campanum, and abounding much in the bowels of the earth, and particularly in marcasites, unites itself to the other ingredients of the marcasite, which are bitumen, iron, copper, and earth, and with them compounds alum, vitriol, and sulphur. With the earth alone it compounds alum, with the metal alone, or metal and earth together, it compounds vitriol, and with the bitumen and earth it compounds sulphur. Whence it comes to pass that marcasites abound with those three minerals. And is it not from the mutual attraction of the ingredients that they stick together for compounding these minerals, and that the bitumen carries up the other ingredients of the sulphur, which without it would not sublime? And the same question may be put concerning all, or almost all the gross bodies in nature. For all the parts of animals and vegetables are composed of substances volatile and fixed, fluid and solid, as appears by their analysis. And so are salts and minerals, so far as chemists have been hitherto able to examine their composition. When mercury sublimate is resublimed with fresh mercury, and becomes mercurius dulcis, which is a white tasteless earth scarce dissolvable in water, and mercurius dulcis resublimed with spirit of salt returns into mercury sublimate, and when metals corroded with a little acid turn into rust, which is an earth tasteless and indissolvable in water, and this earth imbibed with more acid becomes a metallic salt, and when some stones, as spar of lead, dissolved in proper menstruums become salts, do not these things show that salts are dry earth and watery acid united by attraction, and that the earth will not become a salt without so much acid as makes it dissolvable in water? Do not the sharp and pungent tastes of acids arise from the strong attraction whereby the acid particles rush upon and agitate the particles of the tongue? And when metals are dissolved in acid menstruums, and the acids in conjunction with the metal act after a different manner, so that the compound has a different taste much milder than before, and sometimes a sweet one, is it not because the acids adhere to the metallic particles, and thereby lose much of their activity? And if the acid be in too small a proportion to make the compound dissolvable in water, will it not by adhering strongly to the metal become unactive and lose its taste, and the compound be a tasteless earth? For such things as are not dissolvable by the moisture of the tongue act not upon the taste. End of Section 38. Optics, by Sir Isaac Newton. Section 39 of Optics by Sir Isaac Newton. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. This recording is by Mark Smith of Simpsonville, South Carolina. Optics by Sir Isaac Newton, Book 3, Part 1, Query 31, continued. As gravity makes the sea flow round the denser and weightier parts of the globe of the earth, so the attraction may make the watery acid flow round the denser and compacter particles of earth for composing the particles of salt. For otherwise the acid would not do the office of a medium between the earth and common water, for making salts dissolvable in the water, nor would salt of tartar readily draw off the acid from dissolved metals, nor metals the acid from mercury. Now, as in the great globe of the earth and sea, the densest bodies by their gravity sink down in water, and always endeavour to go towards the centre of the globe, so in particles of salt, the densest matter may always endeavour to approach the centre of the particle, so that a particle of salt may be compared to a chaos, being dense, hard, dry, and earthy in the centre, and rare, soft, moist, and watery in the circumference. And hence it seems to be that salts are of a lasting nature, being scarce destroyed, unless by drawing away their watery parts by violence, or by letting them soak into the pores of the central earth by a gentle heat and putrefaction, until the earth be dissolved by the water, and separated into smaller particles, which by reason of their smallness make the rotten compound appear of a black colour. Hence also it may be, that the parts of animals and vegetables preserve their several forms, and assimilate their nourishment, the soft and moist nourishment easily changing its texture by a gentle heat and motion, till it becomes like the dense, hard, dry, and durable earth in the centre of each particle. But when the nourishment grows unfit to be assimilated, or the central earth grows too feeble to assimilate it, the motion ends in confusion, putrefaction, and death. If a very small quantity of any salt or vitriol be dissolved in a great quantity of water, the particles of the salt or vitriol will not sink to the bottom, though they be heavier in specie than the water, but will evenly diffuse themselves into all the water, so as to make it as saline at the top as at the bottom. And does not this imply that the parts of the salt or vitriol recede from one another, and endeavour to expand themselves, and get as far asunder as the quantity of water in which they float will allow? And does not this endeavour imply that they have a repulsive force by which they fly from one another, or at least, that they attract the water more strongly than they do one another? For as all things ascend in water which are less attracted than water, by the gravitating power of the earth, so all the particles of salt which float in water, and are less attracted than water by any one particle of salt, must recede from that particle, and give way to the more attracted water. When any saline liquor is evaporated to a cuticle and let cool, the salt concretes in regular figures, which argues that the particles of the salt before they concreted floated in the liquor at equal distances in rank and file, and by consequence that they acted upon one another by some power which at equal distances is equal, at unequal distances unequal. For by such a power they will range themselves uniformly, and without it they will float irregularly, and come together as irregularly. And since the particles of island crystal act all the same way upon the rays of light for causing the unusual refraction, may it not be supposed that in the formation of this crystal, the particles not only ranged themselves in rank and file for concreting in regular figures, but also by some kind of polar virtue turned their homogeneal sides the same way? The parts of all homogeneal hard bodies which fully touch one another stick together very strongly, and for explaining how this may be, some have invented hooked atoms, which is begging the question, and others tell us that bodies are glued together by rest, that is, by an occult quality, or rather by nothing, and others that they stick together by conspiring motions, that is, by relative rest amongst themselves. I had rather infer from their cohesion that their particles attract one another by some force, which in immediate contact is exceeding strong, at small distances performs the chemical operations above mentioned, and reaches not far from the particles with any sensible effect. All bodies seem to be composed of hard particles, for otherwise fluids would not congeal, as water, oils, vinegar, and spirit or oil of vitriol do by freezing, mercury by fumes of lead, spirit of nitre and mercury by dissolving the mercury and evaporating the phlegm, spirit of wine and spirit of urine by deflemming and mixing them, and spirit of urine and spirit of salt by subliming them together to make sal ammoniac. Even the rays of light seem to be hard bodies, for otherwise they would not retain different properties in their different sides. And therefore hardness may be reckoned the property of all uncompounded matter. At least, this seems to be as evident as the universal impenetrability of matter, for all bodies, so far as experience reaches, are either hard, or may be hardened, and we have no other evidence of universal impenetrability besides a large experience without an experimental exception. Now if compound bodies are so very hard as we find some of them to be, and yet are very porous, and consist of parts which are only laid together, the simple particles which are void of pores, and were never yet divided, must be much harder. For such hard particles being heaped up together, can scarce touch one another in more than a few points, and therefore must be separable by much less force than is requisite to break a solid particle, whose parts touch in all the space between them, without any pores or interstices to weaken their cohesion. And how such very hard particles, which are only laid together and touch only in a few points, can stick together, and that so firmly as they do, without the assistance of something which causes them to be attracted or pressed towards one another, is very difficult to conceive. The same thing I infer also from the cohering of two polished marbles in vacuo, and from the standing of quicksilver in the barometer at the height of 50, 60, or 70 inches, or above, whenever it is well purged of air and carefully poured in, so that its parts be everywhere contiguous, both to one another and to the glass. The atmosphere by its weight presses the quicksilver into the glass, to the height of 29 or 30 inches, and some other agent raises it higher, not by pressing it into the glass, but by making its parts stick to the glass, and to one another. For upon any discontinuation of parts, made either by bubbles or by shaking the glass, the whole mercury falls down to the height of 29 or 30 inches. And of the same kind with these experiments are those that follow. If two plain polished plates of glass, suppose two pieces of a polished looking glass, be laid together, so that their sides be parallel and at a very small distance from one another, and then their lower edges be dipped into water, the water will rise up between them. And the less the distance of the glasses is, the greater will be the height to which the water will rise. If the distance be about the 100th part of an inch, the water will rise to the height of about an inch. And if the distance be greater or less in any proportion, the height will be reciprocally proportional to the distance very nearly. For the attractive force of the glasses is the same, whether the distance between them be greater or less, and the weight of the water drawn up is the same, if the height of it be reciprocally proportional to the distance of the glasses. And in like manner, water ascends between two marbles polished plain, when their polished sides are parallel, and at a very little distance from one another. And if slender pipes of glass be dipped at one end into stagnating water, the water will rise up within the pipe, and the height to which it rises will be reciprocally proportional to the diameter of the cavity of the pipe, and will equal the height to which it rises between two planes of glass, if the semi-diameter of the cavity of the pipe be equal to the distance between the planes, or thereabouts. And these experiments succeed after the same manner in vacuo as in the open air, as hath been tried before the Royal Society, and therefore are not influenced by the weight or pressure of the atmosphere. And if a large pipe of glass be filled with sifted ashes well pressed together in the glass, and one end of the pipe be dipped into stagnating water, the water will rise up slowly in the ashes, so as in the space of a week or fortnight to reach up within the glass to the height of 30 or 40 inches above the stagnating water. And the water rises up to this height by the action only of those particles of the ashes which are upon the surface of the elevated water, the particles which are within the water attracting or repelling it as much downwards as upwards. And therefore the action of the particles is very strong, but the particles of the ashes being not so dense and close together as those of glass, their action is not so strong as that of glass, which keeps quicksilver suspended to the height of 60 or 70 inches, and therefore acts with a force which would keep water suspended to the height of above 60 feet. By the same principle, a sponge sucks in water, and the glands in the bodies of animals, according to their several natures and dispositions, suck in various juices from the blood. If two plain polished plates of glass 3 or 4 inches broad, and 20 or 25 long, be laid one of them parallel to the horizon, the other upon the first, so as at one of their ends to touch one another, and contain an angle of about 10 or 15 minutes, and the same be first moistened on their inward sides with a clean cloth dipped into oil of oranges or spirit of turpentine, and a drop or two of the oil or spirit be let fall upon the lower glass at the other, so soon as the upper glass is laid down upon the lower, so as to touch it at one end as above, and to touch the drop at the other end, making with the lower glass an angle of about 10 or 15 minutes, the drop will begin to move towards the concourse of the glasses, and will continue to move with an accelerated motion, till it arrives at that concourse of the glasses. For the two glasses attract the drop, and make it run that way towards which the attractions incline. And if when the drop is in motion you lift up that end of the glasses where they meet, and towards which the drop moves, the drop will ascend between the glasses, and therefore is attracted. And as you lift up the glasses more and more, the drop will ascend slower and slower, and at length rest, being then carried downward by its weight, as much as upwards by the attraction. And by this means you may know the force by which the drop is attracted at all distances from the concourse of the glasses. Now, by some experiments of this kind, made by Mr. Hauksbee, it has been found that the attraction is almost reciprocally in a duplicate proportion of the distance of the middle of the drop from the concourse of the glasses, viz., reciprocally in a simple proportion, by reason of the spreading of the drop, and its touching each glass in a larger surface, and again reciprocally in a simple proportion, by reason of the attractions growing stronger within the same quantity of attracting surface. The attraction therefore within the same quantity of attracting surface is reciprocally as the distance between the glasses, and therefore where the distance is exceeding small, the attraction must be exceeding great. By the table in the second part of the second book, wherein the thicknesses of coloured plates of water between two glasses are set down, The thickness of the plate where it appears very black is 3/8 of the 1/100,000th part of an inch. And where the oil of oranges between the glasses is of this thickness, the attraction collected by the foregoing rule seems to be so strong as within a circle of an inch in diameter to suffice to hold up a weight equal to that of a cylinder of water of an inch in diameter, and 2 or 3 furlongs in length. And where it is of a less thickness, the attraction may be proportionally greater, and continue to increase, until the thickness do not exceed that of a single particle of the oil. There are therefore agents in nature able to make the particles of bodies stick together by very strong attractions, and it is the business of experimental philosophy to find them out. End of section 39.
Section 40 of Optics. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information, or to volunteer, please visit LibriVox.org. Optics, by Isaac Newton. Book 3, Part 1, Query 31, continued. Now the smallest particles of matter may cohere by the strongest attractions, and compose bigger particles of weaker virtue. And many of these may cohere and compose bigger particles whose virtue is still weaker, and so on for diverse successions, until the progression end in the biggest particles on which the operations in chemistry, and the colours of natural bodies depend, and which by cohering compose bodies of a sensible magnitude. If the body is compact, and bends or yields inward to pression without any sliding of its parts, it is hard and elastic, returning to its figure with a force rising from the mutual attraction of its parts. If the parts slide upon one another, the body is malleable or soft. If they slip easily, and are of a fit size to be agitated by heat, and the heat is big enough to keep them in agitation, the body is fluid. And if it be apt to stick to things, it is humid. And the drops of every fluid affect a round figure by the mutual attraction of their parts, as the globe of the earth and sea affects a round figure by the mutual attraction of its parts by gravity. Since metals dissolved in acids attract but a small quantity of the acid, their attractive force can reach but to a small distance from them. And as in algebra, where affirmative quantities vanish and cease, there negative ones begin, so in mechanics, where attraction ceases, there a repulsive virtue ought to succeed. And that there is such a virtue, seems to follow from the reflections and inflections of the rays of light. For the rays are repelled by bodies in both these cases, without the immediate contact of the reflecting or inflecting body. It seems also to follow from the emission of light, the ray so soon as it is shaken off from a shining body by the vibrating motion of the parts of the body, and gets beyond the reach of attraction, being driven away with exceeding great velocity. For that force which is sufficient to turn it back in reflection, may be sufficient to emit it. It seems also to follow from the production of air and vapour. The particles when they are shaken off from bodies by heat or fermentation, so soon as they are beyond the reach of the attraction of the body, receding from it, and also from one another with great strength, and keeping at a distance, so as sometimes to take up above 1,000,000 of times more space than they did before in the form of a dense body. Which vast contraction and expansion seems unintelligible, by feigning the particles of air to be springy and ramous, or rolled up like hoops, or by any other means than a repulsive power. The particles of fluids which do not cohere too strongly, and are of such a smallness as renders them most susceptible of those agitations which keep liquors in a fluor, are most easily separated and rarefied into vapour, and in the language of the chemists, they are volatile, rarefying with an easy heat, and condensing with cold. But those which are grosser, and so less susceptible of agitation, or cohere by a stronger attraction, are not separated without a stronger heat, or perhaps not without fermentation. And these last are the bodies which chemists call fixed, and being rarefied by fermentation, become true permanent air. Those particles receding from one another with the greatest force, and being most difficultly brought together, which upon contact cohere most strongly. And because the particles of permanent air are grosser, and arise from denser substances than those of vapours, thence it is that true air is more ponderous than vapour, and that a moist atmosphere is lighter than a dry one, quantity for quantity. From the same repelling power it seems to be that flies walk upon the water without wetting their feet, and that the object glasses of long telescopes lie upon one another without touching, and that dry powders are difficultly made to touch one another so as to stick together, unless by melting them, or wetting them with water, which by exhaling may bring them together; and that two polished marbles, which by immediate contact stick together, are difficultly brought so close together as to stick. And thus nature will be very comfortable to herself and very simple, performing all the great motions of the heavenly bodies by the attraction of gravity which intercedes those bodies, and almost all the small ones of their particles by some other attractive and repelling powers which intercede the particles. The vis inertia is a passive principle by which bodies persist in their motion or rest, receive motion in proportion to the force impressing it, and resist as much as they are resisted. By this principle alone there never could have been any motion in the world. Some other principle was necessary for putting bodies into motion, and now they are in motion, some other principle is necessary for conserving the motion. For from the various composition of two motions, 'tis very certain that there is not always the same quantity of motion in the world. For if two globes joined by a slender rod, revolve about their common centre of gravity with an uniform motion, while that centre moves on uniformly in a right line drawn in the plane of their circular motion, the sum of the motions of the two globes, as often as the globes are in the right line described by their common centre of gravity, will be bigger than the sum of their motions, when they are in a line perpendicular to that right line. By this instance it appears that motion may be got or lost. But by reason of the tenacity of fluids, and attrition of their parts, and the weakness of elasticity in solids, motion is much more apt to be lost than got, and is always upon the decay. For bodies which are either absolutely hard, or so soft as to be void of elasticity, will not rebound from one another. Impenetrability makes them only stop. If two equal bodies meet directly in vacuo, they will by the laws of motion stop where they meet, and lose all their motion, and remain in rest, unless they be elastic, and receive new motion from their spring. If they have so much elasticity as suffices to make them rebound with a quarter, or half, or 3/4 of the force with which they came together, they will lose 3/4, or half, or a quarter of their motion. And this may be tried, by letting two equal pendulums fall against one another from equal heights. If the pendulums be of lead or soft clay, they will lose all or almost all their motions. If of elastic bodies they will lose all but what they recover from their elasticity. If it be said, that they can lose no motion but what they communicate to other bodies, the consequence is, that in vacuo they can lose no motion, but when they meet they must go on and penetrate one another's dimensions. If three equal round vessels be filled, the one with water, the other with oil, the third with molten pitch, and the liquors be stirred about alike to give them a vortical motion, the pitch by its tenacity will lose its motion quickly, the oil being less tenacious will keep it longer, and the water being less tenacious will keep it longest, but yet will lose it in a short time. Whence it is easy to understand, that if many contiguous vortices of molten pitch were each of them as large as those which some suppose to revolve about the sun and fixed stars, yet these and all their parts would, by their tenacity and stiffness, communicate their motion to one another till they all rested among themselves. Vortices of oil or water, or some fluider matter, might continue longer in motion; but unless the matter were void of all tenacity and attrition of parts, and communication of motion, which is not to be supposed, the motion would constantly decay. Seeing therefore the variety of motion which we find in the world is always decreasing, there is a necessity of conserving and recruiting it by active principles, such as are the cause of gravity, by which planets and comets keep their motions in their orbs, and bodies acquire great motion in falling; and the cause of fermentation, by which the heart and blood of animals are kept in perpetual motion and heat. The inward parts of the earth are constantly warmed, and in some places grow very hot; bodies burn and shine, mountains take fire, the caverns of the earth are blown up, and the sun continues violently hot and lucid, and warms all things by his light. For we meet with very little motion in the world, besides what is owing to these active principles. And if it were not for these principles, the bodies of the earth, planets, comets, sun, and all things in them, would grow cold and freeze, and become inactive masses; and all putrefaction, generation, vegetation and life would cease, and the planets and comets would not remain in their orbs. All these things being considered, it seems probable to me, that God in the beginning formed matter in solid, massy, hard, impenetrable, movable particles, of such sizes and figures, and with such other properties, and in such proportion to space, as most conduced to the end for which he formed them; and that these primitive particles being solids, are incomparably harder than any porous bodies compounded of them; even so very hard, as never to wear or break in pieces; no ordinary power being able to divide what God himself made one in the first creation. While the particles continue entire, they may compose bodies of one and the same nature and texture in all ages; but should they wear away, or break in pieces, the nature of things depending on them, would be changed. Water and earth, composed of old worn particles and fragments of particles, would not be of the same nature and texture now, with water and earth composed of entire particles in the beginning. And therefore, that nature may be lasting, the changes of corporeal things are to be placed only in the various separations and new associations and motions of these permanent particles; compound bodies being apt to break, not in the midst of solid particles, but where those particles are laid together, and only touch in a few points. It seems to me farther, that these particles have not only a vis inertia, accompanied with such passive laws of motion as naturally result from that force, but also that they are moved by certain active principles, such as is that of gravity, and that which causes fermentation, and the cohesion of bodies. These principles I consider, not as occult qualities, supposed to result from the specific forms of things, but as general laws of nature, by which the things themselves are formed; their truth appearing to us by phenomena, though their causes be not yet discovered. For these are manifest qualities, and their causes only are occult. And the Aristotelians gave the name of occult qualities, not to manifest qualities, but to such qualities only as they supposed to lie hid in bodies, and to be the unknown causes of manifest effects; such as would be the causes of gravity, and of magnetic and electric attractions, and of fermentations, if we should suppose that these forces or actions arose from qualities unknown to us, and incapable of being discovered and made manifest. Such occult qualities put a stop to the improvement of natural philosophy, and therefore of late years have been rejected. To tell us that every species of things is endowed with an occult specific quality by which it acts and produces manifest effects, is to tell us nothing; but to derive 2 or 3 general principles of motion from phenomena, and afterwards to tell us how the properties and actions of all corporeal things follow from those of manifest principles, would be a very great step in philosophy, though the causes of those principles were not yet discovered. And therefore I scruple not to propose the principles of motion above mentioned, they being of very general extent, and leave their causes to be found out. Now by the help of these principles, all material things seem to have been composed of the hard and solid particles above mentioned, variously associated in the first creation by the counsel of an intelligent agent. For it became him who created them to set them in order. And if he did so, it's unphilosophical to seek for any other origin of the world, or to pretend that it might arise out of a chaos by the mere laws of nature; though being once formed, it may continue by those laws for many ages. For while comets move in very eccentric orbs in all manner of positions, blind fate could never make all the planets move one and the same way in orbs concentric, some inconsiderable irregularities excepted, which may have arisen from the mutual actions of comets and planets upon one another, and which will be apt to increase, till this system wants a reformation. Such a wonderful uniformity in the planetary system must be allowed the effect of choice. And so must the uniformity in the bodies of animals, they having generally a right and a left side shaped alike, and on either side of their bodies 2 legs behind, and either 2 arms, or 2 legs, or 2 wings before upon their shoulders, and between their shoulders a neck running down into a backbone, and a head upon it. And in the head 2 ears, 2 eyes, a nose, a mouth, and a tongue, alike situated. Also the first contrivance of those very artificial parts of animals, the eyes, ears, brain, muscles, heart, lungs, midriff, glands, larynx, hands, wings, swimming bladders, natural spectacles, and other organs of sense and motion, and the instinct of brutes and insects, can be the effect of nothing else than the wisdom and skill of a powerful ever-living agent, who being in all places, is more able by his will to move the bodies within his boundless uniform sensorium, and thereby to form and reform the parts of the universe, than we are by our will to move the parts of our own bodies. And yet we are not to consider the world as the body of God, or the several parts thereof, as the parts of God. He is an uniform being, void of organs, members or parts, and they are his creatures subordinate to him, and subservient to his will; and he is no more the soul of them, than the soul of man is the soul of the species of things carried through the organs of sense into the place of its sensation, where it perceives them by means of its immediate presence, without the intervention of any third thing. The organs of sense are not for enabling the soul to perceive the species of things in its sensorium, but only for conveying them thither; and God has no need of such organs, he being everywhere present to the things themselves. And since space is divisible in infinitum, and matter is not necessarily in all places, it may be also allowed that God is able to create particles of matter of several sizes and figures, and in several proportions to space, and perhaps of different densities and forces, and thereby to vary the laws of nature, and make worlds of several sorts in several parts of the universe. At least, I see nothing of contradiction in all this. As in mathematics, so in natural philosophy, the investigation of difficult things by the method of analysis, ought ever to precede the method of composition. This analysis consists in making experiments and observations, and in drawing general conclusions from them by induction, and admitting of no objections against the conclusions, but such as are taken from experiments, or other certain truths. For hypotheses are not to be regarded in experimental philosophy. And although the arguing from experiments and observations by induction be no demonstration of general conclusions, yet it is the best way of arguing which the nature of things admits of, and may be looked upon as so much the stronger, by how much the induction is more general. And if no exception occur from phenomena, the conclusion may be pronounced generally. But if at any time afterwards any exception shall occur from experiments, it may then begin to be pronounced with such exceptions as occur. By this way of analysis we may proceed from compounds to ingredients, and from motions to the forces producing them, and in general, from effects to their causes, and from particular causes to more general ones, till the argument end in the most general. This is the method of analysis. And the synthesis consists in assuming the causes discovered, and established as principles, and by them explaining the phenomena proceeding from them, and proving the explanations. In the 2 first books of these Opticks, I proceeded by this analysis to discover and prove the original differences of the rays of light in respect of refrangibility, reflexibility, and colour, and their alternate fits of easy reflection and easy transmission, and the properties of bodies, both opaque and pellucid, on which their reflections and colours depend. And these discoveries being proved, may be assumed in the method of composition for explaining the phenomena arising from them, an instance of which method I gave in the end of the 1st book. In this 3rd book I have only begun the analysis of what remains to be discovered about light and its effects upon the frame of nature, hinting several things about it, and leaving the hints to be examined and improved by the farther experiments and observations of such as are inquisitive. And if natural philosophy in all its parts, by pursuing this method, shall at length be perfected, the bounds of moral philosophy will be also enlarged. For so far as we can know by natural philosophy what is the first cause, what power he has over us, and what benefits we receive from him, so far our duty towards him, as well as that towards one another, will appear to us by the light of nature. And no doubt, if the worship of false gods had not blinded the heathen, their moral philosophy would have gone farther than to the 4 cardinal virtues. And instead of teaching the transmigration of souls, and to worship the sun and moon, and dead heroes, they would have taught us to worship our true author and benefactor, as their ancestors did under the government of Noah and his sons before they corrupted themselves. End of section 40. End of Opticks, by Isaac Newton.